All right, everybody, welcome back. We are on the next section here, next lecture, and now we're talking about ALUs, or arithmetic logic units, in section 6353 of my book here. And so basically, the ALU is a functional unit that typically does math and logical operations in a microcontroller or a microprocessor. So for example, say if you wanted to design a discrete little microprocessor or microcontroller out of TTL or CMOS chips, you might use an ALU to do the math and logical operations. So you could actually build one yourself to do it. Now, like with the previous lecture when we talked about the adder, the ALU is like the adder, except it obviously it has many more functions. Now, a real ALU would have many functions in a microcontroller or microprocessor, but obviously based on price and the number of pins and so forth, these ALUs are fairly constrained in what they can do. And then also remember the time that these things were made, the 80s, the 90s, etc. Back in that time frame, they actually were quite powerful. So anyway, read through the chapter, the section as usual. And so what we're going to do is we're going to look at two ICs. We're going to look at the 181, and then we're going to look at, I believe it's a 382 chip. The 181 is here in the book, and it's a good example. And I told you that the simulator wouldn't simulate it, and I was wrong. I actually found the ICs in the simulator. I don't know what was happening. Maybe the search wasn't working, but I found the 181 in the simulator, but not the 382. But I do have a 382, but I don't have a 181. So we're going to simulate the 181, which is in the book, so that's good. Then we're going to build something with the 382, and I'm going to show you a design that you could simulate if the IC had a simulation model. But anyway, so let's just talk about what is an ALU. So let's just get down to business here. So first thing, let's take a look at this data sheet here, 4-bit arithmetic logic unit. And you could read through this stuff, and we're going to look at the data sheet on DigiKey in a moment here. All right. But in a nutshell, and let's see if I don't think, yeah, so this gets really into software stuff immediately. So let's go to the data sheet here. And let's find this 181 data sheet, and this is it right here, I believe. Yeah. All right, so this was found here at Philips, has this 181, and they still manufacture this chip, so you can buy this. Anybody who supplies Philips ICs, you can get this, which is cool. All right, and last time this particular document was updated was 1998, about 18 years ago. All right. And so you read through this whole thing, and at the end of the day, what we really care about are the pinouts of the IC and what the thing does. So from an abstract level, it's got, we can take a look at a couple different things here, but it's got inputs for operand A, it's got inputs for operand B, then it's got the output, which is whatever the result is of the mathematical operation. So that is called the F output. I think over here is probably the best thing to look at it. So here's the input A, here is part of, so there's A and B, A, B, A, B, A, B here. So there's A and B kind of together there. And then here is the output here, which is F. All right, and then here's the carry in, which is Cn, and then here's the carry out, which is Cn plus 4. Here's an extra little pin, which is a comparator that says if A equals B, so that's nice. And then here is the operation selection S0 through S3. So there's 16 different operations. So you can think of it as 16 different instructions. So if you were to use this ALU in a little kind of discrete microprocessor that you might want to design, you'd have 16 different operations that the ALU could do. All right. Then it's got some other funky pins. This G and P, I forget exactly what those are, but we can look at them in a second. And then this M pin, this is the mode select, and depending on if you're doing a logical operation or a math operation, you set that pin high or low. All right. So let's go down to the pin description. So again, here you can see everything here. Now, a little bit of confusion, so I'm just going to try and explain it to you, and it's going to confuse you. It confuses me too. But the inputs can be either active high or active low. So in other words, because you're doing math, you can either say to yourself, okay, a high input is a 1, and a low input is a 0, or a high input is a 0 and a low input is a 1. If you do that, then the outputs also reflect that convention. So everything's inverted. So let's just forget about that. We're going to use active high inputs, and then we're going to assume the output is active high also. So there's no inversion of bits. But the pins have these bars over them to show that you can do it like that also. So we're just going to think of everything as active high. And again, this is about conventions. So if you think of everything active high, then you don't have to worry about it. Now, take a look here. So when you think of everything active high, let's zoom in just a little bit. So we're going to not pretend, but we are going to make input A normal positive logic, input B normal positive logic, and the output is going to be normal positive logic. If you do that, then here's A's and B's. Here's the carry out, and now notice the carry out is inverted. So there's an inversion on the carry out, so you got to be careful of that. Then there's an inversion on the carry in. This memory input, this mode input is normal, okay, and then these G and P outputs are normal. Now, if you were to say to yourself, we're gonna pretend, or our convention is that active low bits, we're gonna do an active low logic convention, then some things change. So now the input is not inverted, the output is not inverted, this G and P are inverted, and so forth. So you see it can get confusing, and the inputs and outputs are all inverted. Anyway, the bottom line is we're using active high operands, so this is what the chip looks like for us. So when you're reading it, don't get confused by all this active low. It's not active low, it's whatever you use, the results will be consistent, if that makes sense. Okay, right, and then here's another, this is kind of a nicer, I like this right here. It shows all the A's and all the B's. Forget the bars over them again. Here's the input carry, there's the output carry, there's a comparator. Forget the G and P, we're not going to use these things. And this is carry generate output and carry propagate output. That's for doing math and cascading, but we're not going to worry about it. And then S0 through S3, select what operation you're doing along with M. All right, let's get to that. Another thing, this is an asynchronous device. It's pure logic, right? So there's no clock to it. So it just takes so much time to get through the logic levels and then get a result. So you basically, if you were to put this in a microprocessor or a microcontroller design, you'd have to look at what's the longest propagation delay and then use that. Or you could potentially use the carry out bits and some of the outputs to figure out when the thing was done doing what it's doing. All right, so here are the two function tables, and so we're going to use active high inputs and outputs. This is the one we're doing, okay? So forget about this. This one don't care about the one on the left. All right, so here's the thing. So now here's what's interesting. There are 4 inputs here, right? So this selects what operation, but depending on how you have this M bit set, this mode bit, either high or low, you have 16 different operations. So how cool, it's really got 32 operations, right? So for example, say you just want to invert the input A. You just want to invert A, right? Okay, so you set S0 through S3 all to low, you set mode to high, and then you will get A inverted on the output. All right, say if you want to compute A or B, this is A or, not plus, A or B inverted, right? Then you would put this code on there. In this second row here. If you wanted A not and B, so on. If you just want a logical 0 output, I just want a logical 0 output, then this one in this row right here, and so on and so forth, right? And then this is XOR, so it has all these different combinations here. How cool is that? Now these are all logical combinations. Now we get to the arithmetic operations, and it really is important to read what these footnotes too. Arithmetic operations are expressed in 2's complement notation. So in other words, anything you do, the results are going to be in 2's complement, okay? So it assumes you're putting your inputs in 2's complement if you want to do addition, subtraction, and all that. If not, it just it'll all work out. All right, so let's say we want to do arithmetic operations, then we need to put mode low. All right, and then we need to put the carry in high. All right, carry in high. Then we could, for say this first code right here, this LLLL or 0000, that would just give us A out. So that gives us just A out. And then say if we wanted to do the OR of A and B, that's it right there. That's A or not B. If you just want a -1, I want a -1, just want a -1. This is how you do it right here. And then now here are the math operations. It uses the word plus and minus to represent math. So A plus the logical operation of A and not B. So you can just go through these. So let's say we just want A plus B. Can we find A plus B anywhere? All right, so looking through these things right here, and remember, plus, P-L-U-S. So here it is right here, A plus B is this operation right here. Can we find A minus B? Is there an A minus B someplace? A minus B someplace. Looking for A minus B, A minus B. I know there's an A minus B. I thought there was. I'm probably looking right at it here. Ah, here we go. A minus B minus 1. So A minus B minus 1. So that right there just would give you A minus B and then with an offset of -1. All right. So anyway, and here's one, A plus A. All right, so that's kind of cool. So what's A plus A? That's really 2 times A. So there's multiplication by 2, right? Right? How cool is that? So anyway, 32 different operations, and the clever programmer could, make Quake Arena with these instructions. All right. So we could build a microprocessor out of this ALU, and I've actually done this before, 20 years ago for fun. So you can, with a couple of these cascaded together. All right. So anyway, that's what the chip does. So that's all we need to worry about. And then actually, I would actually like you to read through this data sheet. And of course, this link or this data sheet will be inside of the materials for the lecture. But if you just search for a 74 HCT 181, you can find data sheets, obviously. But I'd like you to read through here. And then here, this is really cool. This is, of course, the logic design, logic diagram of everything inside there. Let's zoom out one little bit here. So this is everything inside there. So you can see all these different paths. What are the worst case paths? And you can figure out how many gate levels there are, right? What are the total gate levels? So going through here, 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 and finally here, 1, 2, 3, 4, 5, 6, 7 gate levels, right? And so anyway, if we went into the timing area, right? The timing, so let's see, logic mode test, DC characteristics. No, we don't want that. We want AC characteristics, which is what I'm scrolling through right now, and I just want to see if there was some kind of, yeah, okay. So let's look at AC characteristics for the HCT. All right, so AC characteristics, this is what we want. And it's now showing you all these different timing delays. So from carry in to carry out takes a max of 63 nanoseconds at this temperature or at room temperature 42, and then all the different possibilities. So basically you could tabulate all the different timing delays for every different operation, and then your microprocessor or microcontroller that you built could take that in consideration. You could just take the slowest one and make that your clock rate, right, plus a little bit so that you don't get in trouble, or you could try and optimize it where you could break the system into a number of clocks, and you could go do other things while you're waiting for the ALU to finish its computation or to finish whatever it's doing. Okay, but that's processor design, and that's a whole nother class. Okay, so so that's it. That's our data sheet for the 181. Now, let's go to the simulator, and let's see what I've got for you here. All right, so so this is fairly big. I think this is probably the biggest thing we've made so far, and I'm not going to be able to get it all on the screen at once. So I'll kind of scroll around here a little bit. So hopefully I don't annoy you too much. Okay, so again, for those of you that are just jumping all around, this is Lab Center Proteus. It's a CAD program for PCB design and circuit design. So it's like Circuit Maker, except it allows you to do full simulation at the processor level, SPICE simulation, analog, digital, and processor, and that's why we like using it. It's not free. It's fairly pricey, but very cheap compared to other high-end tools that it has the same capabilities. So this is an awesome tool. But you can get a free eval version and run all these simulations, and you can use it yourself. You just can't save, all right? So I know I tell you that every time, but it doesn't hurt for people that are jumping around. All right, so let's look at what we got here. So in a nutshell, Let me see if I can get most of it on the screen. All right, so we've got input A, which is going to be 4 bits. We got input B, 4 bits. We're going to have a bunch of pull-down resistors to ground, and we're using 1K pull-downs so that if we have an HC or an LS version of this chip, it would both work. All right, now one thing at a time. Let's deal with one thing at a time. So here's the 4 inputs for the input A, and I'm going to put those into the ALU as operand 1, which is A. Okay. And then here's the inputs for B, and I'm going to put those into the B. All right, low bit is going to be this top, and most significant bit will be down here. So low to high, low to high. All right, so there's our 2 operands. So far, so good. Okay, at the same time, I'm going to take each one of those so we can visualize them, and I'm taking these wires right here, and I'm putting them into a 74LS47. Display driver, and then with a 7-segment display, common anode, so we can see what these numbers represent. So this is the beauty about electronics. Here's the data right here, right? I just take those 4 wires and go take them someplace else. As long as I stay within the fan out of everything, fan out and fan in, I'm okay. So this works. And so we can see what that value is. Same thing with B. Here's B right there. And basically I just copied and pasted this block right here, which we've already done in previous things. How cool is that? All right, going back to the chip. So here's our ALU chip, our 748CT181. There's an HCT, there's an F version, there's an HC version, an LS, many versions. Now they're harder to find. So I've got a bypass capacitor there to our 5 volts. All right. And what else do we have here? So we have our output F0 through F3. Here's the low bit to the high bit going into another 7-segment display and outputting here on a green output. And I call this input A, input B, and the result. What are these capacitors for? These aren't particularly bypass capacitors for noise. What they are is charge storage. So when this LED turns on all the LEDs, it could pull quite a bit of current. It could pull, 70 to 140 milliamps of current, and this capacitor will be a local storage so that when it needs that current, it can get it from the capacitor instead of pulling it from the power supply and causing a little dip on the power supply potentially, just for a nanosecond or a microsecond or a millisecond. But still, better to have it there than not. Okay, here are the outputs. A equals B, so we've got this diode equal there, little red LED, and then we've got this carry out right here. All right, and the carry out was inverted, and I don't think I've checked this and made sure of it, but since it's inverted out, we've flipped the diode so that we've got the cathode pointing here. So when it's on, this would be a 0, low, and then the LED would turn on. And here's a mistake. So this right here. Oops, this right here, since this is the cathode, we need to hook this up to +5. So let's do that. Good. And going over this stuff always helps because you catch mistakes there. Save that. Okay. Let's see here. All right, let's go down here to some of these other inputs. So here's the carry in, right here, and I've got it just to a momentary switch. In this case, we can turn this momentary switch on and off, and when it's off, we'll get a 1K pull down, and when it's on, we'll get a 5 volts, which is a 1. Okay, that's the carry in. Then the mode control, here's the mode control. So when it's high, when it's on, 5 volts, right? That's going to do logic operation. That's going to select logic operation. Now, here's a bitmap. In this tool, you can actually take images and put them inside the circuit design, which is really helpful. You can grab a data sheet and put it there, or some image or a graph, and it just kind of helps. So you can see here's that table that was in the data sheet, and we can see when M equals H, that selects the logic column. When M equals L, and you've got a set carry into high, that selects the arithmetic functions. So that's what that mode control is. Again, we're just going to use a little momentary switch. And then finally, we have our operation selection here, S0 through S3. There's that S0 through S3, and that's on this dip switch right here. Again, we've got pull downs on there, so when we turn the switches on, it gives 1s. We output 1s. All right, so it's a positive logic switch. All right, and that's it. That's the entire thing. So in a nutshell here, we are going to be able to basically build, this is a calculator. It's a very crude calculator. We got to do things manually with putting in inputs, but this could be the basis of a computer. So what would we need to make a computer? We would need a memory. We would need a state machine. We would need a program counter and some other things, which is just some counters. and we're going to talk more about counters in the next chapter, actually. And we would basically have a program in memory, which would be bit patterns. Those bit patterns would be these actual instructions, S0 through S3. And so this program counter would go pull a piece of memory, and then it would put it on a bus, like this S bus we would call it. This thing would execute that instruction. Then a state machine would click through and add 1 to the program counter, and then go get the next instruction and the next instruction, and then run them through here. And then whatever the program was, we would see the outputs, or would do whatever do. And that's the basis of a microprocessor. So that's how you do it. All right, so let's go ahead and run the simulation here. In fact, first let's reset everything. All right, so once again, these are confusing. I hate the way these things are colored. But where the black is where the switch is. So this is on, and this is off. So let's turn these all off. So this should be 0, 0, 0, 0, 0, which is 0 in decimal. And for the code here, let's also make this 0. All right, let's leave the carry in high. In fact, yeah, we'll just leave the carry in high, and we'll leave the mode. Let's see, the mode right now is 1. So carry in high and mode. So let's be careful here. Let's first select these logic operations. How about let's just put it in logic operation mode. So we're going to make mode equals high. So mode equals high, and then I'm not going to care about the carry, so I'm just going to make the carry low right now. So when mode is high, we're going to select these logic operations. We're going to have to play with this, and this is going to be very painful for me trying to switch this and see what's going on here. Okay, so here we go. Let's just run this thing. Okay, now, okay, so we've got a 0 for A, we've got a 0 for B. All right, so let's just start there and make sure we're knowing what we're doing here. So if I click the 1 bit here, I'll get a 1 over an A, and let's scoot this over just a little bit so you can see. There we go, a little bit. And this does not have, this has got the worst scrolling. You can kind of only do this, there's no smooth scrolling. All right, so now let's do the 2 bit. So you can see A is changing. Let's put a 3 on there. Okay, so we can just do this independent of everything, right? Now let's go to B. Let's put a 4 on B. Let's put a 5 on B. Okay, so let's put a 7 on B. So that's all working, right? Okay, so let's go ahead and let's get 2 things that we know. Let's get a 1 on A, and let's get a 3 on B. All right, a 1 and a 3. 3. There we go. So we got a 1 and a 3. So now when we do math operations, we can figure out what's going on. Now, when we look down here, we're like, what is this upside down F thing? Remember, the 7447 only has kind of known symbols for 0 through 9. 10, 11, 12, 13, 14, and 15, the other possibilities for a 4-bit code, it uses these other bizarre symbols instead of hex symbols or something like that. So whatever operation we've got this thing set to, it's doing it, and then the result is just displaying, and it's like it's a 10, 11, 12, 13, 14, or 15, and who knows. So let's do something we know. All right, so let's forget about what's up there. We know we've got a 1 and a 2. We can forget about it for a minute. All right, so mode control is high. So we got that set on high, the switch is down. We got the carry in low. It doesn't really matter. When the mode control is high, we're doing a logic operation. Okay, now, so that means we're in this column right here. All right, so let's select something we can kind of figure out, right? Okay, so for example, if we were to select all highs for the inputs, we should just get A back. So we should just get a 1 back. All right, so let's try that. Let's make it all highs. All right, so here we go. We're making it all highs. Remember, where it's black is the switch. So we need to put them all over here. Okay, and remember, red is high and blue is ground. So these are all highs. We've selected this command here, which is give me back A. Give me back A. All right, and sure enough, there's A, and there's A right there. So that worked. All right, let's try another one. How about B? Okay, so to get B, it's high, low, high, low. All right, high, low, starting from S3. So here's S3. Okay, so this needs to be high, low, high, low. Am I right here? Let me take a look here. So this is supposed to be high. Yeah, that's high, low, and then this is high, low. There we go. Okay, high, low, that should give us back B. All right, and there it is. B was 3, and then we're getting 3 here. Okay, so we're just pushing A and B, our two operands, right out. So we're, that's it. So that's like adding 0 to each one. All right, now let's do something a little bit more interesting. Okay, so why don't we do, how about this? A XOR B. Okay, so now let's not try and do this in our head. So we've got 1 and 3, all right, 1 and 3. So let's go over here to the blackboard. All right. Okay, so we've got 1 in a 4-bit binary. So this is 0, 0, 0, 1, and we've got 3, which is 0, 0, 1, 1. And the question is, and then this is this is operand A, and this is operand B, and we want to do A XOR B. A XOR B. So that means wherever the bits are opposite, you get a 1. Wherever the same, you get 0. So let's do it. So right here, are they opposite? No, we get a 0. Here, are they opposite? No, we get a 0. Are they opposite? Yep, we get a 1. Are they opposite? Nope, we get a 0. So what's this result here? This result is, if you look at this in binary, this is the 1's place, the 2's place, right? 4's and 8's. So this just equals 2. So the output of A XOR B should be 2, all right? Let's hope it is. Let's go back here, all right? So we're going to do the XOR operation, which is this one right here. We're going to do A XOR B, and then there's A naught XOR B naught, or there's A XOR B not, but we just want A XOR B. Okay, so what's the code? It's low, high, high, low. So it's 0, 1, 1, 0, 0, 1, 1, 0. So here we go, 0, 1, 1, 0. So we need zeros on the end here. So we want zeros on the end. So there's a 0 on that end. There's a 0 on that end. So, and there's a 1, 1. All right, so 0, 1, 1, 0. All right, that should be 0, 1, 1, 0. So that should be A XOR B. All right, and dun dun dun, dun, we got 2. It works. All right, very painful, very slow process, but it's super cool. All right, so it would be a lot easier if there were buttons for each one of these operations, right? Like on your calculator, right? I've got buttons here for times, divide, subtract, all those things, and you could see putting it on a dip switch is a nightmare. Let's do one more though. Let's do one more here. How about let's go over here and do the arithmetic ones. Let's find A plus B. Where's A plus B? Here it is right here. So A plus B is high, low, low, high. So it's high, low, low, high. All right, so let's make sure here. A plus B is high, low, low, high. So first let's get the command code right. All right, so we want high, low, low, high. So we want high, low, low, high. Okay, so high, low, low, high. So that's the correct command code. Now we need to switch the mode to low and the carry into high. All right, so the mode to low, where's our mode switch? There. And now we need the carry in. We need to make that high. Okay. Okay. And now it should have added them together. And sure enough, 1 plus 3 is 4. So that's it. So that is your arithmetic logic unit. Pretty awesome. And it's doing everything it's supposed to do. So you can sit here and play with this. And again, the simulation is called Crash Course EE ALU 74 HCT 181_01. All right. So that's that one right there. And I don't think I have another a number 2 version of that. Let's see here. No. Good. All right. Okay. So now what I'd like to do is let's go ahead and let's stop here. And then what we're going to do next is we are going to, we want to ultimately build something over there, and we can't build anything with this chip because I don't have it. And I could order it, but it's a little complicated because it's got so many operations. So what we're going to do is we're going to use a different IC, and we are going to use this one. We're going to use the 74 F382. It's very similar to the previous one. It's still got the AB inputs. It's got the F outputs here. It's got an overflow output, a carry output, a carry input. But it's only got 3 input codes, S0, S1, S2. All right, you can see it here in this one a little bit better. So it's only got S0, S1, S2. So that means 8 codes, 8 operations, okay? So if you go to this little table here, where is the table? Here it is here. So here are the operations we can do. We can clear, we can do B minus A minus B, A plus B, and then we can do A XOR B, A or B, A and B. So it's a basic good set of math and logic operations, and from this you can get a lot of other things. So it's a little bit easier to hook up, all right? So let's go ahead and stop the lecture right here, and then let's start back up, and we will talk about this chip, and then ultimately we're gonna end up on the bench, all right? So I'll see you in the next lecture. Bye. Welcome back. We're on the next lecture. We're continuing our coverage of the ALUs. We just kind of broke the lecture up and just kind of stopped it so we didn't do a long lecture this time because we're talking about kind of the same thing but two different ICs. So in the previous lecture, we talked about the arithmetic logic unit and we used the 181, if you recall. And we built a simulation. We actually ran the simulation and that all worked fine. Now what we're going to do is we're going to use a different IC, but I actually have this one. So my goal is we're not going to do a simulation because we can't, because the simulator does not have a model for this IC, the 382. And this is a more simplified ALU, but I do have an actual IC over on the bench. So we're going to build what we are going to review. And then also what we're going to do is we're going to play around with the input buttons. And if you recall, we had a dip switch that switched everything. So let's just take a quick look here. So before we had a dip switch to select the operation, and now you can see I've got some logic here and then a bunch of switches. So we're going to look at that in just a moment, all right? So let's go back to the data sheet we were just looking at. So the 74F382 and this IC is very similar to the 181. So it's got an input A and B, A, B, A, B, A, B. So you've got two 4-bit operands, and then you've got a control or operation select code, which is S0 through S2. You've got a carry in, which is called CN, and then you've got a carry out, which is CN plus 4. And then you've got an overflow output here. All right, and then you've got ground and power as usual. All right, so that's what the IC is. Now let's get down here and then of course here's, this is kind of showing you the textual names and then what everything does, their functional descriptions. And then here's some interesting things right here. These pin names, description, and then here's this unit loading fan out. So this is this A and this is this B. So what this is saying here is that unit loading is these A inputs and B inputs basically act as one load as an input when they're high, and then they act as 4 loads when they're low. So this is kind of telling you some of this loading information, how much current is going to be required to drive this. This is a 74F chip, and these are faster ICs, and they take more current. All right, they're TTL, but they're a F version. So that's something to pay attention to right here also. All right, here's the function select table. So we have, instead of 16, well, actually we had 32 different functions in the previous IC, and this one we only have 8. All right, and it's simpler. So we've got a clear, we've got B minus A minus B, A plus B, A XOR B, and A or B, and then A and B, and then preset everything to 1. All right. Okay, here's showing some of these speeds here. So path segment is from A or B to the carry in to carry out, and let's see here, anything else interesting. So you can take a look at all these different path lengths here, and 27 nanoseconds. So this is a very fast IC. This is a very fast version of this arithmetic logic unit. If we take that 27 nanoseconds, let's take the 27 nanoseconds. Let's see what we're dealing with here for clock rate. So it looks like we would be talking about 37 megahertz. So if we were to run a system and use this as the ALU, we could probably run the system comfortably at 30 or 33 megahertz and assume that the ALU would have its math done in 1 clock cycle. All right, if not, we just use 2 clock cycles to do the math, right? If we want the processor to run faster, or the state machine. All right, so that is this IC, and let's see if there's anything else here interesting. This is just the truth table, and then here's the design, which we like looking at. And these things, this is exactly what's in there. So you can take a look at that, and you can see here's the F outputs, F0, F1, F2, F3, and then you can see here's that overflow, and here's that carry out. Notice that these outputs here, uh, notice they have, potentially an extra level of logic here. So all of these outputs here kind of have these in front of them. Then this situation here is selecting what's going on, right? And then over here, there's some complexity here. And this says for the F381 only, and then this is for the F382. So see this F381, you can barely see it probably, but this is this one is has a lot of carry look ahead features in it. We're using the F382. Okay, all right. And then the DC and AC characteristics, again, we already saw that kind of table up top, which says it's about 27 nanoseconds. Okay, all right, so that's the IC that we're going to use. You can see this was last updated in 2004, so this is fairly, it's 10 years old from this last update roughly. So you can still find these ICs and use them, just like the previous one. All right, so let's go to the tool. Okay, so we're here in Proteus once again, and again, for those of you jumping around, this is a CAD tool for PCB design and schematic design, but it has a very advanced simulator in it. That's why we're using it. It's a Lab Center Proteus. You can download it an eval version for free off internet if you like, and then you can follow along. You can run the simulations. You just can't save anything, and you can't generate Gerber files. Anyway, so again, this is a pretty complicated circuit. It looks almost identical to the 181 version we just did. All right, so let's go through here again and see what's going on. So first we've got our ALU right here at U574, and this just is LS382. It's just the version of the IC that was in the CAD program here. All right, but we've got an F that we're going to use. The pinouts are the same. All right, so we've got the inputs A0 through A3, B0 through B3. So these are your two 4-bit operands here and here. We're getting those from two dip switches, just like normal. We've got pull downs on them, so when we turn the switches on, we'll get active highs. All right, so that's how we feed the information into the ALU. All right, then so we can visualize them, here's A. We take the 4 bits of A and we put it into a 7447 common anode display driver with a 7-segment display. We do the same thing for B, so we can also look at B. And then this right here is no longer plus. This is really more like the operation we're doing, right? We'll just call it op. All right, move that a little bit. Okay, all right, so that's the operation. All right, and then out here we've got overflow and we've got the carry. Now notice they have bubbles on them, and so I haven't built on the Sawdust breadboard this design yet. So when I do, we'll find out exactly. I believe these are inverted as shown here with bubbles over them, and we could confirm that in the data sheet, but sometimes active low, active high, a little confusing, but I think they're active low, which means that the cathodes will be pointed towards the IC, so when these are low, these LEDs will turn on. So I think this is correct. If not, we'll flip them. We'll figure it out. Okay, now what else do we have here? We've got carry in, which again, we're just using a switch with a pull down and then a switch that pulls it up to high 5 V sub CC. And then now we have this whole situation here, right? So let's take a moment to take a look at what's going on here. So first I want you to see the other version, this one. So this is, and let's change this to OP. Oops. For operation, because it's no longer just an adder, it's an ALU. All right, so this is very similar to how we did the operation select for the 181. We just put a dip switch there, but we found out that was pretty tedious. We had to look in the table, look on the data sheet, kind of figure it out, switch the switches, kind of a pain. It's not like a calculator. But since there's only 3 inputs here, right, there's these 8 different combinations which are shown in this table right here. So if it's 0, 0, 0, that means clear. We're going to call that opcode 1. All right, high, low, low, that's B minus A. We'll call that opcode 2, and so forth, down to opcode 8 here. All right, so the question is, could we design a bunch of switches and some logic so that for every one of these inputs, S0, S1, S2, we could output the correct data depending on what operation that you want to perform, all right? And it would simplify this from a user aspect. It may be more complicated because there's more ICs, all right? So let's go here, back to this. And that's exactly what's going on here. So, so now what I'd like to do is we're going to take some time and we're going to actually figure this out, and we're going to go through the exercise that I did to figure this out. So these 3 input selects basically have 8 different patterns. So instead of having a dip switch and putting the binary pattern for the desired operation, opcode 1 to opcode 8, right? I would rather just press one button. So if I want to do A minus B, I want to press this button right here, and I want it to happen. So what that means is every one of these buttons somehow has to generate a binary pattern of 3 bits. So what's one way we could do this? What's one way we could do this? So one way that we could do this is we could go and do something like this. So let's say that we have a lookup table. So here's a lookup table. And let's say that we have 8 inputs, 1, 2, 3, 4, 5, 6, 7, 8, okay? So these are our inputs right here. And each one of these is a desired opcode. So this is operation 1, this is operation 2, this is operation 3, and this is operation 8. Now, on the output here, we've got 3 outputs. And those outputs are what? They're S0, S1, and S2. Okay, so what we could do is, so we basically have these 8 input lines here. We have these 8 input lines, all right, and each one of them is mutually exclusive. We're never going to press 2 of them at the same time. We're only going to do one at one time. So if I press op2, what do I want? So if I press op2, operation 2, all right, I need a high, low, and a low. I need a high, low, and a low, all right? So if I want op2, this one here, I need a high, a low, and a low. All right, let's take a look at that. So S0 should be high, low, and a low to get op2. All right, so this would be operation 2, op2, right there. Let's say we want op5. What's op5? Op5 is low, low, high. So we want low, low, high is down here, would be operation 5. Okay, so we want these S outputs to output these bit patterns on 8 different buttons here. All right, so there's a couple ways we could do this. we could use a ROM, right, a lookup table. So we've got 8 different inputs. Now they're mutually exclusive, so this is going to waste a lot of memory. So 8 different inputs, that would be 2 to the 8th, which means 256. So if we had a 256 ROM memory or flash memory, a 256 byte, that's all we need is 256 bytes. We could just take 3 of the outputs, right? And in those outputs, for each one of these different addresses, we would put the bit pattern. So what would that look like? Let's actually do it, all right? So let's assume that these are address lines, okay? So let's assume this is A0, A1, A2, dot, 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 down to A7. Okay, so when you press this op1, right, and we put a high there, right, so that would be a 1 there. When we press op2, we'd get a 1 here. We press op3, we'd get a 1 here, but we're not going to get any other combination. So the only addresses that we need to fill up in memory are these. So they would be this: memory location 1, 2, 4, 8, 16, 32, 64, and 128. So at each one of these memory locations in this ROM memory, so here's this ROM memory, and it's got all these memory locations in it, right? And it's from 0 all the way down to 255 are the addresses here. And in each one of those memory locations, we need to put something. But we only need to put something in memory location. So memory location 1, right? Memory location 2, memory location 4, memory location 8, 16, 32, 64, 128. What do we need to put in there? We need to put this binary pattern. So now if this was the output, let's say that this was the output, and each one of these is output. So this is, we'll call this data D0, D1, D2, D3, 4, 5, 6, 7, and D7 would be down here, but we don't even care about those. We'll just make them all zeros. So here we go. So for memory location 1, so memory location 1 here, which would be operation 1. So for operation 1, let's get back to this. So for operation 1, so what's the pattern for operation 1? It's low, 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 okay? So we would put, in this memory location here, we'd put 1, 2, 3, let's do a different color. Do a different color here. All right, so the upper 5 bits are always going to be zeros. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, because we don't care about those. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, now Then we'll put a line here. Okay, now the lower 3 bits, which is going to be D2, D1, and D0, right? That's what we have to worry about here. So and this is basically opcode 1, this is opcode 2, this next one is opcode 3, this is opcode 4. See how this numbering is working? Opcode 5, this is opcode 6, this is opcode 7, and then this is opcode 8. Okay, so this was opcode 2, and this is opcode 1. Okay, so at opcode 1, that's at memory location 1, all right, and we come back here, and that is low, 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 all right, low, low, low. So we're just going to put a 0, a 0, a 0. Let's go look at opcode 4. At opcode 4 here, opcode 4, that's going to be high, high, low, high, high, low. Opcode 4, so we want high, high, low. All right, and let's go look at opcode 8. Opcode 8, here it is. That one happens to be high, 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 so that one's pretty easy. Opcode 8 is high, high, high. So now you see what's happening here. We're going to fill up this ROM, so we actually program this ROM or flash that would have these bit patterns inside of it. So then we would connect switches to each one of these. So each one of these would then basically connect to a switch. And we just have a momentary switch there, right? And the momentary switch would go up to our +5 V sub CC, and then the other end of it here would just go down to a pull-down resistor like that. Let's clean that up. Okay, that's horrible. Sorry. All right, let's clean this up. Let's make this cleaner. All right, so let's just show you exactly what one of these would look like. Let's do it nice. Not in a rush here. It's not like we're driving. All right, so let's take this out. All right, so here would be our momentary switch, like that. Okay, so this end would go, this end would go up to +5 volts, or whatever your V sub CC is, and then this would go down to ground, and this would be your 1K or 10K pull down, all right? And then you would have 8 of these switches here. So this would go into this ROM, and then the ROM would output. So the ROM basically does all the computation for us instantaneously, right? Whatever the ROM delay is or propagation delay, and that's it. How cool is that? So that's one way to do it. So if you had a 256 byte flash or ROM, you could implement the system like this. Let's go take a look at that real quick. Let's go take a look. Let's go to DigiKey. Where'd DigiKey go? And let's say 256 byte flash, right there. Can we find one? So memory, 186 different devices. Okay. Now the problem here is these are all serial. So see this? They're all serial. All right. So let's say parallel flash memory, parallel flash. And give DigiKey a second to go through its billions of parts. Okay, let's try again. That's a little bit better. All right. Now there's 6,000 devices here. All right. So we want flash memory. We want non-volatile, obviously. And then memory size here. So these things are all very, very, very large. So everything is huge, huge, huge. Like, let's just take a look at this 32K. That would be a lot of waste. We'd waste a lot, but that's okay. And I'm sure we could find what we're looking for. Okay, so in stock, nothing there. Is this in stock? Okay, there's one. All right. So this is not really what I wanted to find, but if you were to take a look at this right here, this is obsolete. It's 64K by 8, it's parallel. Let's take a look at this. So this is a static memory. So this is what we would do here. So here's the DIP. NC means no connection, of course. So we would put our switches to A0 through A7. So there's where our switches would be. Then all the other address lines, A8, A9, A10, A11, 12, 13, 14, 15, those would be all tied to ground. Okay. Then here's our outputs, our data bus. We're only reading from this thing. So then we would basically take IO0, IO1, and IO2. Those would be S0, S1, and S2, right? And then we would basically chip select or chip enable. CE is chip enable, and then we would tie output enable low, right? And then we would have write enable would be high, and then we could read this thing with different addresses. There you go. And then to write it, of course, we'd have to do the write cycle and look in the data sheet how to write it to fill it up with the proper data. And then we can see right here, here's the programming cycles, chip erase, and different things here in the data sheet. Right? And you can get a programmer to do this also. So that's one way to do that. That's kind of a crazy way, right? But a lot of people would do that because it would be simple and you could reprogram it to anything you want. All right? Or we can do it with logic. Okay, so now let's go back to this. Let's take a look at this. All right, so we're looking at the schematic here. And so we've got three inputs, S0, S1, and S2. All right, and based on these buttons, I want to generate a signal that gives me this truth table based on these mutually exclusive buttons somehow. So if you look at this for a little while, you figure out, well, we're going to need something for S0, something for S1, and something for S2. All right? Now, then go look at this data table. So now forget about S1 and S2, just look at S0. So S0 basically is high, high, high only when you're doing operand or opcode 2, 4, 6, and 8. So it's high, 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 2, 4, 6, 8. So if we were to OR the buttons for 2, 4, 6, 8 and together, OR them together and put that into S0, that would give us S0. So take a look. So I have each one of these little buttons here. Normally they're going to output a 0. When you press it, you're going to output a 1, all right? So now, let's look at this one right here. So this says, if we look at this, if we were to OR, right, so the only time S0 is ever high, we ever need to make it high, is when you're doing operation 2, operation 4, operation 6, operation 8. So 2, 4, 6, 8. So then we basically go here we go, 2, and we put that into our OR gate. Where's 4? Here's 4. And carefully, there it is right there. All right, where's 6? Here's 6. And carefully, there it is right there. And here's 8. And here it is right there. So we basically just take those wires and put them into this OR gate. So whenever you press any of those, we know that S0 will be correctly assigned a value. Now let's do S1. So you look at S1. When is it ever high? Well, it's only high on opcode 3, opcode 4, opcode 7, and 8. 3, 4, 7, and 8. Okay, so here's 3, which is the button for, A minus B. So 3, 4, 7, 8. So here's 3. There it goes into there, right? There it is right there. Here's a 4. There it goes right there. All right, and then here's this one. There's 7. You can see it lighting up. And then here's 8, 7 and 8 with just these two. All right, and then S2 is the same thing. So S2, let's take a look. What's S2? It is high only when you have operation 5, 6, 7, and 8. So 5, 6, 7, 8. So this one, there it is. It goes, there's the 5. Here's this one going to 6. Here's this one going to 7. And here's this one going to 8. All right, now, this clear button. So what does clear go to? Well, when we're doing a clear operation, it's always 0, 0, 0. So basically, if none of these things are on, we're going to get zeros out of all these. So it's always going to be in clear mode. So its default will be clear. So in fact, this is redundant. You don't ever have to press to clear. It's just clear at all times. So if you have no operation, it's clear at all times. So you notice this doesn't connect to anything. All right, so it's always clear. All right, so now say if we wanted to add two numbers, well, we'd put our first input on A, our other input on B. We'd see the two numbers here, right? And then all we do is just press the button for A plus B. This one, just press it. Boop. And the second you press it, you would see A plus B. Now we want to see A minus B. Well, just let go of that button, press A minus B. Boop. And you would see the result there instantly. So we don't have to go figuring out what codes to put on dip switches. All right, so isn't that cool? Now, the only reason this works perfectly is because they're mutually exclusive by agreement. If you start pressing multiple buttons, you're just going to get, random stuff going in here, and you're going to get a bunch of stuff that you can't hurt it, because the only things you can get are these 8 different codes, but you're not going to get what you expect. So if you put plus, A plus B and A minus B, what's the result of those things, right? It's not going to make any sense. It's going to be some operation you didn't expect. So anyway, so this is what we're going to build. So what we need are dip switches. We need 3 7447s. We need 3 displays. We need a couple LEDs. We need some 4 input OR gates, or we could use 2 input gates. We could use 4 packages that have 4 2 input, and we could do a 2, and then tie the outputs of that into another one. So we're probably going to need 3, because I don't think I have these chips here. We're probably going to need 3 OR gate packages that have 4 OR gates per package, and each OR gate has 2 inputs to build this. And then we'll have our 8 switches here, and we're going to build this little calculator thing. Okay, so this is going to be cool. So I've got the chip over there. So we're going to stop here. We're going to go to the bench, and I'm going to build it, get it working, and then we'll take a look at it. Okay, so I'll see you on the bench. Bye. All right, welcome back. We're on the next lecture, and what we've been talking about is the arithmetic logic units, and we previously built let's take a look, we built a circuit using the 181 IC, which is the ALU, and that particular ALU had 32 different functions, 2 banks of 16. But I did that IC inside of my inventory. But what I do have in the inventory is the 382, and I have a 74F382. All right, so we've built up this circuit here in Proteus, and we've talked about this. And what we're going to do now is we're going to take a look at the bench, and I built this on the bench. And in a nutshell, what this does is we have 2 input operands that are 4-bit, A and B, and then these go into the arithmetic logic unit, A and B, and then we select the operation with these buttons here, and the default operation is clear. So if you don't input anything, it's always clearing as the 0, 0, 0 operation you can see in this table here. Low, 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 it's clearing. So any of these other bit patterns on S0, S1, S2 select these operations: B minus A minus B, A plus B, A XOR B, A or B, A and B, and preset. All right. Then what we did was we took a bunch of switches so that we could press buttons instead of set dip switches, and then we looked at what these values were, and then we created gate inputs to OR gates so that we figured out what S0, S1, and S2, what these inputs would need to be to facilitate each one of these operations with these buttons. All right, so each one of these are momentary buttons. All right, then let's see what else we have here. We have the displays, so we've got 7447s coming out of connected to the output of the ALU, so we can see the result. And then we've just picked off A and B and put those through 7447s to display drivers as well. Okay, so that is what we have here. And the only other thing is the carry-in, which the only time we care about that is if we're cascading something or if we're going to do a subtraction, you have to set the carry-in. And I think that's about it. So I've basically replicated this over on the development board, on the solderless breadboard. So let's go over and take a look at that and see what's going on there. All right, so let's go over to the bench, and what we're going to do is we're going to try some of these operations here and actually watch them output in real time. All right, so let's go over and take a look. Okay, so here we are on the bench, and this is the entire circuit here. All right, and so there's, I believe this one is A and this is B, or it's the other way around. We'll get to that in a second. And then here's the solution, or the output from the arithmetic logic unit. So, and here's the arithmetic logic unit. And then here's our 7432, our OR gates, which kind of create each one of these button presses. Here are those 3 selection lines that go into the 74F382. And then here's display driver, display driver, display driver. And then here's our carry in bit. So it's pretty straightforward. Now, the only thing, so I've just realized what I've left out here is the carry out and overflow bits. So the carry out, looking at the schematic, is on pin 14, and there it's inverted. So that means it's going to be active low. So why don't we, what do you think, use a red LED, little red LED? We'll use a red LED, and then let's get a 100 ohm resistor, and we'll put that in series. All right, so let's find pin 14 here. So the, and let's make sure these wires don't come out. We'll never figure out what's going on here. This took quite a long time to do this. And, you know, this is not the cleanest thing, but it's not the messiest thing either. It's not bad. There's, you know, I try to keep buses and all this. But again, you don't want to spend 20 hours building these things, right? You just want to get them to work, try things out. And then if it doesn't work, then you clean it up. All right, so pin 14 we're looking for on the 74F382. And the chip is a 20 pin, I believe. Let's count it right here. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it's 20 pin, 10 on each side. And again, you know, constantly just do sanity checks. When you're counting pins, remember they go from pin 1, it increases, and then it wraps around this way counterclockwise always. So like these display drivers, I believe these are 16 pin, 1, 2, 3, 4, 5, 6, 7, 8, yeah, and the other 8 over there. You can look on the data sheet, of course, but just, that way it just kind of helps you. All right, so we want pin 14. So this is 1 through 10, 11, 12, 13, 14. So pin 14 is right there. Now, what I'm going to do, I think, is I'm going to bring a line. I'm trying to find a kind of a good place here to put this. So let's bring this way out. Let's bring this way out. So what we're going to do, pin 14, and again, this is, as you do this stuff, you got to kind of make these decisions as well. We could put it right here, but I kind of feel like I want it way over here. So what I'm going to do is I'm just going to take our resistor here, our current limiting resistor, and I'm going to put it right there. And then remember, this is active low, so I'm going to put the cathode. I'm going to put the cathode towards the resistor, and then I'm going to connect this to high, like this. Okay, cathode is towards the resistor, all right? And then I'm going to run that to that output. And what do you think? Let's use maybe white, use a white wire. And you can see I tried to color code things a little bit so that as I'm wiring it up, and this is a good technique. So for example here, as I was making these different buses, I made this one green, this one blue, this one purple, and so on and so forth. So you can kind of see things, because otherwise you'll just get really, really confused. So let's go ahead and strip that wire a little bit. Okay, so right here, and it's going to go to 14. So 11, 12, 13, 14. Hope that's 14. 11, 12, 13, 14. Okay, that looks good. Okay, so there's our whole circuit now, and we've at least got overflow here. All right, so now let's play around here. So the first thing is we've got our 2 operands here. And then we've got these dip switches right here, which select what the numbers are. So for example, and I've kind of colored them in green and colored them in blue here. So I'll put this up. So there's 7, and because we've got a 1, 1, 1 right there. So this is in binary, so this is the low bit, next high, so the 1 bit to the 2 bit, the 4 bit, the 8 bit, the 1 bit, the 2 bit, the 4 bit, the 8 bit. All right, so let's put that back. Let's see, what did we have there? Yeah, 3 and 5, and then we had 3 up here, so I could put that bit, and that would be 7. And then if I go and put a 15 on that, remember these displays blank out on 15. So we could put an 8, and a 4 is too much. That's 12. That's too much. That's 10. There we go. So 8 and 1 makes 9, right? 8 and 1 makes 9. Okay, so we've got 2 things here. We've got 9 and we've got 5, and let's try and figure out which thing is which here. So we got 9 and we got 5, and we're not sure which one is A and which one is B. So the little blue dip switch here has got these yellow wires, and for example, I've got one of those bits going to pin 1. So let's see if that's operand A or B. So pin 1 is A. All right, so this is definitely A right here, and then this is B. All right, so this is A, and then this is B. So A is this one, and then this is B right here. All right, that's the way it is. That's where these buses are. So A is here and B is here. All right, so just kind of remember that. Not going to matter too much. All right, so what I'm going to do right now is I'm going to just kind of turn this, because it'll make it easier so we don't have to rotate our heads 90 degrees. Now the buttons here represent all the operations that are in the design there. So they go from left to right, and the operations, I'm going to put them up on the screen here for a second for me, but they're just like in the table in the Proteus CAD file here, which is Crash Course ALU 74LS382_02, which of course will be in the course materials. So it's B minus A, that's this button right here, there's B minus A. The next one is A minus B, the next one is A plus B, the next one is A XOR B, and so on, all right? So let's try and do one of these and see if this works. Okay, so this first one is B minus A. All right, so B minus A, so that should be, this should be B, and this should be A. So B minus A should be 4, all right? So when I press this button, instantaneously, let's stop the camera from shaking. Instantaneously, we should see a 4 here on this output, and this is the output of the ALU. Ready? All right, so we got a 3. So what's going on? All right, so what's happening is we're doing a subtraction, so we have to put the carry in. We have to insert a carry in. So I'm going to put a carry in. I'm pushing down carry in. Now we do it. 9 minus 5 is 4. That is correct. All right, now let's do the other way around. What's 5 minus 9? Well, it's a negative number, and that negative number is going to end up being larger than what we can display. Because that bit pattern is not going to be displayable, so we get one of these symbols right here because this is working in 2's complement. So that's working. That's what we expect. So that's good. This next one is A plus B. We don't need to carry in. 9 plus 5, 9 plus 5 is 14. All right, so 9 plus 5 is 14, and we're going to get a funky symbol on here that represents 14. So if you look up the 7447 for 14, that's what you would see. Let's do something that'll actually fit on the display. So let's get rid of the 8's place here on B here. Very careful, I don't want to pull anything out. There we go. And let's put 5 and 5, that won't fit. 5 and 7. And let's get rid of that. There we go. How about 4 plus 9? Excuse me. 4 plus 5 will equal 9. 4 plus 5. So here's the plus operator. And sure enough, 4 and 5 equals 9. All right. Now, interestingly enough, 4 and 5, we get a 9, and we get this carry out right here. All right. So we get 4 plus 5 is 9. We get this carry out, and we shouldn't get a carry out. It might be thinking in BCD, and that's why we get that carry out. But anyway, we are getting this carry out here. All right, what's the next operation? Let's pick another operation. So the next one is A XOR B. A XOR B. All right, so 4 XOR 5. So convert 4 to binary, convert 5 to binary, and XOR them. That will be the result. So that is the 1, 2, 3, the fourth button. 1, 2, 3, the fourth button. So A XOR B is a 1. All right. Now, what I've got here is one of my new calculators here. And I think I've told you my daughter, she's 2, she likes to hide them. All right, so we're going to take this calculator, we're going to put it in complex, we're going to put it in base n mode 4, all right? And then what we're going to do is we're going to put the first number in, we're going to say 4, all right? And then I want to XOR that. So in this particular calculator, we have to get the base n operations, which is here. We're going to select XOR, which is 3, if you can see that, XOR. All right, pretty cool. And we're going to XOR that with 5. And then when I press equals, you get the 1, and there it is. So that's correct. All right, so there's an XOR operation. We have anything else exciting? Let's see here. So A and B. So this operation right here, the one before the last, is A and B. All right, so 4 and 5. All right, so 4 and 5. So if you can do this in your head, 4 is just the 4-bit, 5 is the 4-bit and the 1-bit. Right? So 4 and 5 will just be a 4. That's where we've got a 1 and a 1 in both positions. So it should be a 4, right? So there it is, and we get a 4. All right, and that's exactly what we expect. So anyway, it's working. So we got an ALU operating and doing calculations, and it can do math, and it can do logic operations. We have the basis of a computer. So let's go back to the Blackboard here, the computer, and the PDF file, and I want to talk to you about kind of a little bit more about how you would, kind of make a computer, just some ideas about it that you could use this ALU with. So I'll meet you back at the computer. Okay, so we're back on the computer now, and we played with our little prototype, which took a lot of time hooking that thing up and getting it to work, kind of a pain. But as you can see, it mimicked this circuit, which we couldn't simulate because we do not have the 7.4 LS or F382. So anyway, you have the circuit. You can play with it and look at it. And the file is right up here, Crash Course EE ALU 74 LS 382_02. And that works here in Proteus. Now, what do I want to talk to you now? Okay, so we were talking about arithmetic logic units. We've gone through all this material. All right, and now what I'd like you to make sure you do is read this section in my book, 6353 on ALUs here. And what I'd like to talk to you about is, now this, hopefully, you know what, I think this is still, let me see here. Okay, let's see what happens if we click this. Yes, allow. Good. It opens up the browser. Okay, so this is kind of cool. So this is an example of like a homebrew CPU, and I believe this guy made this out of TTL chips. Yeah. A custom CPU made out of 74 series TTL chips, all right? So there are 200 chips in the Magic One. So this is a computer, made with the techniques that we're talking about, and all out of TTL chips. How cool is that? So this is very, very cool, and you could do worse things than read through all of this web page and stuff, all right? So I'd like you to do that just for fun. But anyway, what I'd like to bring your attention to for our coders out there is, and this is kind of C code, pseudocode. So if whatever language you program in, Python, C, C++, etc., you should be able to understand this. So what if we wanted to make a processor, right? And we're kind of thinking about doing something like that CPU I just showed you. All right, well, what we could do is we could think about if we just had some memory, like a RAM memory that we could access through, all right? And then let's say that we want to create an instruction set, and maybe each one of those instructions were like, one of these ALU operations and maybe a branch or a jump or something like that. And then to keep it real simple, maybe we say it's only 256 memory locations, so it's 8-bit. And then maybe to make it simpler, we have what's called a fixed instruction length, right? So the instruction is always the exact same size, so it's not 1 byte, 2 byte, 3 byte, 4 byte, whatever. It's always like 1 byte, 2 byte, 3 byte, 4 byte. So here's a little C code. So just kind of follow me here and see if you can kind of figure out what I'm doing. So let's assume that we create an unsigned array of bytes, so just bytes, and let's assume that we have we're going to put a program in here manually, and the program is going to consist of an opcode, 2 operands, operand 1, operand 2, and then a result. And you don't have to use either of the operands or the result, but they're there. So the memory locations are there if you like them. So an opcode could not operate on the operands and not create a result. It could be like a nope, a no operation. Doesn't do anything except take up time. So these would be wasted bytes, but that's okay. All right, so this is how we would lay out our memory. All right, and this is another thing. If you're into emulators or programming things like that, like one of the things that I did when I was really young was I created a 6502 emulator, Z80 emulator, probably, I think, did I do an 8080 emulator? Maybe, but I would write processor emulators, and it's really fun because you basically just model the processor, and then it's pretty easy because it's just like, what's the opcode, what's the operand, and then just do the code, do the instruction inside of a little bit of code, and then you basically have a giant case statement that just runs through what the instruction is. Anyway, similar kind of thing here. So we've got our program here. Here it is. We got 256 different instructions here, whatever they happen to be. All right, and then create a variable unsigned char IP for an instruction pointer, right? And that's the thing that kind of runs through the memory. All right, then we come to our main here. All right, we reset the system. We set the instruction pointer to 0, then run forever while 1, right? And then, this is just pseudocode. All right, and then we say switch program IP. So what's that going to do? So program is this. It's just an array, and it's going to say switch program sub IP. That's going to access wherever the instruction pointer is pointing, which right now is 0, so it's going to point to this first opcode, right? Whatever that is. Then we go through here, and then we basically say, is it an add opcode? And maybe add is a 12, and maybe sub is a 39, and maybe and is a 42, right? They're encoded. So if it's an add, then we say, okay, program IP plus 3, that's where the result is stored, right, equals program IP plus 1 plus program IP plus 2. Those are the 2 operands. So that operand and that operand, and this would be the result. So it adds these 2. So it basically adds the 2 operands and stores the result. All right. And then that's that. And then we would just implement all these instructions, then default break and switch, and then increment the instruction pointer. Because we're using fixed length instructions, it's always going to be IP plus equals 4, IP equals IP plus 4, just shorthand. All right. And then we just let it wrap around because it's an 8-bit value, so it's just going to wrap around. That's fine. Then we jump back up. That's it. So this basically is a really crude little instruction stream execution unit in C code that you could implement with this ALU, a counter, some memory, and a little bit more logic. We could actually implement that. and that code kind of in this hardware. And that's exactly what that CPU thing that I just showed you, this thing, this homebrew CPU, that's exactly what this kind of does on a more complex scale. And that's what a microprocessor or microcontroller does do. All right. So anyway, take a look at that, think about that, maybe write up a little bit of code in a JavaScript, Python, whatever your favorite code is, and try and implement that. And then of course just read through this right here and kind of, I summarize how you would do that. So that is the end of this. We are done with all this chapter. The next chapter is going to get fairly advanced. We're going to stop in the next chapter basically, but we're going to, I believe we've got counters in the next chapter, so we're going to take a look at that so we can have that counter coverage. But the next chapter would be kind of a whole nother course, right, in advanced digital electronics. So we know enough now to do some damage. All right, so we're going to do a little bit more in the next chapter. We're going to look over that, chapter 7. So if you want to read ahead, go ahead. And then after we talk about counters, then we're going to start building circuits with Circuit Maker, finally. So we're going to build a number of cool little circuits. I don't know, we'll just kind of do it as we go and just get the hang of doing Circuit Maker, make some basic circuits, make their Gerber files, and then figure out how would you send these out for manufacturing and all that. So we're to the last part of the course, and we finally are to the funnest part, because now we can actually build things, which is going to be really cool with all that we know. So now we are, basically, sort of electrical engineers, right? Embedded engineers, right? And we know enough to kind of do what we need to do. All right. So see you in the next lecture. Bye. All right, welcome to the next lecture, and we're actually on the next chapter. And in this chapter, we're going to be covering counters. We've already kind of covered flip-flops, so this chapter is a little bit of a review. However, this chapter has some advanced material in it that we're just going to kind of skim over at this point, because it's kind of a whole nother class talking about what this chapter gets into. But what we're interested here is just the counter material, but we're going to talk about everything else that the chapter talks about as well. And then we'll do some simulation, and then we'll go on the bench and build some of this stuff. So I'd like you to read chapter 7, 2 times, maybe 3 times if you have to kind of understand what's going on. And then from this point on in the book, chapters 8, 9, 10, 11, and so forth, you can read these on your own if you want. But basically, the coverage that we're doing for Crash Course Electronics is going to kind of stop here at chapter 7, and then we're going to get into building circuits and building PCBs as the next part of the course to things up. Okay, so anyways, let's just jump right into this. So chapter 7, changing your mind with flip-flops, flip-flop state machines, and sequential logic. All right, so we've already talked about what a flip-flop is. A flip-flop is basically a memory bit, all right? And there are a few different kinds of flip-flops. And one of the first kind of constructions you could think of as a flip-flop is something that has some kind of feedback so that it maintains state, all right? So in this case, we're showing a buffer, and the buffer's output is tied back to its input. So if the buffer was in a state of 1, then we would get a 1 on the output that would feed back to the input. It would stay in that state, right? So even a passive buffer IC would act like a memory. And if we had a 0 in it, the 0 would be on the left side, it would propagate to the right side, and it would feed back, and we would be stuck with a 0. All right. Same thing here. Say if we didn't have a buffer and we had 2 inverters, we could tie the inverters together, and whatever is on this input right here would come through this first inverter, be inverted, then be inverted again, so we would get the same signal back. However, there's some time delays that are occurring here, and so this T2 here, T1, T0, these would be the propagation delays as the signal is propagating through. So from, say, T0 to T1, that would take T1 minus T0 time and T2 minus T1 time to get to this point, and so on. So just showing you doing it with an inverter here. But the whole idea is feedback for these kinds of memory elements, all right? Now, so Oh, classic. There's a typo right there. I'll have to fix that. This should say classic set reset flip-flop. And so what this is just showing here is, and you can do this with many different kinds of gates, NOR gate, NAND gate, uh, but in a nutshell, you cross-connect two gates like this. So this is a NOR, a two-input NOR, another two-input NOR gate, and you cross-connect them like this, creating our feedback loop. So basically, here's this feedback loop here, and then here is this feedback loop here. So these are cross-connected and fed back. And then the 0, 1, 0, 1, these are just showing examples of kind of how you figure this thing out. So what you have to do is you have to assume it's in a state to begin with, and then you can change the state with these two inputs. And then we're naming these the R and the S, or the S and the R, reset and set. And then over here we have a truth table that we've kind of worked out. And the truth table says if you were to assert the set bit as 1 and the reset bit as 0, then the next state would have Q as 1 and Q naught as 0. So what you kind of do is you got to run through the flip-flops and kind of do these actions, perform these actions, and then see what happens. Then you can see there's this undefined state here. So for example, let's try this set state. All right, so let's assume right now that first, also we have to kind of remember what is a NOR gate, right? So let's just think about this in our heads real quick. Let's go to the, we'll go to the blackboard here. So a NOR gate, if we can remember, right? So we've got two inputs, X and Y, and we'll call this Z is the output, all right? And the inputs, we can have these different patterns here, right? The 4 different patterns. So a NOR gate is like the OR except inverted. So if it was an OR gate and we had these inputs, we would get, for the OR gate, we would get 0, 1, 1, 1. We would get 0, 1, 1, 1. All right, because either one of these inputs are on or both are on. So 0, 1, 1, 1. So that means for the NOR version of this gate, we would get 1, 0, 0, 0. So in other words, the only time that you get a 1 is when both inputs are 0. So the only time you get a 1 is when both inputs are 0. So in fact, we could do this. We could say that this is NOR, all right, and then we could say, call this Z primed here, and we could say that this is OR, all right, and then if this was OR, we would get 0, 1, 1, 1, right? Okay, so with a NOR, the only time we get a 1 is when both inputs are 0, all right? So let's kind of just remember that so we can kind of keep this straight. All right, with a NOR, we only get a 1 when both inputs are 0. All right, so let's go back to the PDF here. All right, so let's assume, for example, let's assume that the current state of this flip-flop is, let's say that we have a 0 on Q, all right, and let's assume that we have a 1 on Q naught. Let's assume that they're opposite and which they're supposed to be. So that's all we're assuming right now. Now, let's go in on S and R, and let's go put a 1 and a 0 here. So we're going to put a 1 and a 0 here. All right, so here we go. So just try and, this is how you do this. You may not be able to follow right here. You'll have to do it yourself. But all right, so we know that, what did we say here? We said that we're assuming that we've got a 0. So we're doing, these values are actually correct here. So we're assuming that right now we've got a 0 on Q and we've got a 1 on Q naught, all right? So that's what these outputs are if we were to measure them. All right, then we're assuming that we're now at this point in time, we're going to put a 1 here on set and a 0 on reset. All right, so here's a 0. So we got a 0 coming through here. So we got a 0 and we got a 1. We got a 0 and we got a 1. So if we got a 0 and we got a 1, right, let's go back here. All right, we got a 0 and we got a 1. With the NOR, we're going to get a 0 out. We're going to get a 0 out. So that's going to put a 0 out here. So we're going to get a 0 out there. So now that here comes that 0 back here. All right, and on reset here, we're saying we're putting a 0. We're doing this first possibility here. So we've got a 0 here, and we just got a 0 here. A new 0 just came out here as it fed back. All right, so we got a 0 and a 0. That's the only case where we get a 1 out of this thing. 0, 0, we get a 1 out of it, right? So now we got a 1 out on Q. So let's see if it's stable. Is it going to oscillate? All right, so we got a 1 out on Q right now. All right, so that's so far so good, but what we want is also a 0 on Q naught. So here we go. So this is a 1 now, so ignore this 0. So it's a 1. So here comes the 1. There's the 1. We still have a 1 here, so we got a 1 and a 1. And the question is, we better get a 0 here. 1 and 1, we get a 0. So let's see. 1 and 1 on a NOR, we do get a 0. Okay, so that's good. So we got the 1 and 1, we got a 0. And now that 0 feeds back here. All right, and now we got a 0 and a 0 again, and we still have our 1 would output here. So that's correct. So the set state works. So basically what's happened is by putting the inputs S and R to those two values, the flip-flop would flip if it already wasn't in the state of Q1 and Q naught 0, it would flip to that state. And then you can do all these other examples. So this is, it's recursive kind of. Well, it is recursive, right? It's a feedback network, right? And just like in software, recursion is a little bit hard to get your head around because you got to kind of take the output and kind of feed it back to the input. The functions call themselves. So it's the same kind of idea here. So just do it a few times. Just do it on a piece of paper and track what's going on. And one of two things will happen. It'll stabilize or it'll oscillate. And if it oscillates, then that is kind of an undefined or a metastable kind of state, and we don't want that. All right, so give that a try. All right, so that's the basis of a flip-flop, and we've talked about this. All right, and then this right here is a transition table. This is showing you kind of the S and the R and all the different things that can happen. Basically, just copies down what I have here in this truth table. All right, and then here's another example where we have two SR flip-flops, and then you put them in a master-slave kind of configuration. All right, you take one SR and you tie it to another SR, and then we can do a kind of a clock here and then invert the clock. So they get clocked on different edges, that kind of thing. So you'll see this kind of concept of master-slave flip-flop. All right, and now we're going to talk about real-world flip-flops. All right, so we've already talked about the D-type flip-flop. All right, and we've also talked about the JK flip-flop. And the D flip-flop was a basic, like a memory bit. So it just has a D input and a Q output, and it may also have a Q naught output. And the whole idea is you assert a 1 to D, and on Q, you'll get a 1 out after you clock it. If you assert a 0 on D, you'll get a 0 on Q. And so it's a one-bit flip-flop. Very simple and very useful. However, there's another flip-flop, the JK flip-flop, which has another input, the K input. And if you look at this truth table and kind of work through this, you could see what's going on. So basically here we've got a clock signal. And then on the D flip-flop, it's pretty straightforward. Whenever it's clocked, Q will follow D. All right, that's pretty simple. But on the JK flip-flop, depending on what J and K are they 1, 0, 0, 1, 1, 1, or 0, 0, you'll get different things happening. So what the JK flip-flop, the one thing that it does that all the other flip-flops don't, is it can hold state and it can flip the state or toggle the state, all right? And the toggle is the thing that we're really interested in, so it can toggle. So you can set it to 1, you can set it to 0, and then it has a toggle function which it toggles whatever state it currently is in. And that's really the one that adds a lot of value to the JK and makes it useful to do things like counters, all right? So here's what you, and we call these things, they're truth tables, but they're called characteristic tables also is the terminology, characteristic table for the D-type flip-flop. It's very, very simple. If D is 0 and you clock it, the next state will be 0. If you put a 1 into D, the next state will be a 1. It doesn't get any simpler than that. Just a memory bit. It's a clocked memory. Now, the characteristic table for the JK flip-flop is if you put J and K to 0, the next state will be what the previous state was. So QT plus 1, time plus 1, will equal Q of what the current time is, or the current step in time. So whatever it is now, in the future, it'll be the same thing. So there's no change. That's just a long-winded way of saying no change. If you put 1, 0, it'll set to 1 no matter what. If you put 0, 1, it'll reset no matter what. Now here's the one that we like. The 1, 1, right, the next state, so the next state will be what the current state is inverted. So it toggles it. So this is what this means. Invert what the current state is. So it'll toggle it. So if it was 1, it'll be 0. If it's 0, it will be 1. That's very, very useful, this one little function. All right. And then, of course, these two set and reset are a nice way to be able to set and reset the flip-flop. Okay, and then you can take a JK flip-flop, and if you take a JK flip-flop and you tie the J and the K together, then you can either get 0, 0, or 1, 1. You can either get no change or invert, and that's called a toggle flip-flop, and that's what's reflected here. So 0 gives you a 0 out, no change, and then 1 toggles you. So actually this is this right here so this is another typo. So that's good that we're seeing this. This should be Q sub t, and then this should be not Q sub t. All right, so I'm going to go back. I'll go back and fix that. So these things should have been copied right here into each one of these. This happens when books are edited and editors go through them and they copy things down. Sometimes the author, me, runs through it to rush through to see what they have as questions, but what happens is they've edited things and they change things and make them incorrect. So one of us made a mistake here and copied and pasted this wrong. But anyway, the toggle should be, if you put a 0 in there, it should be Q sub t, and then if you put a 1 in there, that would be the same as this JK1, which would be not Q sub t. Okay? All right, and then the SR, we've already went over that characteristic table, which is the same thing that was up top. All right, so anyway, the bottom line is D flip-flop if you need a memory flip-flop. You're never going to use a T flip-flop. You'll just use D and JK, and no one uses SR. They're more just educational models. So the JK flip-flop is very useful, and the D-type flip-flop. You're going to see D-type flip-flops for latching operations where you just need memory bits, or shifting operations where you want parallel in, serial out, or serial in, parallel out, that kind of thing. You'll see D because you just want memory. When you want kind of operations on things and you want to count and perform operations like that, you'll see the JK flip-flop. All right, so let's take a look here. So and there are hundreds of flip-flop and counter ICs. So as usual, I'm just going to give you some kind of old go-to parts. So the 7.4 LS7.4, and of course there's many variants of different families here, but this is a dual D-type flip-flop, so pretty straightforward, and it's a dual positive edge triggered. All right, and that's important. That means that on the clock, things happen on the positive edge. They could happen on the falling edge. They could even happen on the level, right, when it's high. But we like things that are on the rising edge or the falling edge. So, and it may depend. So, for example, you may have some logic where you want some part of your logic to be activated on the rising edge and another part of the logic to be activated on the falling edge. So you need to make sure that your chips, your ICs, are either rising edge or falling edge asserted or clocked. So you got to be careful of that. You can't just do it blindly. All right, so the 7474, and it's fairly simple. You can see it's got 2 units inside of it. What's cool about it is it has a preset in a clear, and it also has complementary outputs. In other words, it just means it has a Q and a Q bar. So it's got the inverted. So these are, they've got everything. So these are like the Cadillac of flip-flops. If you don't need all this, you might be better off getting a 4 in a package flip-flop if you don't need all these other features here, right? So if you don't need the set and the preset and all that, and you don't need the inverted output, you could probably use a different chip, which I'll show you in a second, where you might want 4 of these things because you don't need all these other features. All right, but anyway, if you need a flip-flop, 7474 gets it done. All right, now, these are a couple of my favorite flip-flop packages. Real simple. The 74, 175, 174, and 175. All right. So now there's 2 different versions of these things, and again, there's many versions of different logic families. You can find these in things other than LS, of course. But what I like about it is there's kind of 2 versions. There's the hex package, so you got 6 here, right? And then the quad package. So the hex package has less bells and whistles. So it's basically D and Q, D and Q, D and Q, D and Q, and that's it. That's all you got. All right, and then you've got to clear. So you can clear the whole thing out, and then you've got a clock, and you got D and Q, D and Q, D, Q. That's it. Very, very straightforward. So this is great if you need a memory, right? You want to latch something, do some kind of memory operation, shifting operation, whatever. That's what you want right there. Now, if you want a little bit more control, then you can go to this quad package. This is the 175. This is the 174. You go to this quad package, and now look what we have. We've got 4 flip-flops, but now each one has the inverted or complementary output Q bar, right? So we've got that added feature. With each one of these. So for example, let's say that we only needed 4 flip-flops, right? And so you could use this package right here, but what if you needed the inverted versions of some of those outputs? You'd have to add another inverter IC. So instead, you could just use this one IC, and now you don't need two ICs to do the flip-flops and the inversion, because these have the inverted outputs along with them. And that's part of optimization. So here, a little tip. When you're designing digital electronics, just like when you're coding, right? First, you want to write clean, understandable code that doesn't have a lot of clever optimizations and tricks and stuff, right? Once you have the code working, then go ahead and optimize it and speed it up and do all that. Electronics is kind of the same way. When you're designing electronics, first design the design, get it working, make it robust. Then you can start saying, hey, I could turn these 2 chips into 1 chip, and I could turn those 3 chips into 1 chip and do this and do this, and you start doing all that. By the time you're done optimizing code and optimizing electronics, it's hardly understandable. It's so clever, it's so tricky, you don't even know how it works anymore. And if you tried starting off like that, you would never be able to design it. Like the Apple computer, the Apple II computer is a really good example where Steve Wozniak started off with however many ICs, and then he just kept optimizing and reducing and doing this to get down to however many ICs the final motherboard has, which I used to know. You can Google it and look it up how many ICs, but I've heard Steve Wozniak talk about that whole process many times and how he started with so many, and then every day he'd like, I could turn this into this, and it's the same thing with electronics. But start off simple, just make it work and make it clear and understandable so that you know what's going on. All right, but this is some of those different ICs that you can use as part of that optimization process. All right, and like I said, these ICs come in all different flavors: LS, HC, AS, HC, LV, LVC, and so on. All right, so you can find them. Now, the next thing we're going to take a look at is a JK type flip-flop. All right, and one of those standard ICs is the 74LS76, and this is a dual JK flip-flop with set and clear. All right, and let's see. This one I don't have. Let's actually go 7476. Let's go to DigiKey and let's take a look. 74, and we'll just type in LS. They're all going to have the same. And you can see this says obsolete right here, obsolete, right? But if we go 74, let's say HC76, all right, and this one also obsolete, and let's see, 74 LV76. Let's see if an LV is even there. 74 LVC76. Okay, and so now, so what we might want, say, so those are kind of obsolete. You can still buy them, right? 74 LS76. Let's go back to that one. You can still buy the thing, and depending where you go, they have none here at DigiKey. But so, okay, you want a simple dual JK flip-flop. Now there's a new version derived from this, which I don't know off the top of my head, but if we type in JK flip-flop, there we go, JK flip-flop. We want JK type. All right, I want it active. I want it in stock. All right, I want it lead-free, RoHS. I want it, new, still 146. And now here's all these different types here. So let's see, we want it in LVC, or maybe we want it in HCT. So apply filters there. Okay, and then we scroll through here, and then we can see LVC 112, for example, is kind of exactly what we're looking at, just a very fast new version of that 7476. So 74 LVC 112A, a little bit more modern here, 2014, right? You can see there, 2014, and showing kind of what internally this thing looks like, simplified schematic, and down here is then the pinout for the IC, all right? So you can see we've got clock, we've got 1K, 1J, we've got one preset, all right, and then we've got 1Q, 1Q not, and then we've got 2Q not, and so on and so forth here. So again, the ICs in here, you can definitely find them, but there's always something newer and better, or bigger or faster if you need it. But the point is, these are really basic ICs that kind of are the hello worlds of each of these categories. All right. So anyway, so that's the JK flip-flop. All right. Now, So now let's move on to counters, and this is really, so the flip-flop stuff was just should be review. Now let's move on to counters here, and this is really what I wanted to talk about, are counters, because this is important. Okay, so counters are usually constructed based on flip-flops, and now we know that we have these flip-flops that can remember a bit, and then we have this JK flip-flop that can toggle. That toggling and that memory aspect, those two things are very important, and they're going to allow us to count. Now, I want you to look at this binary sequence here, right? So these are binary numbers, 0 through 15, all right? And if you can't count in binary in your head yet, just kind of follow with me here. So this would obviously be 0, 1, 2, 3, 4, and so on. So 0, 1, 2, 3, 4, and it goes down. Now, what I want you to look at, and as a matter of fact, I'm going to zoom in a little bit here for you. Make this real big, all right? Make this real big, and there we go. Okay, what I want you to look at here is this. So 0, 1, 2, 3, 4, and so on. So that's 0, that's 1, that makes sense. Then what happens is this bit goes back down to 0, the next bit turns high, all right? Then the 1 bit turns high again. Then both of those go back to 0, then this bit turns high, then the 1 bit turns high, then the 1 bit turns low, then this bit turns on. You can see this pattern. So now what I want you to do is just like put a piece of paper or in your mind, cover up these 3 digits to the left and just look at the digit to the right. Notice it's always toggling. Every clock, right, it toggles. So it's 0, 1, 0, 1. It toggles, right? Isn't that interesting? So it basically, whatever the clock rate is, say the clock rate is F, it's toggling at F over 2. It just toggles every time. Now look at the next bit. It's 0, 0, then 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Interesting. Now look at the third bit. What do you think it's going to do? 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1. All right, and then look at the high bit, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, and so forth. So each one toggles at half the rate of the previous. So it's kind of interesting, even though this complicated counting is going on, it's following this kind of pattern where this is basically the frequency divided by 2, divided by 4, divided by 8, divided by 16. So it's basically dividing by 2 and toggling. So it's toggling every time. So it's toggling. So that's very, very interesting, right? And binary numbers, when you count, have that property. Okay, so let me zoom in just a little bit more, maybe 200. Yeah. Okay, so now what I want you to also look at is there's a term called Hamming distance. You may not have ever heard this, but Hamming distance has to do with when you're talking about binary numbers. So it's a kind of distance, right? It's a kind of measurement of distance. But it has to do with binary numbers, and it means how many bits change from one code word to the next. So how many bits change from one code word to the next? All right, let's take a look. So starting off from 0 here, right? If we were to go to 1, only 1 bit changed, all right? Now, if we were to count to 2 next, if we were to go to 2 next, look from 1 to 2, 1 to 2, 2 bits change. This bit here changes, and this bit changes. So the Hamming distance is 2, all right? But if we go from 1 and skip 2 and go to 3, so we go 1 to 3, so we go 1 to 3 is the next code word. Look at this. So the 1 stays there and we only change 1 bit. So basically you're only changing 1 bit at a time, very carefully, all right? And so this is a different kind of counting where the Hamming distance is 1. So the Hamming distance, so the number of bits that change per code word to the next is only 1 bit. So it's not going to count sequentially, it's going to count in some funky way. This is the funky way. 0, 1, 3, 2, 6, 7, 15, 14. Okay, so that's Hamming distance account where the Hamming distance is 1, maintained at 1. All right, so that's got a special property. All right, okay, all right, so that's and then here's the rest of the sequence here. So it goes up and it goes down like that. All right, now so anyway, this counting sequence here might be very important to do something so that only one thing changes. So for example, let me show you something. For example, take a look here. Where's a really worst case? This one. So say say from 7, here's code 7, and it's got 0, 1, 1, 1, and then code 8 is just 1, 0, 0, 0. So in this case, what's the Hamming distance? Well, the Hamming distance is 4, right? So you've had maximal change here. So every single bit is changed. So if these were controlling things or something like that, and that's what I'm talking about down there, if these were controlling things, all these were on, then all of a sudden they're all off and this one's on. So it's like there's a lot of changes going on. So, but if the Hamming distance maintained at 1, only one thing changes. And this has some very important use and properties when you're doing things in binary. All right, now, discrete implementation of 2-bit binary up counter. All right, so again, you know, this stuff is important, but I want you to read this again because you know you're going to have to read it a couple of times to make sure you get it. But it is important, and even though we're going to use chips to do this or microcontrollers to do this, I want you to see this because this little trick here, not even trick, this little construct is like the basis of everything that counts in computers. So let's really pay attention here. So if we wanted to make a 2-bit counter, just a 2-bit counter, so the count would be 0, 1, 2, 3 in binary. And we want to go through the states B1, B0, 0, 0, 0, 1, 1, 0, 1, 1. Notice in this case the Hamming distance is not maintained at 1. We're counting sequentially, right? So the Hamming distance from code 0 to 1 is 1. Then from code 1 to 2, the Hamming distance is 2. Then from 2 to 3, the Hamming distance is 1 because only 1 bit is changing, but 2 bits change in this transition, all right? If we want to talk about Hamming distance, but we're just talking about a straight binary sequence now. So that's what we want to achieve, all right? So when we're in state 0 here, or 0, 0 binary, we want to hit the clock, and the next state we want to be this. When we're in this state, that's the present state, and we hit the clock, we want to be in this, and when we're in this and we hit the clock, we want to be in this. So in code, this would be very simple. We would say something like if the current state, we could create a variable if current state. If current state is 0, right, then next state would be 1. If current state is 1, next state would be 2. If current state is 2, excuse me, next state would be 3, and that would be it, right? Or we could just use the computer to add, but let's assume the computer didn't know how to add because we're building the computer. All right, so here's the 2-bit counter. And what is going on here? So we've got these JK flip-flops that we talked about, right? And their property, that toggle property, remember that toggle property? So let's take another look here. Remember, we looked here, just look at the first 2 bits here as we're counting. So 0, 1, 0, 1, 0, 1, 0, 1, and then 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So if we could just get these bits to toggle, right, at half speed each, we'd be counting, right? And can we get them to toggle? Sure. And we can get them to toggle, and we'll just look here, and let me just press a button here so I don't have to scroll forever, for eternity. Yeah, so JK, remember, if we put a 1 and a 1 in the input, we'll toggle whatever the current state is, right? This will invert it. This will invert the current state. Okay, so let's go back there. So we know we need to use a JK flip-flop. All right. Okay, so we'll use a JK flip-flop, and then here's the trick. What we're going to do is, the very first flip-flop here, we're going to inject a 1 into it. So we're going to tie J and K together. We're going to inject a 1. So let's assume that both of these flip-flops are 0 to begin with. So when we power this thing up, maybe it's not shown, but there's a reset pin, and we can make sure that both of these are 0. So Q and Q of both of these are 0. All right, now we've got a 1 and a 1 here. Now look here, we take the output of the first bit here and we input it into J and K of the second flip-flop, and notice it's tied together. So if it's a 1, we're going to get a 1, 1. If it's a 0, we're going to get a 0, 0, right? So if it's 0, 0, it's going to maintain state. If it's 1, 1, it's going to invert or toggle, all right? So that's the trick. Okay, so now, and then what's the other interesting thing? We tie the clocks together. So whatever happens can happen simultaneously. And again, doing analyzing clocked logic takes a little bit of experience. You got to take your time or you'll confuse yourself. And again, it's a little bit recursive here and there, especially if there's actual feedback loops. In this case, there is no feedback loop, which is good, but there's feed forwards, and they're all clocked simultaneously. All right, so let's try and do this. Okay, so here we go. So we've got a 1 here on JK always. So first, let's just forget this even exists. Just forget this other flip-flop. Throw it away. Now, if we've got a 1, 1 here and we've got a 0 on this Q, right? So right now we got 0. If we hit the clock, what's going to happen? It's going to invert that. So we started off, so here's B0. So we start off at 0, we hit the clock, we're going to get a 1. So now we've got a 1 here. So then we hit the clock again, we're going to get a 0. Hit the clock again, 1, 0. So we're toggling, right? It's doing exactly what it should do. So B0 is toggling every clock, right? So every clock it toggles. Click, 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 back and forth. Great. Okay, now let's go back to reset to this first state here. So we've got a 1 here. We've got a 0 here when the thing starts off. So we reset the whole thing back to time equals 0 here, okay? So we've got the 1 here, and we've got the 0 here. So there's a 0 here. So what does that mean? That means maintain state. So now we do the clock, and both of them get clocked at the same time. This one changes to 1, right? So we had a 1 here, which means toggle. It was in the current state of 0. So when we clock it, it changes to 1. However, that 1 is too late. There was already a 0 sitting here when the clock came, so that 0 just meant maintain state. So then we got a 0 out here. So what happened? We got a 1 here, and we got a 0 here. We got a 1 here and a 0 here. That's this one. All right, so we got a 1 here, 1 and a 0. So we got a 1 and a 0. So now we got a 1 sitting here. All right, we got a 1 sitting here. This flip-flop is 1. This flip-flop is 0. All right, so now we're going to hit the clock again. We hit the clock. This one toggles. So it was 1, so it's 0. It's always toggling. But when we hit the clock, remember, it doesn't wait for this one to change. It's already seeing whatever value is here, which was a 1, which means toggle. So now this one toggles. So now finally this one toggles right here. And now we got this 1 here. All right? Okay, so now this flip-flop is a 1. All right, this flip-flop is a 1. This flip-flop is a 0, right? Okay, and now, so we're in this state right here. Now we hit the clock again. So this flip-flop right here is a 0, all right? And we've still got a 1 up here, which means toggle. So now we hit the clock again. This one's going to toggle, but it's too late. It already had that 0 here, which means don't toggle, just stay what you're doing, so stay at your current state, and it does. And we get this state right here, except this bit toggles now, and so we're here with the low bit. So I know it's a little bit confusing, and you gotta kind of run through this, but the thing to remember is this: when this clock hits, whatever the current output of Q is here, and whatever this current output here, that's what we're looking at. We're not waiting for it. When the clock hits, we don't say, well, it toggles and then it changes and then this thing reads it. So at the very rising edge, and that's why the rising edge is important, at that minuscule little 2 nanosecond, 5 nanosecond, that rising edge is when all of this happens. All right. Then the information propagates, the flip-flop changes state, and then that propagates to Q, and then here, whatever happens here propagates and over to the output. But that propagation takes time, and it's already too late. The flip-flop already did whatever it was going to do with whatever input was on there at the moment that the clock rising edge hit, if that makes sense. So this is a counter, and here you go, 0, 1, 0, 1, 0, 1, and then 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and then the next one would be 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, and if you just want another bit, you just put another flip-flop. So that's what these counters look like inside. All right, along with maybe presets and sets and that kind of thing, and then we're not showing the Q output connected here. Okay, all right. Okay, and then this just tries to go through what we just did verbally, which is not easy. And then here is a Proteus simulation, so we could take this, well, this isn't an actual simulation, this is just a circuit. And this circuit right here, using a real 7.4 HC76 with reset and all that, this would make a little counter. So we're gonna actually build this 2-bit counter. We'll probably do a 4-bit counter. We'll build a 4-bit counter, and then we'll also build it on the bench when we get to that. But we're gonna keep talking here and keep doing the lecture. Okay. All right. So that was the 2-bit counter. Now, as far as counter packages, there are hundreds of counters. And in here I said there's dozens, if not hundreds, but there's hundreds, if not thousands by now. And so you can find anything that you want. All you have to do is go to DigiKey or Mouser or Octopart and search for counters, and you can find whatever permutation of features that you want. But again, some basic ones that are like the hello worlds of counters are the 74 LS90 or HC90 or whatever technology you want to use, 90, 92, 93. So this is one category of them, the 90 class, and these are 4-bit counters, and this one's a decade counter, so it counts from 0 to 9, and then it resets. 0 to 9, and it resets. So the 7490, say you want to make a clock, a digital clock, that's what you want to use. It's got internal logic in it, so it'll reset automatically when it hits 9 and then counts back over to 0, right? And that's what you want. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You don't want to count all the way up to 15. Now, the 74 LS92, this counts up to 12. All right, this counts up to 12, so it goes 0 to 11 and then resets. All right, and that has some uses. The number 12 is 3 times 4, and that has some uses actually in binary counting. And then the 7493, this is a full 4-bit binary counter, so it goes from 0 all the way to 15, and then it resets 0, 1, 2. So it just counts around, right? And that's what it does. So if we were to look at 74 LS93, if we were to go over here and type in 74LS93, and looks like these are not obsoleted, at least on DigiKey from whatever their vendors are, and we'll just pick a DIP package here. And another thing, you'll find counters are not cheap sometimes. They're not cheap. All right, so at 1,000 it's $1. This is this part is older, of course, so it's harder to find and it's a little bit more expensive. But counters are not cheap, just to let you know. All right, so let's zoom in here. So we've got, so this one data sheet kind of covers all these 90 series, right? And so we were talking about like the 93 series. All right, so they've got all these different variations and whatnot. And there's their little logic diagrams. And then here's kind of what we're interested in. Here's the 90 sequence and 92 sequence, and here's the 93. So there's the 93, and so you can see the count sequence is 0 to 15, right? And then it just comes right back, just swings back right back. So you can kind of, and the reason why they have these different counters with different terminal counts and then that reset, say you want to count something that maybe there's only 7 of, 1, 2, 3, 4, 5, 6, 7, then I want it to reset. You could do that with a normal 4-bit binary counter like the 7493, right? But what would you have to do? So I think I've got a picture of it here, and just more data sheets. And let's see here. Forget about that. Yeah. So so for example, say you wanted to control when the counter might reset itself, right? Not at its normal terminal count, right? So what you would have to do is you would have to put a gate on the outputs, and you would have to say when the output is some specific value and put an AND gate there, right? So in this case, we're looking for 1011, so we're looking for 1011. So when we get 1011, this is going to turn high, and if there's a reset that's active high, we could plug that back into the counter and it would reset. So 1011, this counter would reset. So 1011, what is that? That is 8, that's 11. Right? So 4-bit counter to count to 11 design. All right, so this one would count to 11. Now, the 7490, let's make sure the 7490 counts to, let's see, the 7490, let's go back to this data sheet, 7490, and yeah, so the 7490, because it's a BCD counter, doesn't even count that high. So we need to, this should be, and the this should be the 74 LS93. We would use the 93 here because we want that full 4-bit counter. And this is this version of the book. This is kind of my editorial version. That's why it's got a few more typos than I'd prefer. But I'll fix that before you guys have got it and all that. So don't worry about that. But this is 74 LS93 because we need it to go past 11 normally, because normally it would reset. If it was a 7490, it would reset. But it's a 74.9x class counter is the point here. But here we're putting some logic here to reset the thing when we want it to reset. Okay. All right. Let's see. All right. Now this next section. So what we're going to do is we're going to stop here. And we are going to start this next. Now, so this next section is kind of like a bonus section, sequential logic and state machine block diagram here. And what we're going to be talking about is kind of how you make state machines with electronics. So what we have is we've got some flip-flops. The flip-flops maintain the state, and that's the memory. And then we have combinatorial logic, and the combinatorial logic works on that state to figure out with the present state and with inputs, variable inputs here, I want to give some kind of outputs, and I want to transition to another state. So this is kind of this block diagram of what a state machine is when you implement it with electronics. So this section here, 7.3 sequential logic design concepts, what I'd like you to do is read this now. So we're going to stop this lecture right here, and then I want you to read this, and there's only a few pages left. 1, 2, 3, 4, 5, 6, 7, 8 pages. I'd like you to read this yourself because this is fairly complicated material. So this is pretty advanced material, and like I said, this would be for another class where we're talking about advanced digital electronics. But I want you to read this, and then if you read it, then when I come and lecture on it on the next lecture, I think that you'll understand it a little bit better, and you won't be hit with so many new terms. All right. So let's stop the lecture here. I'd like you to read 7.3 before you take a look at the next lecture. Then watch the next lecture. We're going to talk about this. Then we're going to go to the simulator and then do some simulations. And then we're going to go to the bench. All right. So anyway, so that's it. And I will see you in the next lecture. Bye. So that's a counter. And that's it. So that's pretty easy. So let's see here. If we look at this state table, and then the state table has the present state, the input, and the next state. Okay, that's how they're written. And just so it's a tabular form, so you can kind of keep things straight. All right. So now look, if we're in state 0, 0 and C is 1, then the next state we transition to 0, 1. If we're in 0, 1 and the current state, the input C is 1, then we transition to the state 2, and so on and so forth. Now here's the interesting thing. Say we're in this state right here, that would be a 2. This is the 0, 1, 2, 3, right? If we're in this state right here and we have a 0 on the input C, we stay in the same state. Okay, so basically this edge right here is not drawn in these others, but when C equals 0, we just stay in the current state. We stay in the present state. All right, so this is showing it here, and we could draw them all here. It's just a little bit redundant, but we could draw those edges right there. When C equals 0, it just stays inside of the present state. So that's a counter, okay? And we would implement that with some flip-flops and some combinatorial logic. Okay, now let's take a look at this other state machine here. So in this case, this state machine, there should be some text here. So this figure, it hunts for the pattern of 1, 0, 1 in binary, 1, 0, 1 in binary. So if we take a look here, so here's the state machine. And another thing, obviously you can draw these circles wherever you want. So sometimes you can make these so they look artistic and whatnot. But anyway, so let's take a look here. So we start off in state 0. So here is state 0, and we output a 0. So here's the present state, and under the bar is the output. All right, and then the input is shown by these variables on these transition arcs. All right, so we're looking for a stream of bits here, and these bits could be coming from anywhere, right? From a serial line, from something else, an Arduino, Raspberry Pi, whatever. And what we're looking for is 1, 0, 1. 1, 0, 1. All right, so here we go. So we start off in this state. If we get a 0, then we just come back to the state. All right, so we just go right back to the state. So we maintain state if the input is 0. That's what this B equals 0 shows. Now, if we get a 1, that means we found the first bit in our stream we're looking for. So if we get a 1, we go to state 1. All right, now we're in state 1. If we get another 1, then we just go right back to this initial state, state 0. We've lost our pattern. But if we get a 0, then we transition to state 2. Now we've got 2/3 of the pattern. We've got 1 and we've got 0. If we get another 0, we go all the way back to the initial state. But if we get another 1, that means we got 1, 0, 1. Then we found the pattern. We go to the final state, or found. We output a 1, And then no matter what we get, 0 or 1, we stay in the state. And this is the way that we want to design this. So when we find the pattern, we stay in this state. No matter what, we're in the found state, and then we could do something else. The logic could do something, transition to another state, do something, and then come back to the start state again. All right, so that is another state machine. So you can see how you can design these. So they're pretty fun. So you've got the present state, you've got the outputs, you've got whatever it's going to transition on, whatever the inputs are. These are the inputs here, okay? And in this case right here, we've only got 1, 2, 3, 4 states, so we could encode that with 2 bits, right? So we would need a 2-bit flip-flop, right? 2 flip-flops, or a counter that we could use to count like this, but typically you will use flip-flops, all right? And this little note right here, there's what's called Moore machines and Mealy machines. Typically you'll want to use Moore machines, and it's these two words have to do with the architecture of the state machines. Mealy machines can be a little bit more efficient, but they can glitch during transitions. Anyway, you can read about them in Wikipedia, something like that, and a long drawn-out analysis of it, but we like Moore machines. The outputs are only based on the present state, all right? Okay. Let's see here. So this is just for that same figure, the state table for the counter, right, which we already talked about verbally. And then now, here's where things get complicated. So I'm just going to go through this. Like I said, this is a bonus section, and hopefully you've already read it. But if not, this will be the first time you're seeing this. So this is like some wow stuff now. So deriving the combinatorial logic for the outputs in the next state. What is this all about? All right. So now, if we look at these state diagrams here, right? We see things like, well, we've got the present state as S0 or S1 or S2 or S3, and we're getting an input variable of B, and B is doing this, and we want the output to do something. Here's the outputs, and we want to transition to another state. So basically, all this is code. You could think of this as code. It's like if one variable is this, and if this, then this. It's all this if and then stuff, which we could just implement with AND gates and OR gates, all right? That's basically what this is doing. However, when we're designing electronics, we do this a little bit more with a process and a procedure, with an algorithm, and that's what these things are. Okay, so K-maps are Carnot maps, and what these are all about is this. When you have a function, a Boolean function, or any logic function for that matter, you can optimize the logic function by using various algorithms, all right? And these algorithms can be done by a computer, obviously, or they can be done visually, or they can be done with intuition and common sense. But one way or another, there are ways and methodologies where you can run through an algorithm and optimize a Boolean function or any logic function. All right, and that's what these things are about. So Carnot maps are one way of doing it, or what we call K-maps. And what the K-maps do is they allow you to visualize redundant logic. All right, so like when you design a circuit, many times if you just kind of sit through and say, if this, if that, or this, or that, and this, or that, much of it is redundant and can be reduced and optimized. Let me show you an example. And this is why when you're coding, if you don't know anything about optimization theory, you'll actually write code that's about 50% or 100% inefficient in many, many cases. All right, so let's go here to our drawing program, and let's see here. And let me show you an example of something. All right. So let's say, for example, that we had a variable x and we had a variable y. All right, I'm just going to kind of make this up right now. All right, we had a variable x and we had a variable y. Okay, and let's say that we wanted to ask, we went through some logic and we decided that we want to know when x and y. So we put an AND gate there. All right, reasonable enough, x and y. All right, and so this is and so this is xy is the output here, okay? But now let's say that we always know that when we go through this and actually run it, x happens to always be 1. X is always 1, right? X is always 1. So if X is always 1, then that means that this input right here is always 1. So it's pointless having X as an input. We don't even need it, right? We can just get rid of X, all right? And we could just tie this. We could just tie this to a 1 if we wanted to, right? We could tie this up here to plus 5 volts to a 1. And then when y is 1 or 0, we're going to get this function because this x right here is always 1. So basically, what's 1 and y? Well, that just equals y. So we don't need this gate, do we? So because of details of what's going on with the logic, we can reduce this entire AND gate. So logically, we want xy. But practically, this just is y. Y, and why is that? Because x is always 1. Because it's always 1, 1 and y is always y. Guess what we just did? We just got rid of that 74 LS 08, 1/4 of that, or whatever gate we used. We just saved money. Now imagine doing that tens or hundreds or thousands of times. So that's what logic optimization is all about. And you can do the same thing when you're coding, right? When you're coding something, if you're doing a bunch of ands and ors and this and that, you realize I don't need to do this because no matter what, this is always true, right? So for example, let's do another one. Let's say that we have a variable a, all right? And we want to know, we'll say something like a or not a, all right, equals z. So a or not a equals z. Okay, fine. So what do we got there? Let's put a OR gate. So here's an OR gate. All right, let's put the variable a right here. And then let's put a here again. We could put a bar over it, or we could just invert it here. So we could manually put an inverter here, right? We could do that. Or we could put a dot here, right? Whatever you want to do, all right? And then here's the output z. But wait a minute. Let's say that a equals 0. Okay, a equals 0. So if a equals 0, we're going to get a 0 here. What are we going to get here at this input? Well, if a equals 0, this is going to invert it. We're going to get a 1. So what are we going to get out of this OR gate? We're going to get a 1. Okay, let's try the other case. What if a is 1? Well, a is 1. A also goes in here, but it gets inverted. So we get a 0 here. We get 1 or 0. We get 1 again. Guess what? No matter what, a or a equals z always equals 1. So guess what? We don't need this gate again. Total waste of money. So this is fine and dandy, and we can see these are very obvious, simplistic examples, right? However, if you had 1,000 gates or 10 gates or 100 gates and you're looking at all this, it's very hard for you to run through this in your brain. You know, us lowly humans do not have this kind of computing power to run through all these permutations if we had something complex. Therefore, we come up with a visual way to do this. And this will work with 2 variables, 3 variables, 4 variables. After that, it gets kind of complicated. But so if you have a 2 variable, 3 variable, 4 variable logic system, you can actually optimize it with these things called K-maps, all right? So, and again, this is a whole course, you know, or at least a few lectures, which we're not going to get into, but I'm going to kind of show you this just to kind of give you an idea. So, so how you draw the K-maps is like this. So basically, you draw this 2-dimensional grid, and then what you do is you can pick the top. So there's this x-axis and this y-axis. And then what you're going to do is for every permutation of your input variables, right, you're going to write those values down here, and you're going to do the same thing here. All right, and then the order is not important here. We could put S1 and S0 over here. Then the table would go, you know, lengthwise. We could put, you know, we could flip them around if we wanted to, S0, S1. It doesn't really matter. The whole point is you have to have every single possibility for these variables. So I just decided there's 3 variables. There's S1, S0, and C. S1, S0, and C. because there's three variables, I decided I wanted to put S1 and S0 up here because that's kind of the state, and so that's going to go horizontally. And then C, which is this clock, I'm going to put it here vertically. But I could have done anything else I wanted. I could have put S1, S0 here, and I could have put C here. Now, here is very important little note. So this represents S1, S0. So this is the present state, and this happens to be a clock variable. Could have been anything else. It could have been two variables. It could have been another A and B. Then we would have four different combinations for A and B. Here is something that's very important. Look at these variables here. 0, 0, 0, 1, 1, 1, 1, 0. If you can count in binary, this is 0, 1, 3, 2. 0, 1, 3, 2. What's going on? Why aren't we counting in standard binary here, right? The reason why is we need the Hamming distance to equal 1. Remember the Hamming distance? The Hamming distance is the number of bits between one value and another only changes by 1 bit position. So from 0, 0 to 0, 1, how many bits changed? Just this 1 bit. Now from 0, 1 to 1, 1, how many bits changed? Just this bit. Now from 1, 1 to 1, 0, how many bits changed? This bit. 1 bit every time. So we count in Hamming distance binary, okay? Not in binary, but in Hamming distance binary. So, if you can't do that in your head, you can get lists of numbers, you know, for 2 bits, 3 bits, 4 bits, 5 bits, and count like that. Now, here, there's only one variable, so it's either 0, it's either 1. We don't have to worry too much about Hamming distance because there's only one variable. All right. Now, what does this table represent? Well, this particular table represents the variable y0. So y0 is going to be a 1 when c equals 0 and s1, s0 equals 0, 1. Or when c equals 0 and s1, s0 equals 1, 1. Or, where's another one? When c equals 1 and s1, s0 equals 0, 1. See that? So you fill the table up with all the ones wherever the output variable is a 1. Okay? And then over here, here's output y1. We do the same thing. Wherever the system is a 1, we put those 1s there, right? For the variables s1, s0, and c. And we fill it up. Okay, now, here's the hard part, right? And this is the magical part. So now, you see there's this, we've circled these 1s. We've circled these 1s, all right? This is called 1s looping. And what's going on here is this. Mathematically, what's going on is you have to make circles that are rectangular, right? And basically, these circles will always end up being powers of 2. They have to be powers of 2, all right? And so take a look here. So when I circle this, the first thing is that you see this C, it transitions from 0 to 1. And in both cases, this circle covers 0 and 1. In other words, C does not matter. It doesn't matter what C is. I'm still getting the same values here, right? I'm still getting these same values no matter what C is, right? Now, so C is out. We don't need to C. So C has been optimized out. It's been reduced out. In other words, it's like the example here where we've got A or not A. It doesn't matter. It's not relevant. It's always going to be 1 in this case, right? Same thing here. The C is irrelevant. No matter if it's 0, no matter if it's 1, we still get these outputs. So we can throw C away. Now we look a little bit closer. All right, so now 0, 1 or 1, 1. All right, so one of those variables always stays the same, and that's the S0. So S0 stays the same, and then S1 can be 0 or it can be 1. So that means it's irrelevant. S1 is irrelevant. So the only thing that's important is S0. So S0 is the only variable here. So Y0 equals S0. Done. We just optimized that. So this function right here, what was this function originally? Let's try and write it down. All right. So each one of these ones represents an AND term. All right. So the first one says C is 0 and S1, S0 is 0, 1. All right. So what we're going to do here is we're going to go to our drawing program. And we're going to draw a bunch of terms here. Let's go down here in a different color. So all of our terms look like this. They look like C, S1, S0, plus C, S1, 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 S0, plus there's 4 of them. C, S1, S0, plus C S1, try not to make these subscripts, S1, S0. Okay, now let's look back here. All right, so what do we have? So we need to write these terms down. So there's a 1 here when C is 0 and we've got 0, 1. So when C is 0 and we've got 0, 1, when C is 0 and we've got 0, 1, so when C is 0 and we've got 0, 1, so that's like this, okay? We've also got one when C is 0 and S1 and S0 are both 1s, all right? When C is 0 and S1 and S0 are both 1s, that's this term. You kind of seeing how this is working? Now, when C is 1 and S1, S0 is 0, 1, and when C is 1 and when S1, S0 is 1, 1, is this term here. So basically, these two terms are exactly identical to these two terms, except C is knotted here and it's not knotted here. All right, so see these terms right here? We're just going to copy them again, except we're not going to not C. All right, so that's a mouthful, like this. And the other term is like this. Okay, so those are our terms there. Those are our 4 terms. So those 4 terms equal this output y0. All right, so those 4 terms equal our output y0. Now, can we, using Boolean algebra, also reduce this? Can we, using Boolean algebra, also reduce this? Sure. So let's try it. So see this term right here, this C bar? So I'm going to factor it out. So there's C bar. I'm going to factor it out. And then what am I left with? I'm left with S1, S0, plus S1, S0. All right. So all we did was we factored out this C bar out of here, okay, and we got this right here, okay, and then let's see here, and again, as you're doing, and the whole point here is we're doing Boolean algebra, and we may run down the wrong path here, all right, so let's over here, let's see what we can do here. Let's see, in this case, instead of factoring out C, let's factor out C S0. So C S0 is common in both of these, so I'm going to factor that out, and then I'm left with S1 bar plus S1. Okay, so in this case, look at that, S1 bar plus S1, no matter what S1 is equal to, this is always equal to 1. So what do we get here? We just get C S0. See that? Now when we're over here, right, we kind of went down the wrong path a little bit, but that's okay. We can come out of this. So I'm just going to take this and I'm going to copy this up here for us. All right. So this is C bar, and then we've got S bar S0. Oh, sorry, that's S1 bar S0, and then we've got plus or S1 S0. Okay, so what can we do with this term right here? So S1, S0. So what we could do is we could factor out the S0 here, right? We could factor out the S0. So we get C bar, now we get S0, we're going to factor that out, and then we get S1 bar plus S1. So what happens here? This goes to 1. So now we're just left with C bar times S0. So C bar S0. That took care of this whole term right here. Now we got that or, and now we've got this right here. C S0. All right, now look what we got here. So let's factor out the S0. So we'll have C bar plus C, all of that times S0. What's C bar or C? That again is just 1. And we're left with just this S0 here. And this equals Y0. All right, and hopefully that's what this said. Yep, Y0 equals S0. Okay, so you could see that is not the easiest thing on earth to do. It took some time. But when we did it graphically like this, right, we just looped it, and instantaneously we can read off Y0 equals S0, done. All right, and the same thing here. We come over here, C is completely covered, so we can throw C away. We come over here, and the value is the only thing that doesn't change. See the 1 and the 0 changes, so that means S0 is minimized out, right? So S1 is the only thing left, so Y1 equals S1. Instantaneously, you can read that. So the only thing you got to do is be able to draw these K-maps, and then you can do this minimization. All right. So that's how we optimize these complex logic functions that we will make for the state transitions and all the state outputs. We kind of create these logic tables, these K-maps, and then we manually do this algorithm graphically and do this ones looping process, all right? And then that's it. And then we can here's some more, right? Here's some more ones looping. And here's the original K-maps, and you're showing, see how these things are all over the place? So now we can't draw one square over this because this one's 0. You only can draw rectangles where everything are ones, right? Is ones. So we got to break this up in a couple places. So here we can do that. Here we can do one, and then this one just by its lonesome, and that's what's reflected here. You see that? And then when we write this all down, this variable right here, there's nothing we can do about this. This is just C, and then this is S1 not S0, C, and then S1, S0 is here. So this is S1 not S0, so that's this. So that's this thing here, right? And then these guys right here, this one, this vertical one optimizes out C, so we're left with S1, S0 not, so S1, S0 not, which is here. And then this one here optimizes out this variable S0, and the variable that stays the same in this is S1, but we also need C0, and that's this term here. Okay, so not the easiest thing in the world. It definitely takes practice. And like I said, this is typically a college level course in digital electronics, usually I think sophomore year maybe in electrical engineering or computer engineering. So it's not easy. All right, and this kind of goes through this. I'm sure there's graphical examples of this on YouTube. If you type in K-maps and optimization and go to YouTube, you can probably see videos where it shows and then kind of points to the variables and all that. It's kind of like learning matrix multiplying, right? If you've ever done linear algebra, matrix multiplying, it's a little bit tricky. You know, me, I remember to go like that. I grab the variables and I go like that and I multiply them. Okay, and then here's our implementation of our 2-bit counter design with these functions that we optimized with the K-maps, and this is showing how that would be done. And so these functions right here then feed back into the inputs, and then this does a 2-bit counter. All right, does a 2-bit counter, and it's doing it with D-type flip-flops. So D-type flip-flops, not JK flip-flops, which are designed for counting, or can count, but with just standard D-type flip-flops. So this is combinatorially computing the next state based on the present state and then feeding it back. All right. Okay, so sequential circuit design algorithm. 1, define the problem in all the states, inputs, and outputs. 2, based on step 1, create a state table and or state diagram, assign binary codes to each state. You can make them arbitrary, but counting in binary or Hamming distance is a good idea and a good start. Also, there's what's called one-hot design. We'll discuss in a moment, which I'm not going to discuss. 3, derive the logical equations through brute force or K-map minimization. Bottom line is you got to find the equations that describe all your outputs in your next state, all right, and through K-maps or just doing it like we did it right here, right? That kind of thing. Okay. For each flip-flop and each output. Translate the logical expressions into hardware, build your design, make $1 billion. This is my favorite part, make $1 billion, okay? All right, and that's kind of how you do the sequential circuit design. And this is what's going on under the hood. So if, you might get a modern tool where you say, give me a state machine. Like if you're programming or you're designing things in a VHDL, very high definition language for hardware design, or Verilog, it does these kinds of things for you. It builds this stuff for you so you can kind of think in code. All right. Let's see here. Here's the pattern detector that we talked about, and the K-maps for the pattern detector, so the 101 pattern detector. So we did the state machine for it, right? We did the state machine. Where's that? So there's the state machine for it. That's all fine and dandy, but now we actually have to design the hardware that can take the present state to the next state for the input B, right? And that's what is going on down here. And so this example is showing this 101. So here is, we've got two variables, 2 bits to represent the state because there's 4 states. So here are K-maps, right? For S1 and S0, there's our 2 bits that represent the state, S1 and S0. Here's our K-map, here's our K-map, and here is what these inputs are that would get us the next state for S1 and S0. That's taking care of our state machine, but not our outputs. So we've got these two tables here, and then here's our input B, right? And then the in this one right here, we don't really output anything, right? So if we wanted to also put an output, then in state 3 maybe, when we're in the final state, the found state, we could create another variable, call it O for output or Z for output, and then we would have another K-map that would give us the output for that variable. All right, and that's how you do that. So anyway, like I said, I just wanted you to just to kind of see this and just kind of let it sit in your head. So there's, flip-flops, that's how you have memory for your present state. Then there are combinatorial combinational logic. That is what you use to create the outputs and transition to the next state and also feed back the input. There's a methodology we can use to figure this stuff out called K-maps, which uses this minimization algorithm, which is based on Boolean algebra, which is based on doing this ones looping, and these ones loops aren't magical. What they're doing is just graphically doing Boolean algebra. They're graphically doing this operation more or less, all right? And that's what's happening there. Then you write all that down, and then you implement your hardware, and your hardware looks like this. It looks like this. And here's the OR gate. This is ORing together those min terms, right? And these are those AND terms, those product terms, the AND term, AND term, AND term. All right, and then here's C, and here's an inverted version of C because we need the inverted version of C. Here's the present bit output, and then these flip-flops happen to have Q bar, so they already have inverted versions, right? There's the present S1 and the inverted version. So then I just put these things, outputs into all these gates, and we more or less implement what all this is right here. And how do we get all that? From the ones looping in the K-maps, okay? Now, typically, as a modern hardware engineer, electrical engineer, there's not a whole lot of times that you're going to be doing logic optimization. And remember, there's not a whole lot of times you're going to be building things out of discrete logic because you're going to be using microcontrollers and microprocessors. However, you have to still do this to do what's called glue logic. Some point, the rubber hits the concrete and you need to count something up or you need to OR something together. You need to do something, right? And that's going to have to be done discretely. And you may have a function of 5 or 6 variables and you're like, this is wasting 3 or 4 or 5, 6 little TTL chips. Can I optimize this? Yeah, use the K-map to optimize it. Instead of throwing another field programmable gate array or a complex programmable logic device at it, you can just do it with a couple gates if you're smart and know how to do this. All right, and of course you save money. And it also helps you when you're doing your coding, when you're doing your C coding, your JavaScript coding, your Python coding, your PHP coding. Anything where there's an and an or in the language, I assure you, you're probably not taking advantage of cases where you could optimize something if you were to look at it in this way. That's this beautiful crossover between electronics and coding and mechanical engineering, if you ever get into that. Everything has analogies to everything else, and things you learn in electrical you can apply to your programming. Things in your programming you can apply to your electrical, like thinking like you're coding instead of doing hardware. Think of it as code, and then you're implementing the code with hardware. All right? Okay, I think that's about it that I wanted to fry your brain here. And yeah, that's it for the summary. Okay, so we're going to stop here. And what we're going to do next is, what are we going to do next? We are going to look at some simulations. So we're going to stop here and we're going to look at some counter simulations from the previous lecture, the counters we talked about. Then when we're done with that, then we're going to go to the bench and we're going to build a couple little things because we always want to build something and see it in physical hardware and not just simulation. All right, so I'll see you in the next lecture. Bye. All right, welcome back, and we're on the next lecture. Like I said, what we're going to do now is we're going to do a couple simulations going back to the counter material. If you're following along, we just did the kind of bonus section on state machine design and sequential logic with K-mapping and ones looping and some very advanced topics. So now we're going to jump back in here to stuff we understand a little bit better. All right, so what do I have? I've got Proteus running here, Lab Center Proteus, which again is free for the evaluation version, which can run these simulations. The name of this currently is Crash Course EE 2-bit counter 74LS76_01. Of course, it'll be in the material for the lecture. And what do we have here? All right. So again, this always looks complicated, but let's break it down piece by piece. So first we're using the 7476, which is a JK flip-flop. It's a dual JK flip-flop, so we can implement something that has 2 bits, like a counter. They're completely independent. J and K input, and they've got reset and set inputs, and Q and Q bar. So these are really full featured. So these are great for state machine design. You can do a lot of things with them, or you can just use them for simple things like 1-bit memories or counters or whatever. Now, to make the JK flip-flop count, we're going to use it in toggle mode. And if you recall, toggle mode is when J and K are both tied together and tied high, the flip-flop will toggle 1 to 0. All right. If it's 0, it'll maintain the current state. If it's a 1, it'll toggle on the clock transition, on the rising edge or the falling edge of the clock, depending on the design of the particular flip-flop. Okay. So if we take one flip-flop and we take a clock signal and we tie it to the flip-flop and we put J and K, tie those together and assert a 1 there, this will toggle and it'll count 0, 1, 0, 1, 0, 1. Now if we take the output of that, all right, and we take that output and we tie that to J and K, we take that output and tie it to J and K, all right, then that will then be used as the input into the second bit to tell it to toggle or not to toggle. The same clock goes to both of these flip-flops, all right? Same clock goes to both the flip-flops. All right, so we've got the output from the 0 bit. We take that and we tie it together and we put that into J and K, all right? And then this output right here, don't let this confuse you. Let me highlight it. This output right here is just so we can display the bits, right? That's just an output for display, so think of that as not even there. All right, and then the output of the bit 1, right, B1, doesn't do anything. It just sits there. So this is going to count 0, 0, then it's going to count 1, 0, then it's going to count 0, 1, and then 1, 1, and then cycle. So it's going to count in binary from 0 to 3 and cycle. So then what we do is we take the output of that bit and we take the output of that bit. We take them both and we put them here, drive them out here to 2 LEDs for display, to ground through some current limiting resistors. We also take those bits and we put them into A and B, the low bit and the next highest bit of a 7447 display driver so we can see the digits. Then we tie C and D low, right? And then we set up the lamp test and the trailing 0 and all that. We set those all high to deassert those features. Okay, now what else do we have? We've got set and reset here. So if we hit these switches, that would set the bits and this would reset the bits. All right, and then we've got our clock right here. All right, and then if we look at our clock, I'm running our clock at 2 hertz. All right, and it's a low voltage is 0 volts and the high voltage is 5 volts. So we're doing a 5 volt kind of system. Let's just put that at 1 hertz. All right, we'll slow it down. Okay, and let's go ahead and let's run the simulation. So 0, 1, 2, 3, and also as that's counting, you can see the bits here. So there's 1, there's 2, there's 3, right? And again, you're going to have to learn binary. You're going to have to get pretty comfortable with binary. Now, as this is running, we can hit these sets and reset. All right. So let's let this thing get to like 2, and then I'll reset it right when it hits 2. 1, 2, and then I reset it. And see how it went to 0 automatically? Now, if we do set, it's going to set both of them to a 1. So let's let it get to say 1, and then I'll set them both to 3. See that? Because we set both of them to 1 and 1. So that's how we can put a 0, 0. We can inject a 0, 0 or inject a 1, 1 with that set and reset. And that's it running. All right. So let's stop that. Let's increase the clock frequency. How about 10 hertz? 10 hertz. And let's run it. And then there we go. So it's counting down here in binary so we can see it. And then it's transitioning here. Now, take a look. When I move this mouse, that slows the system down just because of the GUI interfacing and all that, right? And so you kind of typically just leave that mouse alone and it will kind of act more real time than it should. it will act real time as it should. If you move things around and start moving windows around, then it'll have a hard time maintaining real time. And down here you can see the CPU load is only 1%, 2% in the simulation. The reason why is because it's mostly digital. It's a very simple digital simulation. As we put analog blocks in there, then the computer has to work harder. All right, so that's cool. So basically, how many chips does this take? Well, the 7476 is one IC, and then we've got our display driver, another IC, and that's it. So two ICs, we basically made a counter plus a display, and then we just have some passive components, some switches, capacitors. Here, remember, always put your bypass capacitors. There's the bypass for this chip. Here's the bypass for this chip, right? And some LEDs, some pull downs, some pull ups, and that's it. Very, very simple. All right, let's go ahead and resave that with that 10 hertz. We'll leave that. Okay, now let's go ahead and look at another simulation. All right, a little more complicated simulation. So what is this simulation right here? This is the 4-bit counter, the 4-bit counter. Let's take a look. So if we go back to the material here, close your eyes if this gives you a stomach ache, scrolling really quickly. I know some people it does. All right, so when we're talking about counters, we had this, a 4-bit counter to count to 11 design. So this is the 8 place, the 4 place, the 2s, the 1s. If you add all that together, that makes 11, right? So this reset code right here, so this is 3 plus 8, this is 11. When this reset code hits here, 1011, we put that into this AND gate and we code this up correctly. So we got to invert this 0 here, right? And then when this code hits, this will output a 1, and this 1 can go into this reset of this counter. So this counter has 2 inputs, and depending if they're 0, 1, or 1 or 0, you can get it to reset or count. Okay, so that's all we're taking advantage of, and that's why these chips, that's why these ICs have extra inputs like that, so you can kind of finagle a function without adding extra logic. Okay, so here's that 74LS93. It's a 4-bit counter. It typically will count up all the way to 15 and then reset. But let me show. I want to show you something. I want to show you something here. I believe, is this it? Yeah. So this is the 7493 data sheet. A data sheet from a manufacturer, and what I want to show you is the actual internal architecture of this. So this is the Philips version of this 4-bit Ripple binary counter. All right, what I want to show you is this, and let's hold on a second because I don't know if I like the way that this one looks. Give me a second here and figure this out here. Yeah. Okay. I don't know if I like the way that this looks, but what I want to show you here is this. So this right here, the CP, all right, this is the input. This is the input. This line right here is the input, okay? And notice the output of the first stage comes out to Q0. So the output of the first stage comes out to Q0 here. So remember, this is a binary counter kind of thing, but the output of the first stage comes out to Q0. Now look at the second stage. Here's the output. It goes into the next stage and it comes out. Then look at this stage. It goes out and it goes to the next stage. This first stage is disconnected. And the reason why is it just adds some functionality. So if you want to make this into a full 4-bit binary counter and not a 3-bit binary counter, what you have to do is you have to take this output here and then tie it back into this CP1 to connect it here. And then that basically creates a 4-bit binary counter and connects it all together. All right, so a little tricky. I don't really like the labeling of these things, but this one is separate. And to get it to be a 4-bit binary counter, you got to take this output Q and tie it right back here. And if you don't want that functionality, then you can leave them open and you can make the counter do different things. It makes it more flexible. So you say, well, why isn't it connected? Well, that's why, to make it more flexible. That's all. Okay, so let's go back to our design. So this makes it a little bit easier. So see QA, QB, QC, QD, and see we take that first bit output and then we tie it back into this clock B here, okay? And that closes a loop and gets the counting function to work for 4 bits. All right, so clock A is our clock. That's all there is to it. Now, this R01 and R02, this selects different counting modes, reset mode, this and that. So if we just tie one of these high, then based on the second input, if it's 0 or 1, it will count or reset. If it's a 1, it'll reset. If it's 0, it'll count. So again, why are there 2 of them? To give you this flexibility so that depending on positive logic or negative logic, this and that, we might have 2 inputs we need to use here to do this, and we would have those 2 inputs. But since we don't need it, we tie it high, all right? And we look at the logic table inside of the data sheet to make sure that's what we want to do. All right, so this is a counter. This is just going to count. So here's the beautiful thing. Now we've got this counter. Its clock is coming from here. Forget about how we're deriving this clock. I will show you that in a second. We've got this 1 pin pulled up here. All right, we've got the 4 outputs right here. We're taking those into 4 LEDs so we can see what's going on in binary. We're also taking those 4, and look, what do we have here? We've got our trusty display driver circuit. And I don't redo this every time. I just do this. I just grab it, I copy it, I paste it, bam. Look at that. That's how fast, you know, this is the ultimate copy and paste is hardware design, right? Software, you can't really do this. You can copy and paste, but you got to change things and do this. With hardware, you literally copy and paste. It's beautiful. All right. Okay, so there's our display. There's our binary display. Now, let's talk about what's going on here. This is this feedback circuit so that when we get that code 1011, right, it will reset. So this basically takes the outputs here, puts them into this AND gate, and then inverts the proper one that we need because we're looking for a 0 in one of those bits, right, 1011. And then, and this also I decided to change the code to 1101 13 instead of 11. Okay, I changed the code from the example in the book. The example in the book does 1011, and then I decided to make it 1101. All right, just for fun. Okay, and you could change it to anything. Just move the inverters or add more inverters. Do whatever you want. When we get when the code is asserted on this input of this AND gate, and we get all of these things to be 1s, right? So if this one's a 0, then we'll get a 1 here. Then this is going to output a 1. That is the reset code for this counter. So when we get a code 13, it's going to reset. So when we hit 1101, it's going to reset. Now this is very, very, very important. I want you guys to make sure that you get this little point right here. When this hits, it's going to instantaneously and asynchronously reset this counter. All right, so it's going to happen really, really fast. So it's not going to maintain this 13 count, right? It's only going to hold it for like nanoseconds. Then it's going to propagate through here. It's going to propagate. So we're talking about 5 nanoseconds here, 5 nanoseconds here, and then it's going to hit this reset. And whatever that reset takes, then it's going to reset it. So it's going to glitch out this code for a few nanoseconds. That's very important to know. It's going to glitch out that code for a few nanoseconds, then it'll reset. Okay, so now we've talked about all this. Now, oh, and what if we didn't have a 74HC21? This is a dual 4-input AND gate, right? What if we didn't have that? Well, we could just use 2-input AND gates and just tie one here, and then take the outputs of those to 1 here. So we'd have to use 3 of them, but we could do it if we didn't have this more exotic part, okay? All right, what's going on here? So this is our clock. So first I've got a clock signal here, all right? And here's our clock signal at 1 hertz, okay? And that clock signal goes into this OR gate. So now we basically want to have 2 different clocks. One is a manual clock, which I could pulse myself. One is another clock, maybe derived from some other part of the system. You can't just tie those together. Remember that? You can't just tie signals, because if one is high and one is low, that's called a short circuit. That's bad. But so we have to put them through some kind of logic, an OR gate in this case, right? Now, you could technically tie them together with resistors and diodes, right? But that would be crude, and you don't want to do that. That's Mickey Mouse. We don't want to do that. We want to do it properly with an OR gate. Okay, so let's go ahead and run this and see what happens. So we're expecting it when it hits code 1101 to instantaneously reset. So this is going to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we're going to see some of those weird codes that represent 10, 11, and 12. Okay, and then it'll reset. All right, let me get it all on the screen here. Okay, here we go. Ready? Run. So 0, 1, 2, yep, 3. That's 3. Then this will be 4. And these will be off. 5, this one will turn on, right? 6, this will turn off, this will turn on, right? 7, these 3 will be on. 8, now this will be on and these will all be off. 9, this will be on. This will be off, this will be on. There's 10. There's 11, there's 12, and then here's our reset right there, and it reset. Now what I want you to do is I want you to watch. So right now, this is always a 0. See the blue 0? Blue represents 0, so it's always in count mode. Now when this thing hits 13, which is in 5 more counts, then you're going to see this turn red. So I want you to pay attention right here, right? Did we miss it? Did we miss it? We missed it. Okay, let's pay attention again. So 2, 3, 4, 5, 6, 7, 8, 9. Keep your eye over here. 10, 11. It's going to happen really fast. And it's happening so fast we're missing it because it is an instantaneous glitch. Okay, now let's turn the clock off here. So first let's stop the simulation. And let's see here, we'll double click this and we will make the frequency, we'll make the period say 1,000 seconds, all right, which is a long time. All right, now that clock won't clock this, but we'll do it manually. Okay, so now we'll hit the system clock manually. So here we go, so watch this. So there's 0 and So what's happening here is this clock is actually stuck asserted high. So let's fix that. Let's fix that. It's asserted high. All right. So for some reason it's starting off high. So what I'm going to do is I'm just going to put that as a 0. Its high value is a 0. So this thing should be quiet now. Now there it is. There's the 0 that we want. And I'm just trying to. I can't really get this any bigger. We're kind of stuck with it this size. Okay, here we go. So it's manually pulse the clock. 0, 1, 2, 3, 4, 5, 6, here we go. 8, 9, 10. There's 11. There's 12. Now the second this hits 13, right, the next pulse, this thing is going to reset, all right? And there, and it reset. And that's it. So it does exactly what we would expect it to do. And let's turn the clock back on. We got to stop the simulation before we can edit any of the properties. So pulsed high voltage is 5. And let's put its frequency back up to 10 hertz. Nah, that's too fast. Let's do 3 hertz. 3 hertz. All right, and let's run it. And there we go. All right, and reset. That's it. Okay, so again, simulation is great because you can kind of work things out and try things, but you know, it's always nice to also build things on the bench so you can get those real world aspects of stuff. So that's what we're going to do next. So I'm going to think of, we may build one of these things, we'll see, but I'm going to think of something derived from one of these things. We'll build it on the bench. So I will see you in the next lecture. All right, bye. All right, welcome back everybody, and we are on the last section, the end of the course, and now what we're going to be doing is we're going to be designing circuit boards. So I am going to give you a crash course within a crash course on PCB printed circuit board design using Circuit Maker. So you know, throughout the book or throughout the course, a lot of times what I'll do is I'll go over something I've already kind of gone over, and those are for students that are jumping around, all right? So some of the stuff I've gone over a little bit, but it'll help refresh your memory, and then also if you're jumping around, it'll help out. So what we're going to do is we're going to break this up into 3 primary parts. So first, we're going to install Circuit Maker right now, all right? And we're going to do that after we take a look at what's up here on the screen. We're going to install Circuit Maker, which is fairly easy, and I'm not going to sit through the entire thing. You'll be able to do it. It's just like any other installer. All right, then what we're going to do is we're going to kind of go over an overview of circuit boards, printed circuit boards, kind of how they're manufactured, what's inside of them, what they look like, and just some of the terminology before we jump into actually playing with Circuit Maker and designing circuit boards. So, and then the last part is we're going to actually design circuit boards. So I've kind of pre-designed 3 different projects, and they start off, one is fairly simple. It's a through-hole circuit board, and it's got a 555 timer on it. And it's I'll show it to you when we get to it. And then the other one is a little organ, all right, again based on a 555 timer, trying to keep it simple with things that we've used. And then the last thing is kind of like a Simon game, a color matching game, Simon, if you've ever seen that. And that's the most complex, and that one's surface mount, not because it needs to be surface mount, just because, but it's so that we can see a surface mount example. And these circuits are complex enough where maybe the first one took me 10 hours, I don't know, 15 hours from beginning to end of laying it out, picking the parts, moving things around, all that, designing it. Maybe the next one took 20 or 24 hours, and maybe the last one took 30 hours. Maybe it took half that much. Hard to say. The bottom line is they take a long time, so it's not something I can just sit and lecture for hours and hours and hours. It'd be huge. So what I'm going to do is we've already got the 3 circuits already completely designed, so I'm going to show them to you, and then we're going to kind of redesign them in real time. The first 2 at least. The last one I think is just too complex to even remotely do in real time. So I'll go over different elements of it and talk about it. But the first 2, I think we can sit here and I can talk about something and show you how to do it, and then just speed the video up as I'm kind of moving things around. So you might see 20, 30 minutes of me moving things around will just be 1 minute. So we're gonna figure it out, and we're just gonna do it like that so that you can actually see the thought process and what goes on. So anyway, let's begin. So up here on the screen, I've got chapter 5 from the book, the design your own game console, or Black Art of Game Console Design. Same thing. All right, and you should have already read through chapter 5, and we've already gone through this material a couple times in a couple different places. But what I want to do is I just want to skip down to the section on printed circuit boards. And I want you to read this section again, because when it comes to prototyping and building things, you really need to know all this stuff. So right here it's talking about SMT, or surface mount technology, the different sizes, these codes, the 402, the 603, the 805, the 1206. When we do surface mount, we're going to kind of stick to this 805 size, and then I recommend to you kind of you start at 805 is good, and then maybe go down to 603 and 402 as your skills increase, or as you need to make things real small. All right. So anyway, and then here's some surface mount components and their different names. This is what TI calls them, Texas Instruments, SOIC, SOP, SSOP, and all of these have acronyms. Like this stands for Small Outline Integrated Circuit, and so forth. So a lot of these, all of these have names, and some companies will call them slightly different things, all right? But you got to kind of just look at them and figure it out, depending on the company that you're getting your parts from. But anyway, you've seen this before. And what I want to do is get you down to this section here. This is on wire wrapping. We've talked about this. Okay, and then we start talking about circuit boards here. All right, so I want you to kind of reread the section on circuit boards, because that's exactly what we're going to be doing here. And this starts roughly at about page 291 in this PDF here, but it's section 5.5, printed circuit boards. So it's kind of showing kind of how you can do them yourself with just copper boards and then etch them and all that, and we talked about this. And then here's a design where you can see there's layers of this. This is a 3-dimensional stack. This only has 2 layers actually, a top layer and a bottom layer. Red layer is top and blue layer is bottom, and then wherever they overlap you get kind of this magenta color. All right, so that's showing that. And when we go over, and then here's a 4-layer design, much more complicated and very hard to see what's going on if you stack all the layers visually. So, and then, here's some cross-sectional views showing what the circuit board looks like. So here's a board that has 4 layers where you've got signal, signal, power, power, and then you've got power, signal, signal, power, so 2 different ways of doing this. Anyway, so I want you to go through all this thing and learn all the terminology and so forth that's inside of this document if you haven't already read this, all right? So there's a lot of information here, and you really do need to read it. Even though I'm going to be talking about this, I want you to read it also, okay? And then we talk about different tools, Lab Center here and whatnot, and we're going to be using, of course, Circuit Maker because it's free, all right? So, and then of course you can install Proteus yourself, and we've talked about that many, many times, Lab Center, Proteus, and you go to their website and install that, but it is expensive and it's not free, but the eval version will work for simulation and you can play with it at least. All right, so anyway, chapter 5, I want you to read the entire thing, specifically on the PCB design stuff, so that's fresh in your mind. All right, so now what I'd like to do is we're going to install a Circuit Maker. All right, at least show you what you need to do. Now, just before I made this video, I did a Windows update, and now of course things are crashing. So Circuit Maker started crashing, and it's never crashed before, ever, ever, ever. It's really a solid program, slow but solid. So hopefully it doesn't crash on us. All right, so the first thing we're going to do is we're just going to go to circuitmaker.com. It's spelled just like it sounds, circuitmaker, one word.com. Okay, all right, and now I already have an account. So the first thing that you have to do on CircuitMaker, the software is free, is so you're going to sign in here, sign in or sign up. And so we would hit the sign up if we were here the first time, right? So this is what you're going to do. So you're going to just put your name here, first name, last name, your email, accept the terms, you're not a robot, and then you're going to do sign up, and then keep going through whatever screens that you need to do, and then that's it. You've got an account, and that's all there is to it. Now what's going to happen is once you've done that, and you can probably do this without even doing it. Yeah, you need to do this. No matter what, if you're not logged in, it won't let you get to any of these menus. So once you've created a free account, which takes all of 5 seconds, I just have no more emails to use, so I can't create another account unless I create a fictitious email just to do that, but I think you guys can figure that out. So let's go ahead and sign in. All right, so we've got my email here and then my password, and then I go ahead and sign in. All right. Great. And one thing, Circuit Maker has a lot of people. There's a graph someplace. If you type in Circuit Maker number of students or users, user base as a function of the month, it's like this exponential curve. So I think there's like 100,000 or 200,000. The point is there's a lot of people on this website, and there's a lot of people using the software. So sometimes the website does weird things, like you just saw it put up that couldn't find page. All right, so anyway, when you log in, you'll kind of go to this start page here on the web, and this is just a web view of things, and you can do things on this web view and go around projects, hubs, components, all these different things that you might want to mess with. But you're not going to use this for your actual design, of course. All right. So, for example, I can go to my projects here, which are the projects that we're going to actually make. So you can see here's that first one. This is this magic wand. That'll be our first one that we do. And then we're going to do this 555 timer organ. And then we're going to do this Simon. All right. So when we get to that, we'll be able to go to each one of these and play with them. But we're not going to do it on the website. We're going to do it in the tool. So for example, if I click on this right here, okay. All right, so if I click this right here, so I can follow, I can edit, I can delete it. I got a little picture there. You got your profile. It kind of shows you all the design files and all the things, but I can't open it, right? Because I don't have the tool right here. All right, so this is just the data view so that people on the website from a web view can see what's going on with your project and so forth. Now, the interesting thing about Circuit Maker, which we've talked about, is this is a very open source kind of community. So the whole idea is other people can see your designs, and they can fork the design also. See how they can fork the design? And then you give one of, I think there's 6 or 9 licenses, from completely don't touch my design, you can't do anything to it, to do whatever you want with it. You select whichever license that you want. All right, so while you're watching this right now, these things are not all done. So by the time I get to the next couple videos and we actually start designing, you would be able to go here and mess with these. So if you try and mess with these things right now, I may change them as you were to watch this video. But of course, by the time you're watching this video, it'll all be done. So anyway, all right. So now, so this is the website. Play around with this. You can figure it all out. But what we want is we want the actual desktop application so that we can design circuit boards. All right, and it's a cloud-based application, so it runs on your desktop and it communicates to the cloud to get the footprints of the ICs themselves, the data sheets, and that's where your files are actually stored. All right, unless you generate outputs, then those are then downloaded locally so that you can take them to a manufacturer and all that. All right, so what we want to do here, so you created your account. This would all be empty, of course, so let's go back home. So this would all be empty, and this is what you would see. It would just come here, and these are just general projects from everybody else. So how these projects are sorted up here, these are the people that are uploading the most stuff, I would imagine. All right, I don't play with this much, this interface right here or anything, but I would imagine that's what's going on, and that's why it's putting these up here. Okay, so we just go to download, and when I click that, because I'm logged in, it goes down here and it starts downloading circuitmakersetup.exe. All right. So then what you would do is you would go ahead, and I'm not going to do this because I've already done it. So then what you would do is you would go ahead and open this and execute it. And as you do that, it's just going to be a simple install. It's a Windows installer or whatever your platform is. Simple, straight installer, and then it's going to install on your system. Once it's installed, now, all right, you can have this web page open if you want, and this is where all the help ends up anyway. It pushes you to a web URL. All right, now that we've got that going, so now let's go ahead and it'll install after you're done, and then it's going to give you an icon just like anything else on your desktop. So we're going to double click Circuit Maker. All right, two things. The installation is fairly long. It can be very long because it's going to the cloud and it's doing things. So depending on your computer and your connection, it might take 5 minutes. It might take 25 minutes. Also, the first time you run this program, and the first few times it seems, it's really, really, really slow because it's caching things, it's downloading things. Then over time it seems to speed up. And then of course, as you cache more and more components that you use more and more often, it seems to speed up. But just be patient with it because it is a cloud-based program. Okay, so now you can see that this window right here is mimicking this web view. So it's very, very similar. It's mimicking the web view. All right. Now, another thing you can also see is I've got two windows here open, right? Now, this other one is right here. So I've got two Circuit Maker windows, and the reason why is because I drag this one over here to my other screen, which you can't see. And what that helps me do is on one screen I put the circuit design, and on the other I put the layout, the PCB design itself. All right. So in our case, I'm going to you know what? I'm going to leave that window. I'm just going to minimize it. I'm not going to use that window. I'm going to do everything over here so you can see it, of course. But that's nice if you have multiple monitors, and if you've got a third monitor, then you can go ahead and put something else on that as well. All right, maybe you could put this start page. Okay, so that's the program, and then now I'm already logged in here. Okay, so what we're going to do is this is how it's going to look kind of when you launch it. So when you launch this program, so I'm already I was logged in, and let's close Circuit Maker again. I hope it doesn't crash. All right, there's that web view, so same thing. So let's launch it again. I've logged out this time. Now, I think it might auto log in. We'll see. We will see. All right, it's opening all my windows up, and it seems to know who I am. Okay, no, it's not. Good. All right, so here we go. So this is kind of what you should end up getting. So I'm going to type in my credentials here, my email, and then my password, which I don't remember any of my passwords. So if I'm ever tortured, you'll never get them from me. And I'm just going to put remember me here, sign in. And even this sometimes takes a while to sign in. Okay, so here we go. So we got projects, which are everybody's projects, the whole planet of Earth. And then we got my projects, which I've got three here for you, and then one thing that I'm working on, another little product, experimenting with this tool. So here they are right here. And now we're not going to go through a lot of this right now. We're going to stop in a minute, and then we're going to go and talk about general PCB technology, right? But since you probably installed this, let's see if we can get this thing to do something, and you can try something. Okay, so the first thing is, one thing you can do is you can look for anything under my account. So under Andre Lamoth. So under Andre Lamoth, and there is a little accent on the E right there. So you got to put that in. Or you could just search for Lamoth, I would assume. Or you could search for this name. All right. So either way, you can find all these projects, and then you can open them up and you can fork them and do whatever you want. And of course, I'm going to tell you exactly what we're going to do when we get to the point when we actually redesign these things. But let's just give this a try. So let's load one up. I don't want to load the other cool ones. We'll just load the simple one up first. So I'm going to click on this one. And because this is kind of a web view, you kind of single click. You can double click, it's not going to hurt it, I don't think. But if you single click, that kind of gets it done. And things will kind of flicker. The mouse will flicker or whatever, and it's doing stuff. There should be some kind of processing or busy signal. But anyway, So now we can see, we can go in here, we can edit, we can delete, we can fork, we can follow, we can do whatever we want. And you're seeing my personal view here. And then, or we can just say open design. All right, so we're going to open design. All right, and it went to the cloud there and got the files. Now, currently, there's two parts to this design. One is the schematic. One's the schematic, and one is the circuit board itself. All right, and when you're starting off in PCB design, you may not know the difference here. So the schematic is the actual electrical design. It's completely abstract. It's just a bunch of blocks and wires and all that. It has nothing to do with the physical design, which is the printed circuit board. All right, so what I'm going to do here is, here are the two documents. So over here, and we're going to go through this tool as best as we can. I've been learning it also. Of course, I use Proteus Lab Center for the last 15 years, but actually used this tool before back in college when it's Altium, so I've used this for many years as well. So the good thing is it's like it's very Windows-ish. Whether you're a Linux user or not, I mean Windows kind of, not Microsoft Windows, but it's just a Windows-like program. So it's things do what you expect them to do. But it is tricky finding things and all that. And as we go through these designs, hopefully we'll go through enough examples where you can see how to do most things. All right. Okay, so all right, so over here in the document tree under projects, so under home here, we've got these project documents, and we can select these here and then load them up. All right, so the first one we're going to load is this SCH doc, and this is the extension for schematics. So I'm going to double click that. And there are some things I don't like for example, I'd like to see that highlighted, right? I can't tell if I'm clicking it. It doesn't highlight it. So, you just got to bear with this. Like I said, this is a very webbish kind of interface. Even though it's a desktop application, it's very webby, and I don't like webby stuff. In fact, if everyone got rid of internet tomorrow and cell phones and social media, I would not care. I would just be like I was back in the 80s and 90s on my computer, bulletin board, and just do everything on your computer. All right, so this is that slowness I was talking about. Now, once I've got this thing loaded and running for a while, and I've got all these applications or all these files loaded, everything is pretty quick. But the first time you do it, you're like, what is it doing? This schematic can't be but a couple hundred K size, right? Because it's basically a very simple data structure that references other things. So why does it take so long? I don't know. So I have no idea. Bad programming, using too many APIs, too many layers, probably. So let's give it a second here. Let it keep spinning there. And but the one thing that you're going to really, really like about this, and of course you have no frame of reference if you haven't used other tools, but I'll tell you right now, I've used many, many CAD tools, PCB CAD tools, and this is hands down right now for free better than EagleCAD. It's better than KiCad is another free one that I used to recommend to people. But this is very, very natural, and it's very professional, and it's very, very close to Altium, which is like the premier PCB design tool in the world. $5,000-$6,000 a seat plus, depending on what pieces you want to it. So anyway, all right, I'm going to click here. So whenever you see, little things spinning like this, you know that something's not responding possibly. So I'm going to click. No, it's downloading something. It's downloading something. Let's let it keep doing that. And then I will just edit this out. All right, yay, it's done. Okay, so there's the schematic. Now let's load the layout. Okay, so now you see it is highlighted. So now I'm going to double click and I'm going to load the layout, which will open up as another tab inside of this main window here. So again, this is going to take some time. So I'm going to just edit this out, and so it'll just seem like instantaneous too while I sit here and twiddle my thumbs. Yay, there it is. All right, so this probably looks pretty confusing, like what are we even looking at here? So I'll show you that in a second. And like I said, I don't want to really get into this right now. I want to save all this so we can go through this in a sane way, but this kind of a, just a little sneak peek. Okay, so here is the schematic, and now one thing is I'm going to do as I play with this thing is I'm going to go over here. No, I'm not going to go over there. I'm going to turn on this key press tool that's going to show us key presses. Key press or key I or QI, key press. We'll turn this on. All right, and let's go back. All right, so now over here on the left, you can see what I'm doing here when I type. All right, and use the mouse. Now, I found that this, I've played with a lot of these little applications that show key presses and mouse movements. On my particular computer, with the software I'm running, with God knows what drivers, it seems to crash a lot. It doesn't crash the computer, but it crashes. So we're going to try it just so you can see this, because it's kind of hard to figure out what I'm doing, and I don't even know what I'm doing sometimes. It's just I feel like, am I hitting Shift or Control or Alt? So that way you'll be able to see, and I'll try and repeat what I'm doing. All right. So anyway, so what I want to do here is I just want to make this bigger. So if I right-click on it, that allows me to drag this window. So right-click, drag, and that's common in a lot of applications that are drawing programs or whatever. Right gives you the entire canvas. All right, now if I want to make this bigger on my particular setup, the scroll wheel. Okay, the scroll wheel is set to move it up and down. So if I hold down Shift, I believe, or Control, yeah. So if I hold down Control and I use my scrub wheel up and down, I can get it to resize. All right, so that's one way to do it. All right. So, okay, so now if you look at this design, it's fairly simple. It's got a 555 timer over here, and this is generating a system clock for us. Then it's got a 4-bit counter, which just counts up, all right? And again, you're going to see how I picked these, how I did all this, and all that. Then the output of the 4-bit counter, we take 3 of those bits, and we put them into a 3 to 8 decoder. So as this thing counts, the 3 to 8 decoder turns on these outputs in sequence. So Y0, Y1, Y2, Y3, Y4, and lo and behold, I've got these LEDs lighting in sequence, right? So it's kind of like a magic wand, right? And then we got power over here, some batteries, and you're going to see all that stuff. Now, let's go to the layout real quick. So here's the layout. All right, and again, so I'm holding down Control and scrubbing it to make it get bigger so I can see what's going on. And so you can see how I've laid all this stuff out. So I had to do a few things here. I had to figure out the size of this board, right, which I basically said, how big are the batteries? And then based on the batteries and based on the LEDs and kind of some rough spacing. The one thing you're going to learn, and we're going to go over this in gruesome detail later when we actually do the design, there is no why when you're designing circuit boards. A lot of times it's a multitude of things. It's I want it to look good. I want it to be easy to assemble. I want it to be easy to maybe manufacture. I want it to be cheap. I want this. I want that. There's many constraints. It's an optimization problem, very complicated one. And as of yet, no computer has been able to do this. There's no computer program yet that can completely design a circuit board from a schematic itself. So there's software that runs in these things that'll place the parts. There's software that'll route it out. But there's really nothing that decides, well, what shape should I make the circuit board? Where should I put this? What should I do? What should I this? And kind of give you some end result. Now, probably someplace in a university or at one of these companies, someone's got something that sort of will do this. But without machine intelligence and a really advanced expert system, it's just going to be a train wreck every time. So for now, we have to do everything. So we kind of lay the parts out ourselves. We kind of route it ourselves. There are auto routers, and we're going to use the auto router, which in this is not bad. But on complicated things we wouldn't do. But for the most part, you have to do this. So I had to sit here and play with this, and this is why this takes a long time. Should I put the resistors here? Should I put them there? Should I make the LEDs this way? Should I make them that way? Should I put these chips here? And as I do this process, all these things are going through my mind of 30, 35 years of designing circuit boards, which I'm going to try and distill to you as I'm doing this in real time so you can see what I'm thinking, right? And if you listen to me design and some other designers, you can take all of us together and take the best parts, and then you do your own design. All right. So now watch this. So this is a 2D view, and it's a multi-layer view. So right now we can show one layer at a time. So I'm going to go to this view, and then single layer mode. And so now this is the back copper or the bottom copper. All right, so this is the layer on the back of the board, and then I can press a couple keys. There's the top copper, and then I can start going through all these layers down here, all right, that show all these different things. But what we're really interested in most of the time is just the top and bottom copper, obviously, when we're doing these designs. And there they are right there, all right? And when I when we go over this, I'm going to go over and talk about, what's going on with these traces. They're going through these. Is this okay? What were my thoughts? All that kind of stuff. But there's something cool that I want to show you. So I'm going to go out of that single layer mode, and I'm going to put this all the way back so it's visible on the screen. All right, and this is a really odd shape, right? Obviously, I made it like a wand, so it's real long. But check this out. So I press 3. I hope it's 3. Yeah. And what's happened now is this has gone into a 3D view, and it should, it's downloading everything in real time as we're talking here. So it's downloading everything. Let me move this around. There we go. Zoom it out a little bit. Zoom it out. Okay. And then, so when you press 3, it takes it to this view. You press 2, it goes back to this 2D view. So 3 goes to this 3D view, which is just awesome. The right button grabs the screen and moves it around as usual, but in 3D. And then if you hold down Shift, it puts this little sphere. And wherever you put that, that becomes your rotation point. So you press that. Now, with your mouse, you can either press these 4 directions here, or you can grab with your right button. So, and, get it to do things. And so that action is not, okay, there we go. So I can get it on that axis, and I highlight it there. So you got to press the right button. If I press the left button, it doesn't like that. So the right mouse button, okay, right mouse button, right mouse button, right mouse button, or you can just put it on there and just kind of go in general and just kind of drag. And that's what I like to do, like a 3D CAD program. And now I'm going to zoom out a bit. So there it is. Now, so that's what it's going to look like, right? And so there's 3D models of these components and 2D models for the actual circuit layout. So some, poor person had to sit here and make all these models. All right. Now the community makes a lot of these. I've, made a couple of them, and other people make dozens of them. Some people probably made hundreds of them because they just sit and do it. Now, for example, these parts right here are not showing up, not because they're not in the design. There's just no model for it. All right. So this is, we don't get to see a model because there's just simply not a model, but this is what the PCB looks like, and that's what we care about. Same thing with these potentiometers, there's just no model. All right, so that's it. So that's why this thing is really, really cool, because not only can you design your circuit, you do your schematic design, right, over here. All right, then you go and you lay the thing out. You lay it out here and you get all the traces and all the parts and all that, but then you can kind of do this visualization and see what the thing will look like. You can see above and below and all that stuff, and kind of see what's going on here, right? And then that will help you in your design, and also to fit into enclosures or whatnot. So for example, say that I wanted to put this in a toy, right, and actually sheathe it in plastic and all that. I believe, I'm pretty sure you can export out the 3D step model, STEP, a 3D model of this entire thing, and then import it into something like SolidWorks or Inventor, and then use that as a model to show what you're, obviously it's not going to work or anything, it's just a static model, into your 3D model of your plastic design, so you can kind of see what's going on and see where things are going to potentially collide and interfere. So anyway, so that's Circuit Maker, all right, and then again here, let's go back to this view, which is just the circuit board. All right, and go back home. All right, and then if we go, I believe if we go to view here, we can go home here. Yeah, and then this just gets us back to our page here. We can go back to my projects again, and we can load up a different project. And the cool thing is you can have as many projects loaded here as you want. And I advise you do load them, because that way they stay in the memory and they're quicker to get to. All right. So anyway, that was just like, I just want to show you this just a little bit, but mostly I care about you installing this. So again, to reiterate, you're just going to go to the Circuit Maker website. You're going to create an account. You're going to download the installer. You're going to install the program. When you're done, you're going to go on your desktop. You're going to double click the icon, and then this thing is going to pop up. You're going to log in. It's going to come in with the login screen. You're going to log in, and then you're going to have nothing. So you're going to set up your profile. So if you go to My Profile, you're going to set up your profile, right? And after you've set up your profile, then so people can see you and talk to you and communicate with you. And I just realized I had 9 messages. They're probably just bot messages. And then what you can do is start searching under different people, their names, or just search. So for example, if we go here, and we see here, let's see, we go home, we'll go to projects, okay, and then I'm sure, which I can't see right now, so this in this particular view here, components, projects, and yeah, view all, I don't want to view all. There we go. Okay. Was that there just a second ago, that search box? Maybe it was. Maybe I'm tired. Anyway, so if we type in search and we say we want to look for things that are Arduino-ish, that have the Arduino in the tags, right? So these things all have Arduino in the tags, all right? Supposedly. Now, if we wanted to say we were interested in a Cortex M4 processor, all right? Does anything come up with Cortex M4? Yeah. So there we go. All right. So anyway, you can search for different things here. You know, maybe something that SparkFun designed and put up here. So here we go. So here's some SparkFun things, and these are open sourcey. Okay. So anyway, so you can search for stuff, and then also, now this may or may not work. Yeah. Let's try my last name because I've got, yeah. So because my first name is A-N-D-R-E, and that E has got an accent on it, which is Alt0233. So you got to do that. Maybe I'll change that just to make it simpler, because no one's going to know how to put that accent, that Alt0233 code to do that. Yeah, I'll probably fix that. But anyway, you can always search under just Lamoth, and then I'll also put Crash Course Electronics. By the time you get this, it'll work like that. So anyway, so that's it. So that's Circuit Maker. So get it installed, get it working, play around with it a little bit, and then in the next lecture, we're going to look at circuit boards themselves. I'm going to show you some actual circuit boards. I'm going to show you some stuffed circuit boards, some surface mount circuit boards, some through-hole circuit boards, some close-ups, just talk about a little bit so we have a little bit of language, even though I know you're supposed to read the chapter here, right? Chapter 5 here, assuming you've read that, but maybe you haven't read it all the way. But I want you to have that common language and actually see these things in my hands. And then after we get done with that, then we're going to go ahead and we are going to start designing. We're going to start with this magic wand. So this is going to be super awesome, and this tool is a lot of fun. And once we get done with this, I mean, you're going to be able to make just about, you know, anything you want that's relatively simple. You're probably not going to be able to make an Xbox, but you might be able to make a little video game console, or little things like that. So definitely be cool. All right. So I'll see you in the next video. Bye. All right, welcome back, and we're on the next lecture where we're going to talk about circuit boards some more. And we're going to actually take a look at them, and we're going to start digging into how they're constructed and some of the terminology and language to describe them, and just so you have some context for when we start doing the actual design, because otherwise you're just going to have no idea why we're doing any of this stuff. So what we're going to do is we're just going to jump into the deep end. We're going to kind of look, use the computer here, and we're going to go to the bench, and we're going to look at actual circuit boards. I'm going to hold them in my hand and show you different things. But first, let's sit on the computer for a few minutes here, and I'm just going to kind of go through some different things to kind of show you some stuff, so that when we go over to the bench and look at various things, you'll kind of have some idea what we're talking about. So first, you should have read chapter 5, so hopefully you did, inside of the book, especially on the PCB stuff. And then use Google and YouTube also, and just search under PCB design, things of that nature, so you can just get as much information as possible, because the most electrical engineers don't know a whole lot about printed circuit board design. And even myself included, even though I've been building them for 30 years or so, you kind of learn what you need to know to build them, and then over time you start to understand, oh, that's what this means and that's what this is, because you kind of leave it to the printed circuit board company to take care of things. So from an electrical engineer's point of view, we provide the design and these things called Gerber files, which I'm going to show you what that means, and then they build the circuit board. And of course, we know how the circuit board is made roughly, right? We know that it's got layers, and there's copper, and there's this, and there's that, but it's still something that it's a whole field unto itself, manufacturing circuit boards. So the more you know about it, the better. and it'll help you in your designs as well. It's kind of like if you're a programmer, if you know how a computer works, right, and you know how to program an assembly language and you know computer architecture, you're going to write better code because you're going to take advantage of the architecture of the computer and not just program it like it's this abstract thing. Same thing with circuit board design. Even though you're designing a circuit board based on your circuit, uh, you know, someone has to manufacture this. And the more you know about the manufacturing process, the easier and the lower the cost and the better the reliability of your circuit boards will be. So anyway, all right, so let's we're gonna kind of jump all around here and just kind of do this, you know, on the fly and see what happens. So the first thing is what's on the screen here. So what you're looking at here is a circuit, a product I developed a few years ago, and this is a medical video board for overlaying diagnostic medical information into a single screen so that eye surgeons could do eye surgery. All right, so that doesn't really matter, but what matters is it's a 4-layer board, and I wanted to show you this as an example because we've got it over there on the bench. And in this tool right now, so this is Proteus, so this is not Circuit Maker, but I designed in Proteus, so that's why I wanted to show you. So this is kind of what it looks like to me as I'm designing this thing, right? So this is you know, the actual circuit layout of the product. Now, here is the schematic of it, and you can see the schematic is very complicated, right? It's got these big, large chips here, and you know, hundreds and hundreds of signals all over the place. So this is not easy to develop this product, right? And all kinds of stuff. And then all this gets taken, and then chip by chip, part by part, I put it on the circuit board and I wire it up in a way that it's going to work electrically, and then also so that it's aesthetic, and then also so it's manufacturable. Now, so let's talk about what the whole circuit board is. So the circuit board, a printed circuit board is it's basically a substrate that the copper wires representing the traces in the circuit, right? So we've got this schematic here, and every one of these little wires, these are all these little lines or wires, and then in this case you see it goes to a signal called VBus29. This is called a net, N-E-T, net. So in modern circuit design, you won't see us run wires everywhere. Like for example, here I'm running wires to all these little devices, these connectors, these video connectors, right? And that's just to show the connection, and then I have the space to do it. But another way you can do it is you just kind of put a label on the net, and then everywhere that net, so VBus40, which you may or may not be able to see, VBus40, everywhere there's a VBus40, that means a wire needs to be ran there. They're all the same net, okay? So when we take this schematic design and we bring it into the PCB layout, what's going to happen is the computer is going to have hundreds or thousands of nets that all need to be connected by you or the computer. Someone's got to connect these. So every one of these little wires you see, these little red wires and blue wires, are these various nets. And I've connected all of them. Now, you'll also see a little bit of residue. You see these green lines here? And different tools use different things to represent this. This is called the rat's nest. And what this is, it shows every single connection. And now, even though these things are connected, the tool thinks they're not connected. And this is due to bugs in these tools. These tools are not, you know, they have flaws in them. And if you don't place a wire perfectly or get it, you know, dead center on something, sometimes the design rule checker will not realize that you actually have the wire connected. So that's just an annoyance. All right. Now, so the PCB is made on something. All right, and it's layers of copper, and these layers of copper are in 3 dimensions, right? So they're layered. All right, so now take a look at this. So take a look here. And so if you just search into Google PCB layers explained or PCB layers stack up, things like that, you'll be able to see these things. So what I want to show you is this kind of search right here, and this is nice because it shows a few different things here. And we can take a look at this, for example. Let me make this a little bit bigger for you. So what this is showing a stack. This is one printed circuit board. It's a cross section of it, and it's showing you the stack of all the different layers. So now here's a copper layer. So this is the top copper layer right here. All right, and then you can see inside of it, it has other layers inside of it. And you know, here's another layer right here. This is a ground layer, right? And then this is called mid layer 1, mid layer 2, mid layer 3, mid layer 4, and here's the bottom layer. So now we want to run wires to build this circuit board, right? So that we connect all these nets, these hundreds of nets that we have to connect. Now, we can't just connect them in a two-dimensional flat grid because lines would intersect and it all be shorted out. So we have to create multiple layers in 3 dimensions. And typically, most modern circuit boards have, ready for this, 30 layers or more. Some have 60 layers. So a motherboard might have 30 to 60 layers, if you can believe that. So it's pretty nightmarish. So very, very advanced tools are used to design those things. Most stuff that you'll make or hobbyists make have 2 layers, maybe 4 layers, maybe 6 layers. All right, and so they're much simpler. But the point is typically, say we start off with a 2-layer board, we'd have a layer on top and a layer on bottom. So all the stuff in the middle we would not have. So we would only be able to put traces on the top and on the bottom. So if you go get an old circuit board out of something from, say, the 60s or the 70s, you'll see that typically everything is on one side, and it's usually drawn. It looks like it was drawn with a pencil or a pen, not a computer. There's not right angles and 45-degree angles. Everything's kind of like serpentine lines and free flowing. It'll just have a layer on top, typically, and maybe it'll have a layer on bottom, and that'll be it. So now as time went on, we can easily manufacture these boards. So now, so what are these things made out of? All right, so the material that each one of these layers is made out of is typically it's a fiberglass material. It can be other things, and it's impregnated with a resin. So it's like a fabric. It's like literally a fabric. It's flexible. It's a fabric, and it's impregnated with resin. So it's like fiberglass. That's what fiberglass is, right? It's glass impregnated with a resin. And so each one of these layers, and now they have different names. So these layers, and again, depending on where you look, you'll see different layers, but it'll be called core or substrate, and that's the material that the circuit board is primarily made out of, right? And that core material or substrate material, depending on where you look at it, has some names, and these names are like FR1, FR2, FR3, FR4, FR5, and this stands for this has to do with their mechanical properties and their thermal properties, this FR material. So that's kind of the core. That's what the majority of the board is made out of. Now, above and below each one of these core layers is what's called this pre-preg, and this is pre-impregnated. And this is, again, just a fiberglass with a resin inside of it. So again, we have to layer these things up, all right? And so this is how they layer the boards up, all right? So if we go to, and I've got a couple searches here. So if you go to a printed circuit board and search in Wikipedia, all right, this is, you can kind of scroll through this, and this has got some interesting information. But what I want to show you is, and give me a second here. Here we are. All right. So these are common substrates, and these are used for to make that core or the substrate of the printed circuit board. So this is what it's mainly made out of, right? And then there's these copper layers that are etched on top of these things. So they start with like a copper foil, and then they etch things away, right? But anyway, so these FR, this stands for flame retardant or you know, flame retardation, how much it's not going to start on fire kind of thing, right? So it's flame retardant 2, flame retardant 4, but also it has to do with the mechanical properties of it. So now typically most boards that you'll get from a hobby PCB shop is you can select FR4, that's the most common, and it's fairly cheap. Now, if you go down to FR2, for example, this phenolic paper, all right, this is really cheap. So this is literally made out of paper, paper impregnated with a resin. So this is super cheap. If you find like some old toys or Chinese toys, you'll see they're made out of this. So this is super cheap. Now FR4 is woven fiberglass with an epoxy resin. So this is actual fiberglass. So this is really nice. It's very, very strong. It can be flexed and all that, and it can take a pretty good temperature. All right. And there's some of its properties. And then, of course, you can go to aluminum also, all right, or metal core board. They have lots of different things for that. Now, there's some other materials here which go up the scale here. So, for example, FR3, FR5, woven fiberglass, high strength at high temperature. So why you might want this FR5 material is, I want this board to stay strong even at a high temperature and say 170 degrees Celsius, which is very, very hot. All right, and then some of these other materials here. So basically these days, anything you want can be made if you need it. But typically you're going to say, I want FR4, flame retardant level 4, and that's going to give you good mechanical properties, and it's cheap, and it's fiberglass, and that's that. All right, so going back to our picture here, so this is what these boards look like. All right, so now if we type in here PCB 2-layer, PCB 2-layer, and inside of my book in chapter 5, this material is here also somewhat, so you can see some of these things. So here's like a 2-layer board. So let's take a look at this. All right, and you always take your life in your hands. All right, well, that's not working the way I want it to. Let me make this bigger. I'm just trying to make this bigger. Okay, there we go. All right, so here's a 2-layer board, and so let's see what's going on here. So in this case right here, we've got now this is okay. So this board is actually not a 2-layer board. So this is a 4-layer board right here. And what's going on here is it's got a top layer and it's got a bottom layer, but it's got 2 inner layers that are power layers. And you can see ground and 3.3 volts. So here's another layer right here that just has power. So a lot of times when you do a 4-layer board, top and bottom will be signal. Then the 2 inner layers, you'll make those power and ground so that you can easily get to them, because you've got all these ICs all over the board. And then if you want to run power, you got to run it around all the signals. It becomes difficult. So what you do is in 3 dimensions, you put power and ground on those inner layers, and then you can get to them very easily. So that's what this is showing right here. So a top layer, a bottom layer, and 2 inner layers. And then you can see how this is constructed. So it's got core material on the top, core material on the bottom, and then this pre-preg material here in the middle. So it's much thinner. And you can also look, the thickness in this particular version is 0.264 millimeters top and bottom for the core material or the substrate. That's our FR4. And then we've got only 0.1 millimeter, very, very thin in this pre-preg section to make this thin. Now, let's talk about thickness of the whole PCB. So these 30 or 60 layer PCBs, you're thinking, wow, are they like this thick? Are they like an inch thick? No, they're very thin. So they can make these layers as thin as you want them. And these days, anything you want can be done. Typically, so now there's some typical sizes for circuit boards. Most of the time, a default is about 62 or 63 thousandths of an inch. All right, so if you go to a PCB shop, it'll say 0.062, 0.063. That's kind of the typical thickness of the whole thing. Then what they'll do is they'll kind of back up and figure out, well, if you've got a 2-layer board or a 4-layer board or a 6 or an 8-layer board, and it's usually always a multiple of 2, because if you put something on top, you put it on bottom to keep it symmetrical. But no matter what how many layers the board is, they'll make it fit inside of that thickness that you give it. Now, if you just put too many layers, they might have to make that thickness a little bigger. So if you do a 2-layer board, it'll still be 63 thousandths of an inch thick. If you say a 4-layer, it'll be 63 thousandths. If you say an 8-layer, it'll be 63 thousandths, unless you wanted a different size. Now, if you say 60-layer, they may be like, we just can't fit it into 63 thousandths. It's got to be 80 thousandths, all right? But you can make it whatever size you want. Now, why would you make it different sizes? Well, one, you just may want some mechanical strength. You may want that circuit board very strong. Maybe it's going to flex. Maybe it's in an F-16 fighter or an F-22 Raptor or something, right? That's one thing. Two, it's for thermal reasons. The thicker the board is, right, the more thermal mass it's going to have, so it's going to be able to dissipate heat better, right? So that may be another reason for it. So anyway, when you're making these boards, just I would suggest to start off with the default thickness of the 62, 63 thousandths. Depending on the manufacturer, they may fudge that a little bit, and just kind of start there. All right, so let's back up here and back up here. Okay, now let's take a look some of these. As a matter of fact, I want you to see, let's go back to this one actually. Oh boy, look at this board right here. How crazy is that? So look at this. So this has got all these different layers, and now what are these things going through here, right? So I want to talk about that stuff. Let's talk about that. And this one may have some arrows. Yes, this is good. So let's see, if I click on this, you always take your life in your hands when you click on things. Okay, that's not where I want to go. So let's try view image. Is that going to help us? And let me see if I can make this bigger without breaking the computer. Okay, so we've got this layer stack up right here. So let's take a look. What do we got? We got a top layer. So here's our top layer. Here's our copper. And now, how is this put on here? How this works is they put a copper foil of a certain thickness. They put a copper foil on here, and then they etch away what you don't want, with an acid or some other, technique. So they etch it away. So that's how, so they don't draw the copper on here. They actually start off with a solid sheet and then they etch it away, right? And that's inside of my book. You can see there's solid copper material and then it's etched away. All right, then we've got this ground plane right here, and then we've got another layer here. Look at that layer there. Then we've got another core material here. Then we got another layer here. Then we got another layer here, which is putting 3.3 volts, and then we got a bottom layer. So how many layers is this stack? Okay, and you call it a stack, kind of like you would call a networking stack, same kind of thing. So we got the top layer. There's one. We got this layer 2, 3, 4, 5, 6. So this is a 6-layer stack. So this is a nice stack. So with 6 layers, you can pretty much do anything. So you basically, in this one, we've got 4 signal layers. We got the top layer, the bottom layer, then we got these 2 mid layers that we can put signals on. Then we got a ground layer, and we got this 3.3 volt layer. Now, no one said you have to do signals or ground or power. You do whatever you want. But typically this is how it's done, and the reason why it's done this way is for ease of routing and also for electromagnetic interference, things of that nature, to keep the board quiet. So you put the power on the inside and then you route down to it. Now, so what are these things? So in 3D, this is obviously a cross section. So these things are circular to begin with. These are called vias, V-I-A, vias, all right, vias. And what vias do is they allow you to go in 3D from one layer down to another layer. All right, down to another layer. And so that's how we can get signals from one layer to another without crossing. So say, for example, see the signal right here? And we got this signal right here. Say, if we look at this right here, say I need this signal and I need this signal to go over here. Well, I can't just run it here. I'd short into this. So what I do is I via down and I go around the thing in 3 dimensions. So you got to think everything in 3D, all right? So going back to this guy right here, you can see we've got these multiple layers. Now, so first let me do one thing. So you see all these little circles here? These are design rule violations. Not really violations, but the way the design rules are set, it's violating the default rules, all right? So I've set these, a few rules that I cared about. You can set all these design rules. And what design rules are is when you're doing the circuit layout, 2 things. One, your manufacturer may say, hey, you can't have holes that are smaller than this diameter. 2, you can't have traces that are this close to each other. 3, 4, 5, 6. There could be hundreds of rules, right? So I know what rules that my manufacturers need to take into consideration. So I may set up the tool to show me those rule violations, or I might not because I'm just lazy and don't feel like it. Now, in this case, there are so many different places where I have to set rules. I just let it violate it because I can see that these are all okay. So anyway, we're going to turn off the rule system right now, if I can find it. So I've been using Circuit Maker a lot. So for you guys, so here we go, enable design rule checking, and watch this. Boom. Now they all disappear. Okay. Okay, good. Now let's turn off the rat's nest. That's that little green stuff, right? Let's turn off the rat's nest, and now that's gone. All right, so now we still see there's these layers here, right, which makes this really hard to understand what's going on. So now what I'm going to do is I'm going to turn off a bunch of stuff. So I'm going to turn off the top silk layer. Look at that. I'm going to turn off the bottom silk layer. I'm going to turn off a lot of these things here so we don't see them. All right, and these don't matter here. And all right, and I'm going to turn off the bottom. Okay, so now all that's on right now is the top copper. So now you can see there's the top copper layer. That's it. That's all my traces for the top copper. That's where the chips mount onto. These are surface mount chips here and here and here, right? And then these things are through hole. These go through holes. That's why they're called through holes, right? And we're going to look at all that in detail in a little bit. Now, so look at the vias. There's not that many vias. So if you look at this design, every place you see one of these little holes, this is the representation of a via. And this is what allows me to go down through the circuit board and get to the other layer, whatever layer I want to. Now this board right here is a 4-layer board. It ended up being. So I had 4 layers, this and power layers. Now, I'm not sure why. Oh yeah, there we go. So here's, yeah, as a matter of fact, so now we've got all the layers, just the top layer. So now we have just the top layer. Now here is one of my power layers. It's just somehow the colors have changed into these really ugly putrid colors. So let me turn off the top copper. So this is one of my inner layer 1. So this is an actual power layer. So see, this has got my 3.3 and my 5 volts and my 1.8 volts. There's a lot of different voltages in this design. So that's a power layer. And then this other layer, See how it just shows it completely solid like that? See, that's a ground layer. So I can get ground anywhere I want there. So that's a ground layer. All right. So anyway, that's the top layer. And everywhere you see these little holes, those are vias going to one of those other layers, either power or ground or to the bottom layer. And that's how I'm routing all those nets that need to be routed, right? But there's not that many of them. And the reason why is because I did this manually. And also this looks very pretty. So if you're a circuit board designer, you'll look at this and say, oh, that's a very pretty, design. And if you let the auto router do it, typically it will not be this pretty. It'll be kind of ugly. So some people don't use auto routers. I rarely use them unless it's a simple board that I don't care about. But in something high speed like this board works up in the like half gigahertz range or even gigahertz range. So you kind of have to manually route it. All right, so not a lot of vias, which is good. All right, so nice and clean. Now let's turn on the bottom layer and let's take a look at that. Okay, so there's the bottom layer. So the bottom layer has, look at that, very little. So I was able to, and I'm sorry it's hard to see in this blue, but I was able to mostly route everything on that top layer, plus the power layers, and that's was my goal to do that, all right, in this particular thing. So now, okay, so now we've got our PCB. So again, we design our schematic, we get all this stuff. It's full of a bunch of chips and parts and components, and then all these nets. Then we have to lay this thing out by dragging the parts onto here, and we're going to go over this in gruesome detail. All right. And then we, layer by layer, we do this. Now we have to decide how many layers are we going to do. Are we going to do 2 layers? Are we going to do 4 layers? This comes from experience. If it's a simple board, you start with 2 layers. If it's a fairly complicated board, here's the thing. The cost to go to 4, so usually the cost to go to each new set of layers. So if you start off with 2 layers, let's say that's $1 a board. 4 layers will be $2 a board. 6 layers won't be $3 a board. It's only going to be, a fraction now because we're only talking about 30% more copper, right? And so on. So as you add layers, the cost starts kind of decreasing, the acceleration of the cost decreases, right? But you get all these layers. So what you have to decide is, if I want to try and stuff something into 2 layers, is it worth the time? Is it worth your time? So say if you spend 100 hours laying out a board, or 50 hours laying out a board, or 200 hours laying out a board, which is very common when you're doing a complex board, especially if you manually route it. And a lot of engineers will say, oh, I can do that in a day. But it's not true. It may take a day to get the most of it done, but then they spend a week tweaking it. So it took 40 hours or 80 hours or 100 hours, right? So anyway, when you're deciding what layer stack to use, with your simple board, start off with 2, but you may just want to start off with 4 layers and then have a top layer and a bottom layer for signal, and then 2 layers for power, or you might want to make the 2 inner layers for signal also, and maybe put power on them also, just to make it easier for you to route, all right? And then there's all things about noise and stuff like that. We'll talk about that a little bit, but it's inside of my book also, why you pick the things that you pick. And again, this is a big subject, but for now, you can also look online and look up 2-layer stack, 4-layer stack, 6-layer stack. What should I do? And there'll be lots of references that'll tell you. All right. So, okay. So now let's. So we're looking at this. So now we've kind of got layer stack. Now let's talk about. So we've designed the printed circuit board, and when we use Circuit Maker, we're going to start off with a really simple circuit, so you can kind of see this whole process. Obviously, when you're all done, what do I do now? I have no idea what I got here. Okay, so you've got to export this in some kind of file format so that this thing can be manufactured. All right, so get ready for this. So the file format is called Gerber files. Gerber, G-E-R-B-E-R, like the baby food if in the United States. I don't know if Gerber is worldwide, but there's a little food, baby food called Gerber, Gerber baby. Anyway, Gerber files. So here's an interesting thing. So if we look up, and we've got giant Google here. Let's make that about 125%. I like that. Okay, so Gerber file format, and we could say origin. So yeah, and here it is. I've already looked this up and got it here for you. So Gerber files. So this was to manufacture a circuit board, you need some kind of file format. Now, we've been building circuit boards for a long, long time. All right. Honestly, I wonder if we've been building them since probably since the early 1900s, some kind of circuit boards, right? Something, whether they're manually done or whatever. But by the 50s or 60s, obviously we got pretty good at doing this stuff. And then I believe by the 80s, and if you read through this, yeah, so Gerber, so in 1980, so it's 36 years ago, that's a little bit incorrect right there, it's 37. But anyway, Gerber files, well, it's August, so it is correct. So Gerber files were invented by a company, Gerber, and let's see here, electronic design. I believe the name of the company was Gerber, if you read through here. But the point of it is, it was a company in the 80s who came up and developed by UCAMCO, initially by Gerber Systems, Gerber Systems Corporation. And this is really interesting. This is where this comes from. Where does this word come from? You know, it's just so, you know, you want to know. So a Gerber company, Gerber Systems Corp, developed this, and this UCAMCO, whatever. This was 36 years ago. And what was this? So back then, before we had all this circuit stuff, right, before this was a big deal, we still had mechanical stuff, right? We're building cars and building machines and building planes and all this. And we had kind of numerically controlled machines that would drill holes and lathes and CNCs and all that kind of stuff. And they used a kind of a control format that was in 2 dimensions that would move tools around and drill holes and that kind of thing, right? So that's where this Gerber file is derived from. So it's derived from kind of plotter controls, which are based on these what are called G codes, which is a language which allows you to describe something in 2 dimensions to draw, right? So that's what this Gerber file format is based on. So it's a file format, just like anything, but it's designed to represent these 2-dimensional vector images, plus drilling, the size of the holes, all kinds of stuff. Now, by today, we're here with these extended, so these are the 2 major formats right now, this RS-274D and then this 274X. All right, so this is revoked. I didn't know it was revoked. But anyway, the majority of tools, you can output this RS-274X format. All right, and this is the latest format. And when you do this, what happens is this. So what happens is this. You take your circuit board, all right, and now, so if we turn all the layers back on, and of course we're going to do this when we get to Circuit Maker. Obviously, I'm going to show you how to do this on Circuit Maker. When you have your thing all laid out and it's all ready to go. So this is a completely done circuit. So this is ready for manufacturing, okay? So now I'm ready here and I want to export this. So now, depending on the tool, in this particular tool, and again, you don't really care because we're not going to use this tool, but you see I go up here to output, and then I say generate Gerber file, generate pick and place file, generate all these things. There's all these different kinds of files, and you could read about what all these things mean, but really the ones that we care about are the Gerber file and the drill file, which says where to drill the holes and the size of the holes. But in this tool, it's embedded in the Gerber file generation. So this one actually generates the drill file and the Gerber file in one. Now, there's one other file that's important depending on the tool. It's the pick and place file. And what that is when you send this to be manufactured, you generate Gerber files. And I'm going to show them to you right now in a couple seconds. But say if you want to manufacture the board and have robots build this thing at a contract manufacturer in China or the United States or wherever you may want it, something needs to know where all the chips go, right? So there's what's called a pick and place file. You've heard this word before, pick and place machine. And we should go look on YouTube. These things are crazy. So after the circuit board is made, so one company builds the circuit board typically. They're really good at building circuit boards, and they've got these big manufacturing lines that just build circuit boards. So you get the circuit boards, you build 10, 100, 1,000, a million of them, whatever. Now they ship them over to another company that has these pick and place machines, all right? And again, you can YouTube this pick and place machine, and we'll do it in just a second. And then what they do is these pick and place machines are loaded up with all the components. So someone buys, a buyer buys all the components for your board. And they put them on reels and trays and all kinds of funny little things so that robots can grab these things and then place them in your board at very high speed. So the pick and place file is a file that has instructions of where the component is, its orientation and position, so that a robotic hand can grab it from some coordinate system, right, and then move it to a position in that coordinate system at a certain depth and this and that, and what does it look like so I can grab it and all those things so that it can be placed. Okay, so we'll take a look at that in a second. So Gerber file, pick and place file, you got to generate those. Now, when you generate them, depending on what tool what tool you're dealing with, okay, they will have different names. All right, so now this tool, the Proteus tool that I'm showing you right now, and again, we're going to use Circuit Maker, but the Proteus tool has beautifully sane names. Look at these names. Top copper, top silk, inner one, inner two, those are the inner layers. Bottom resist, bottom copper, top SMT paste, that's the surface mount paste. So when you have surface mount, that's a layer that shows you where the paste goes, the solder paste, so you can put surface mount parts on, which we've talked about before. The solder resist, these layers are a mask so that when the boards are soldered, they use a wave soldering that protects the board so that only places where solder goes get solder on it. That's what the solder masks or solder resist layers. But they're in English. You can read what these things are. One of my biggest pet peeves about these other tools, Circuit Maker included, is they have these file names which have these layer encoded names which are all over the map. And I actually printed them out someplace, which I've kept here for years. It's over here someplace. And so I can figure out what's the top copper layer. And it's got a weird acronym for it and file name. So you got to figure out what your tool outputs, and then you got to look up what these different things are. But in here, they're just in English. So what I'm going to do is I'm going to drag this over to another screen, and I'm just going to drag these layers here. Okay, so take a look at this. So here's the top copper layer, which is already up here. So here's top copper. Now, the one thing I want you to notice, so here's the top copper layer, right? Now look back at the tool, all right? And then we're going to go here, and let me turn this off, and we'll go top copper. All right, so now you'll notice that it looks very similar to this. So there's that, and now this tool that I'm using, which just disappeared, so this tool that I'm using, let me back out a little bit. There we go. So this is the top copper layer. Now, what's all this filled material here? So now, before I finished this design, I filled each layer with copper or ground. So basically, every place that you see black, I filled with copper. And this is called a copper pour or copper fill. And it's good for noise, and it's good for a thermal reason, and it also creates what's called a Faraday shield so that EMI, electromagnetic interference or radiation, can't get out of the boards. So this particular version of the design, that didn't happen yet. So when I finally finished, I created these copper pores, and that's why you're seeing all the solidness here. But they won't touch anywhere. So notice that it never touches anywhere unless it's a ground. So see these little pieces coming off here? These are ground. So apparently these components, whatever they are, these are probably capacitors. And that's where they're grounded. So if you move around here, every place there's a ground, see that? See this one right here? It's connected there, it's connected there. So this plane becomes a ground plane. And so all the planes in my design, and this design right here, are all grounded. So they're all grounded so I can get to them. Because if I didn't do that, for example, say like this ground right here, this ground right here, this ground right here. If I had a ground on the inner layers only, I'd have to put a via, punch the via down, and then go to the layer, the ground layer, in the stack up of the board to get to ground. So this is a much better way to do this, all right? So I ground fill everything, and it helps with noise, and it's also very good thermally. Okay, all right, so that's the top layer. Now let's look at the bottom layer. So I'm going to get bottom copper, and I drag it over here. All right, now this tool right here that I'm using, so this is a Gerber viewer. Now many tools, so many CAD programs like this have a built-in Gerber viewer so that you can look at the layers of your Gerber file. The whole thing is, though, they're not in the Gerber file display business. They're in the circuit design and layout business. So when they make the Gerber viewer, it's not very good. It's usually kind of cheap, right, and cheesy. So you got to go to a company that's in the Gerber file business that manufactures stuff, and they make a tool. Gerber viewers are very expensive, a good one. But there's this company, Pentalogic, which I've talked about before, which is this one right here. And let me see here, about. Yeah, so this is Pentalogix, P-E-N-T-A, Logix.com. This is a free edition of what's called ViewMate, and allows you to view your Gerber files. Now, there's ViewMate and then ViewMate Deluxe, where you can actually edit them in this tool. And that's what all this crazy stuff is. So you can actually edit this. Now, why would you want to do that? We've talked about this. You're done with your circuit. It's all done. Everything's done. And you get ready to go to manufacturing. You go, oh my God, I messed up this one trace. Do you want to go back into the circuit design? Do you want to re-export the Gerber files? No, because you can introduce more errors. All I want to do is take this trace and do something with it. And this Gerber tool will allow you to do that. All right, but anyway, here's the bottom layer. Now, if we go look at the circuit, so let's switch to the bottom layer. So here's what the bottom copper looks like. And again, forgive the blue color here. All right, so if you can kind of see that, hopefully you can see it. So it's got this kind of little shape here, this little thingy, and then some thingies over here. Now let's go take a look at it. That's a technical term, but it looks the same, right? And again, it's all filled. And you see I can fill everywhere I want. Now look at all these mechanicals. These are all the inputs. See how they have those nice grounds around them? Ground, and then they're connected to ground because one end is connected to ground. Most of these video inputs and video outputs, through-hole components, that's what these represent, are grounded. All right, so that's that layer. Now, let's go to an inner layer. So let's go to inner one. And this is one of our power layers. So here you can see the power tree. So this is the 3 volt and 5 volt and 1.8 volt power tree. And so one of these is 3 volts, one of these is 5 volts, and this is how I route power to all those chips. And then I via down or via up from the top and bottom layer. That's what's going on here, right? That's that inner layer. And then here's this inner layer too, which is just a ground layer, just another ground layer. You can see it's just all ground, okay? All ground. These take some time to understand what you're looking at. And, you know, if you're confused right now, it's okay. It took me some time too. I would look at these and go, what am I looking at, right? But the more you see them, the more you'll understand. Now, let's take a look at top silk screen. This is easy enough to understand. So this is for the printing on the board. So on the top and the bottom of the board, only on the top and bottom, they paint on text. And this text has all the reference designators for each one of the components, so you can tell what the things are, and then just the outlines of them, and just, you know, information and whatnot. And that's called the silk screen, right? Or the overlay, or whatever the tool wants to call it, depending if you're in the United States, if you're in the Middle East, if you're in Europe, if you're in UK, if you're in Australia, depending on what tool, they call things slightly differently. All right, so you got to be careful of that. All right, so that's the top silk screen. I don't think this thing has a bottom, so yeah, I didn't do bottom because I didn't need it. Now, let me show you the SMT paste mask. So what is going on here? Well, if you look at this, and then if you go back to the tool, right, you can kind of put this together in your mind. Let's go, so here, look at this right here, and now let's go to the tool, and let's go to the top layer, only the top layer, and let's add the top silk, just so you have some reference here. Help me, where's top silk? There it is. Okay. So look at these chips. So here's a big chip, Athena and Zeus and Ares, right? And this mini USB chip. These are all surface mount chips. So now, if I want to manufacture this, what's going to happen is, now here's something else I got to talk about. What's going to happen is someone has to solder all these chips down. Now, we don't want people doing this. It would take an eternity. We want machines doing it. So what they do is this. They take a solid piece of metal, usually made out of steel, all right, very thin steel, solid piece. Imagine putting it on top of the circuit board. Then imagine cutting out little teeny tiny holes everywhere one of these little pads is sitting. So see this little pad right here on pin 50, pin 40, all these pads. Makes a little hole. It's usually cut with a laser, and then basically you can overlay this on top of it. And then what you're left, so it's a stencil, and what you're left with is a place to put all the solder. So then what happens is this stencil, right, is laid literally on top of the circuit board. It's latched down carefully and via registration, so it's exactly in the same place, because we're talking about thousandths of an inch accuracy. It has to be laid down. It's locked down. Then solder paste is squirted on the edge of the board. Then a Ouija just goes over the board, back and forth, and then it puts the solder paste through the stencil, and it ends up on all of these little pads. Ends up on all these little pads of all these little components. Then it's removed. The solder stencil is removed, and now what's left is the paste on the board, right? Now what happens is a robot grabs every one of the little surface mount parts and puts it on there. Brrr, thousands of them, blah, 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 does all that, right? Then it's put in an oven and cooked and soldered. And this process may happen a couple times. You may have the top of the board, the bottom of the board. You may have some through-hole soldering. It's a very complicated process. That's why you got to watch videos to really understand. So when we go back here, that's what this is. This is the solder paste mask. This is where I want solder. Paste, solder paste. This is for the surface mount parts. This is where solder paste goes for the surface mount. So what's going to happen is this is used to build a solder stencil. So basically everywhere you see green, a laser is going to cut through this solid piece of steel, very thin steel, right? You can do it with aluminum too, but the steel is much better. And it's very thin. And it cuts all these little holes out, and then you got that, and that's what you use for your product. Now let me show you. All right, and again, it's always nice to see something. So we'll say solder paste stencil. And we should, here we go, exactly, can we get some images here? Here we go. And so, yeah, so I mean, basically, this is what we're talking about. So this thing is cut out like this, and then it's put on top of the board. Then a Ouija solder paste is squirted on the board, then a Ouija goes by, and then it ends up on all these things. Then the solder stencil is removed, right? No, here he is right here. That's great. And you know, SparkFun is a great website. So is Adafruit. They have lots of pictures of these kind of things. And here's someone applying solder. He's got the stencil down. Notice it's locked in there. And then he's going to Ouija the whole thing on there. All right. And then after that's done, then now they may put these by hand. I hope they're not. But a machine will then go and pick and place all these parts. Okay. So let's see if we see anything else here that's interesting. And then here's, you know, now here's something. So this is after this has been, look at that. So that's that solder paste on there. Very carefully, then someone's got to put all these parts on here, or a robot's got to put them. Then it's cooked in an oven. And here's another example. There you go. So after the solder paste is put on there, someone is manually grabbing these parts one by one and putting them on here. This looks, I've seen this. This is a, yeah, I think this is some kind of circular LED thing, some kind of toy that you can make to experiment and learn surface mount soldering. Now, this is, obviously someone did this by hand, right? This is really bad. Someone did it, but you know, this is okay if you're doing it by hand. Hey, and you don't have a stencil, that's okay. And then here you go with the squeegee thing again. When you pull this off, it's very, very nice. But this is messy work. Another thing, solder is toxic. Please wear gloves. This is really bad. You should have some plastic gloves on, some latex gloves, something like that. You don't want this in your fingers. It ends up in your mouth. All right. And over time, you'll be eating a lot of solder. All right. And if it's got lead in it, not a good thing. All right. So please wear gloves when you use this stuff because it is toxic. Okay. So that's what happens there. Now, so we've talked about the, and again, here's the company, Pentalogix with an X, pentalogix.com. Here's where you can get that Gerber viewer. And like I said, there are very few really good Gerber viewers. This company, Pentalogix, makes one of the best, and it's an editor, and it's cheap. Very hard to find these things. They're very expensive. This is a great company. They also make circuit boards. I've told you about this before. They also do manufacturing, and they're really smart people and cool guys. So you can call them up and talk to them and ask questions, and they'll educate you if you need them to. So they have all these different things here, and I don't work for them, but I use their stuff once in a while. So let's see here. And I believe if we go here on CAD CAM software, let's go to learn more. You know, websites change every day these days. Yeah, here we go. So ViewMate Deluxe. If you're going to get real serious, I suggest you buy this thing because it's awesome. ViewMate Deluxe. That's all you need. Now, you can see some of these other tools. These CAD tools or EDA, electronic design tools, $10,000, $1,500. These things are not cheap, $1,200. This is expensive stuff. But this is very cheap, and you can get a free version of this. I think if you just click here, I'm trying to figure it out. If you click here, I think you can get the free download from here. And 95 computer locked, ViewMate Deluxe. You got to look around on the website. You got to look around on the website. I don't want to sit here and do it while you're watching, but it's on here someplace to get the free evaluation version. All right. So anyway, so that's one of the things that I suggest, and this tool works really well and allows you to edit Gerber files if you need it. Of course, you don't have to pay for it if you're never going to edit it. If you just want to view it, just download the free version of it. Okay. All right. So let's see. What else have we need to talk about before we start looking at the circuit boards again? So let's go back. Let's go back here, not to this tool. Let's go back to this view here, and let's see. Yeah. Okay, so now what I want to talk about here is actually this is pretty good. So let's look at this, and let me see if I can just view the image. Good. Okay, so now let's talk about these vias again, because this is a little bit confusing for a lot of people. So So the via is used to go from one layer to another when you need to connect something. So you're like, well, how do I know to use a via? Well, you don't. So as you design, you're going to get the hang of this. So you can use the auto router of the tool to auto route the whole circuit, and then it turns it into a bloodbath, or it does a good job depending if it's a $500 auto router or a $50,000 auto router, right? So a lot of times when you're starting out, you want to route things yourself so you understand why to position things, where to orient your chips. For example, if you've got a big data bus someplace with a bunch of signals that needs to go into some other chip with the same signals, you want to rotate the chips in a way that they're right next to each other, right? You don't want to put objects in the way so that you have to route around. You're going to learn all this. It's like laying down freeways. It literally is like laying down freeways. If you were a city planner, okay, except you have to think in 3D. So, and when freeways all hit, you have all these overpasses and underpasses. Same thing here, but instead of just putting the road over something, we create another layer and we work on the layer. So it's like a 3D road system. Now, let's talk about these vias a second, because I want you to know what these different terms are. All right, so when you have a via that goes all the way from the top and the bottom, or from the outside layers, top and bottom, all the way through all the layers, that's a normal via. So it's gone from the top all the way to the bottom. All right, now, in this case, this via touched this layer and it touched this layer, but it goes all the way through. All right, so that's a normal via. Now, these two vias right here have names. They're special kinds of vias. So now, this via right here, okay, it goes from one layer to this other layer. All right, so I wanted to go from this layer to this ground layer. So I just went, through here. So one side is exposed, one side is hidden. All right, inside of here. All right, so in this case right here, this is called a blind via. All right, so it's called a blind via because you can't see the other side. You're blind to it. All right, so that's a blind via. So whenever it goes from the top or the bottom to an internal layer, that's called a blind via. Now, this via right here, so this is totally internal in the board. So in this case, I had signal layer 1 and signal layer 2, and I needed to connect two nets from layer to layer, from this layer to this layer. Now remember, the yellow represents copper. It's a cross section. This crosshatch stuff represents material, and so does the white stuff. All right, so here, this number 2, right? This is a hidden via. It's completely hidden. I can't see it. The problem with this is this. When you're doing circuit board design and you have a normal via, it goes from the top to the bottom. I can see it. I can take the board and I can flip it over. There's the via. Flip it over. There's the via, right? I can check continuity. It's working. The via is working. When I've got this via, I can see one side of it, but the other side is hidden, or it's blind, right? It's inside. So I can see this part of it, but I can't really tell if it goes in here unless that signal goes someplace else that I can get to. So that right there is a little bit harder to debug. Finally, this completely hidden via that's inside of the circuit board, right? I can't tell anything. It's impregnated inside there. So if there was a mistake in manufacturing, I won't know. So if I have a circuit going this way and a circuit going this way on two different layers, right, on two different layers, and I want to via through them in the middle of the board, I'm going to use this hidden via right here, but I won't know if it works unless it works, right? So the problem is the more that you make more complex boards and you have vias all inside and these kind of special vias here, which are a little bit more expensive depending on who's manufacturing the board, it increases the probability that something's going to be wrong with the board, right? Because it's more complex. So that's why starting off, if you can just have a top layer and a bottom layer, that's it. That's what you want to do because then all your vias go straight through. Also, you can actually manufacture these boards at your house. So if you remember, we had that kind of copper clad. So let's see, homemade copper PCB. Okay, let's go to images here. All right, so here's a perfect example. So let's see here. Let me just scooch around here a little bit here. Okay, any of these really will do. But in this case, so take a look at this right here. So there's no copper on top. There's only copper on the bottom because you can't see any traces on top. So like, see this board right here? So what happened here is he etched away all the extra copper, and you do this with chemicals, and it's really messy and disgusting and dangerous. And then he drilled the holes through here. Okay, here's another one. He just drilled the holes through here, and just with a drill, right through. So you didn't need to put any vias. But now let's say that you wanted to get a little fancy. All right. And say this board right here, this, and I don't know if this is a homemade one, it looks like it is. and maybe it's got two sides. So it's got a top side and a bottom side. And if you want to get a signal through the top and the bottom, now you don't have a PCB manufacturing plant, right? Now what they do is they punch a little lug through there, and they solder it, and they do a bunch of different things and steps to make that electrical connection. But you can't really do that. So what you do is this. So you take the top, you take the bottom, you've got the circuit traces, and then what people will typically do is they'll take a little piece of wire and they'll put the wire through the drill hole, right? So you're going to kind of make a via. You'll put the wire through the drill hole, you'll solder it to the top, you'll solder it to the bottom, you'll kind of clip it, and that's how you'll make the connection in 3D. So let's go to our handy dandy drawing program here real quick, which we haven't used in a bit. So let's see if I can still draw. All right, so let's say that this is the top layer here. So here's the top layer. All right, there's the top layer. All right, and well, in fact, let's just, you know what? Let's do this like this, because this is really what's going on. So here is, if we make the circuit board ourselves, there's only one substrate. That is a horrible rectangle, sorry, but okay. So this is our substrate here, okay, which is fiberglass also, even when you do it yourself. Okay, so there's that. So there's our substrate, and then this comes with the top and the bottom is covered in copper. Okay, and then on the bottom also is covered with copper. All right. Now we etch this away. So I'm gonna show the top here. So we've etched something away, and then say here's, you know, a circuit trace. Okay, so there's a circuit trace, just like that. Horrible. Okay, so there's a circuit trace, and then let's say right here is where we're making this artificial via. Now, let's we'll draw the bottom in yellow. So now imagine here down on the bottom, so we have this little thing traced out, and then maybe the wire is going like this. Remember, think in 3D. We're all in 3D here, so this is in this 3D plane on the bottom. And then maybe it goes over here like this, whatever. Don't really care. All right, so this is in 3D. Now remember, it's in 3D. So basically, I got to connect these two somehow. I got to connect these two. So then what you do is you just take a piece of wire, and we'll show that in let's show that in this purple. You take a piece of wire, literally take a piece of wire, run it through there, and then you solder it on the top, you solder it on the bottom, and then you clip off, clip with your scissors, you clip the wire off, and that is your connection there. So now we have this artificial cheap little via. So we can do two-sided boards with this, right? This allows us to do, you know, here's the top and then here's the bottom. So we can do two-sided boards at home. So going back to this picture here, so basically you would etch these boards, and that you do this with chemicals and all kinds. There's lots of ways to do this actually. You drill all the holes out, which is very painstaking. But you know, hey, if you're doing a simple board and you're really good at this, and you can make the boards with a laser printer. There's lots of ways to do this. You actually can make a little production house at your house or your home lab and get this done pretty quick for relatively small PCBs that are fairly simple, two layer. You drill all these holes. Now this is kind of a pain in the butt. I wouldn't want to drill all these holes in a board that had like a gazillion holes, right? That would be a pain. Now this board is got, and I'm waiting for it to res up. No, it's not going to. So this is all surface mount, this is all through hole. Even though these look like they might be surface mount, they're not. There's just enough room so he can drill it manually. And he or she, takes this board, puts it in a jig, and takes their drill press and drills it. Now, you might be able to go buy a little PCB manufacturing device, and on Kickstarter and if you go to Alibaba and you go to eBay, you can actually buy things that make circuit boards. So it'll actually draw the circuit board, it'll put the parts on there, it'll drill the holes. They have these things for a few $100s. You kind of do that. But the point is, it's a manual process, so if you want to do it at home, you can. Okay, so those are the different kinds of vias. All right, so now as designers, so let's back up now. Let's back up here. We've been going down, drilling down. So as designers, we start off with, we design our circuit, all right? And this is, we need to know engineering and all that and part selection, and this is a big process, and we're going to do it when we build those little circuits, all right? we design our circuit, we get it all done, we get all the hundreds of parts like this massive ugly thing, right? Then we go to the PCB layout, and this starts off, it's just a blank page. So then what we got to do is we got to say, hey, what's the size of the PCB? Let's turn all these layers on. You can see there's this yellow line here. This is the outline. So this is the size I want the PCB, this yellow outline, right? Which I've measured, however many thousandths of an inch or whatever. This is like 5 inches by 6 inches, something like that. What's the size of it? Then you start laying the parts out. I'm not putting any circuit traces down. All I'm doing is saying, hey, I want the video inputs in this case. I want video inputs here. I want power here. I want video outputs there. I want the USB bus there or USB bus here. I want the keyboard there. I want a programming header here, on and on and on and on. Okay, now I want the data flows from the inputs to this big chip here, this big processor decoder, this HD decoder. Then there's this encoder, which is going to send it back out. So I probably want those next to each other. Then I've got a processor that's kind of controlling things. I'll put that up here out of the way. Then I've got this USB interface. I'll probably put the chip by the USB interface. Then I've got power. Let's keep the power away from the compute. So I got 6 different power domains. 1, 2, 3, 4, 5, 6. All these different voltages here. Digital supplies and analog supplies. I got these big capacitors right here, which are tall also. So I'm going to kind of put the power supply over here. Then I start laying these things out. And then one thing at a time, I start routing them, either with an auto router or by hand. All right. That's the process. And then I realize, you know what, this is not going to work in 2 layers. I got to go to 4 layers. I got to go to 6 layers. And this is the process. It's not easy. All right. It takes actually years to get good at this. But with an auto router and fairly simple designs, you can kind of do it yourself. And there's some really horrible, you got to be very careful going on internet and Googling circuit board layout, because some people do this really bad and really wrong, and they have no training, and you shouldn't pay attention to them. Okay, now let's see. So we've kind of looked at what circuit boards are made out of. We've kind of looked at these different stacks of them. We now know there's a top layer, a bottom layer, there's inner layers. They're made out of copper. They etch the copper away. We know what the stencil is for the solder paste mask. We know what Gerber files are. That's the actual file that describes how things are manufactured. And the output of that Gerber file is a bunch of different files, which are usually zipped up in a single zip file that we send to the manufacturer, along with that drill file, which may or may not be embedded in the Gerber file and maybe something separate. But here's the drill file. So if I double click that, there's the drill file. It's all in plain English. That's another thing. So here's the drill file. Here are the drill sizes. And here's all the places I want holes. Okay, this is just, and this is this language, this language. And this is saying I want this size hole, and I want these holes in these locations. That's what does that. Now here's the other thing. If I open these things up, they're all in English. They're all in readable ASCII file formats. So this format, this Gerber file format, this RS-274X format, is completely human readable for a reason. So humans can read it, because they may have to go in and edit it, and they used to have to edit it, and that's why it's ASCII and not binary. Okay. Now there are binary versions of this, but we always want to output these readable ones. Now, and then the last thing that I talked about was depending on what the tool is, they may have these different names here. For all these. They may not be in nice English names. Top copper, inner, bottom solder, bottom copper. It may be completely encrypted. Let me show you that real quick. All right, so if we go here and we'll say Altium PCB layer names. Okay, okay, so with a little bit of searching, so here's you know, kind of what you'll see is the other labels for these layers, which many other tools will use. So to see this GTL, that's top copper, BL is bottom copper, TS is top solder. So there's some method to this madness. Aperture list, drill file, keep out layer, and so on and so forth. So anyway, when you output your Gerber files, depending on the tool, you may get all these funny file names like what are these things, right? And so you need to Google it and look up and find what these things are, or look in the help of the tool. And we'll do that for Circuit Maker when we get to that point. All right. But just to let you know, these have these names. So in the case of the Proteus tool, they always have the text output as the extension, then they name the file in here, which to me is very easy and makes sense. Everybody else uses this horrible thing where it has the extension is what it is, which I think is a horrible idea. So it should be named in it and should be in English because the file's in English, but they don't do that, so we can't cry over it. Okay, so let's see, is what else is there? So what else is there that we haven't talked about yet here? So we've talked about what the circuit boards are made out of. We talked about the, oh, there's one other little thing you'll see. When you go to manufacture, and we're going to do this process also, we're going to actually go to a website and as if we're going to manufacture one of these circuit boards after we have the Gerber files. One thing you're going to see is the weight of the copper, and you're going to see this thing 1 ounce and 2 ounce and 3 ounce, the weight of it. What is that all about? Well, if you look at this picture right here, when they put on the copper foil and then etch it away, the copper has some thickness, right? It's not like a two-dimensional object. It's a three-dimensional object. It has thickness, and you can see the thickness right here. That thickness right there. So obviously, the thicker it is, the more current it can carry, right? And also the more heat it can handle. So the measurement of the thickness is measured in ounces, all right? And where this comes from is if you were to take 1 square foot of this material, 1 square foot of this, what would it weigh? And if it weighs 1 ounce, it's 1 ounce copper. So in 2 dimensions, you take a square foot. If it's 1 ounce, then that would be its thickness. If it's 2 ounce, then that would be its thickness, and so on. So if you go here and you Google and you say PCB copper thickness 1 ounce, 1 ounce versus 2 ounce, and maybe explained. I'm probably asking too much from Google here, but we'll see. All right, and here we go, how copper weight. So anyway, all right, so you can kind of look through here and they'll explain what this is. Copper weight is defined as the weight in ounces of a copper present in 1 square foot of area, just like I said. The parameter indicates the overall thickness of the copper in the layer. All right, so now when I design circuit boards, I typically want 1 or 2 ounce copper. I prefer 2 ounce copper because it allows more current, and we're talking about something that's very thin. So the actual thickness of the copper, if it's 1 ounce copper, is 35 microns, 35 micrometers, or if it's 2 ounce, it's 70 micrometers, or 2.8 thousandths of an inch, 2.8 mils or 1.4 mils. All right. So now typically when you build a circuit board, they'll allow you to have heavier copper on the outer layers. So you might be able to put 2 or 3 ounce, and then on the inner layers, you might be able to put 2 or 1 ounce copper, depending on the manufacturer, right? So if you're building a board that's got a lot of current rushing through it, you want the 2 ounce copper, or maybe 2.5, or maybe 3. It gets expensive though. But you definitely don't want to mess around with the 1/2 inch copper. That's just too thin. All right. And you got to watch out for that. So that's what this copper thickness, and that's where this ounce comes from. All right, so it's basically measured an ounce per square foot, and then that gives it a certain thickness, and these thicknesses are right here roughly. So just remember, it's about, for 1 ounce copper, it's about 35 micrometers or 1.4 mils, and it's linear. It's a linear relationship, so if it's 2 ounce, it's going to be twice that. If it's 1/2 ounce, it'll be half as big. So 1 ounce is 35 micrometers or 1.4 mils. Start with 1 ounce copper when you build your circuit boards, are going to be fine, and then you can kind of, as you understand things better, and your requirements need more current or whatever, instead of making the trace wider, you may not be able to make it wider. Remember we talked about the current carrying capacity of these traces? It depends on, obviously, their three-dimensional structure. So you may not have room to make the thing 40 or 80 or 120 thousandths wide, but you might be able to make it thicker. That's where that ounce copper comes into play, but it gets more expensive, all right? Okay, so I think that's about it. I think that's enough kind of prelim to give us a little bit of language. I think we're ready to go. So let's stop the video here, and then we're going to go onto the bench, and I'm going to show you circuit boards and all kinds of cool stuff, and we're going to talk about those. Okay, so I'll see you in the next video. All right, welcome back. We're on the next lecture here, and last time we talked more about printed circuit board design and kind of looked at things on the computer. We talked about Gerber files. We talked about the layers of the circuit boards. We talked about what they're made out of, what PCBs are made out of. We talked about vias and a number of different things. So now you should have kind of an abstract idea. based on what we talked about. And now what we're going to do is we're going to actually look on the bench and kind of go back and forth here on the computer on the bench, and we're going to look at actual circuit boards. So some different projects that I've developed over the years. Some are surface mount, some are through hole. And this way you can actually get a grounding and see what we're talking about here, so that when we go and design our circuits, and for example our first one, which is going to be this little magic wand here, which is going to end up looking like this circuit board down here, right? And we're in Circuit Maker right now, so it's going to end up looking like this. Hopefully that's what it'll end up looking like. So anyway, so let's go ahead and we'll just leave this here for now. So let's jump over to the bench and let's just start taking a look at stuff and just kind of going through it like we would if we were just kind of doing a show and tell. All right, so I'll meet you over there. All right, so we're here on the bench, and I've just put a few circuit boards, stuffed circuits that would actually fit in the camera view here. All right, so it doesn't really matter what they are. It's just showing kind of a multitude of different things, so you can kind of get an idea. And what we're going to do is we're going to talk about each one of these a little bit, and some of the techniques used on each one of them. And so you can start to see the things that are similar, the things that are different, and and just get an idea of what's going on here. And then also, I've got a bunch of blank or unstuffed circuit boards, and we're going to look at those as well. So we're going to look at a lot of stuff. So this is going to be a lot of fun. So again, as usual, I'm just going to go out of order and just make it up as I go. That's the way I like to do it, just like I'm lecturing in a class. So we're going to see what's going to happen here. So all right, so let's start off. And so we see a bunch of different things here. So let's take a look at something that we've seen. So if you recall on the screen a little while ago, we had this, and this right here was that medical controller, right? And this was that board we were looking at, that 4-layer board. And here's those video inputs, and there's those 6 different power regulators. Here's these big capacitors for the power supply. Here's this video decoder, video encoder, and here is this PIC 32-bit processor. Here's an FTDI USB to serial bridge, and there's a PS2 adapter, and here's a programming port for the processor. I believe this is if I recall, yeah, this is a filter IC and a little adjustment potentiometer there. So anyway, a lot of cool things here. So now this board, and let's go ahead and let's see if we can zoom in a little bit. All right, so we've zoomed into the board here, and we've got the other close-up camera, so we can take a look there also if we want to. But what I want to show you is if you look at this, it looks exactly the same as those Gerber files, right, that we had. So there's the top layer. Now we can't see the inner layers, right? But if we turn the board, on its side here, and of course it's not focusing because it's too close to the camera, but we could see the layers. If you looked real close, let's go over to the other camera, as a matter of fact. Let's see if we can do that. All right, so we're over here on the other camera, and if I put this back just enough, let me see if we can kind of zoom in, and you might be able to actually start to see the layers. And you can see the substrate there in the middle, and on the top and on the bottom, so you can see there's that yellow substrate, and on top is green and on the bottom is green. It's actually, that's just the paint. All right, so everything is kind of yellow. And then inside of here is also, basically inside, if I can get my finger in here, inside of here are those other inner layers as well. But that's what it looks like on the side. So just like we saw in the on the computer. All right, so let's go back here so we can kind of look at this at some distance. All right, so we've got our top layer. All right, we've got a couple inner layers which we can't see. And then we've got, this is called the silkscreen layer, the thing that's got the text on it, all this writing so we can see things. And the reason we want to see things, of course, is so that we can see what components to put down here. All right, and on the bottom, so there is the bottom layer, so there's the bottom copper, and again, that looks exactly like what we saw on the computer there. All right, and there's no text here. We can put text here, and a lot of times boards have components on both sides. All right, so I'll show you a board that has components on both sides in a minute. So now let's kind of take a look here at some of these components. So this is a quad flat pack QFP. There's another QFP. This is an SOIC or a TSOP, and it's only got leads on 2 of the sides, where these quad flat packs have it on 4 sides, right? And so those are all surface mount parts. And then all these little tiny components, and again, we're going to look at some other stuff on the zoomed in camera in a moment. Those are all surface mount. Now, these are all mechanical components. So we refer to these as mechanicals, right? Or you just say the word mechanical, it's mechanical. And those typically go through hole. Now you can also get surface mount mechanicals, but they're not as strong. So like right now, I'm putting a good amount of force on there. You see I'm flexing the board, right? And you know, I probably maybe could break that out of there if I really wanted to. The part would probably break before it would pull out of the board. Now, if it was a surface mount mechanical, I could probably rip it off of there. So it's through hole for a reason. You can see over here, you can see all those solderings, and you know, we're soldering right through there. Now, you can also see the vias. So you see these little holes here everywhere. Those are those vias we talked about, which are punching through. Now, there might be internal vias. Remember those hidden vias? Or there might be blind vias, which are totally internal, right? And then over here we've got power supplies, and we've got 6 different voltage regulators, and you can see we've got these capacitors here, right? Larger capacitors, so no need to spend the money to make these surface mount. They're through hole. So those are through hole capacitors. These are probably 220 or 470 microfarad. Yeah, they're 220 microfarad. And then we've got these big ones right here, which you would, you know, never want to make these surface mount. They're just too expensive. So you get these big electrolytics. All right, so that's you know, one circuit right there. So that is a video controller. All right, so let's take a look at something else. So let's see here. So this, let me back out just a little bit. Back out just a little bit. Okay, this guy is an old X Game station. So this is something, I don't know, I did this about 12 years ago, something like that. It's a game console, and it was kind of a do-it-yourself game console, purposely made with all through-hole components. So except for one part, and I'll tell you why. So if you look at all this, so we have all these dip chips, right? So these are dual inline packages. Dip, 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 dip. All these are dip. Even these clock oscillators are dip packages. And the reason for that is so I could put sockets. So see how these are socketed in here? So let me see, let me go onto the zoom camera, and let's back out of there, and we got that specular, there we go. So you can see each one of these chips is inside of a socket. So the nice part is you first solder the socket into the printed circuit board, then you put the chip inside of there, all right? And that protects the chip, or if the chip is damaged, you can pop it out, or if you want to change it. So again, you see everything is through hole, through hole, through hole. Here's a big connector. This is where a game cartridge goes in, through hole. So a lot of through hole components where I could. And then a couple things aren't through hole. So for example, under this heat sink here, there's a processor, and this is a quad flat pack, and this is called an SX52. It doesn't really matter. And then here's a memory. Now notice the memory, I couldn't get this in a through hole, right? And typically you're not going to find these in through hole because they're just a little too advanced, a little too modern. This is 128K static RAM, and this is what's called a J-leaded package. And it's J-leaded because if you look at it on the side, these things kind of make J's. You can see right in there. Let me zoom in a little bit. And let me see if I can point to one. It's always interesting trying to point. Yeah, there we go. So you can see it's J-leaded, and you just solder that. So you know there's a surface mount component, but the majority of the board is all through hole, right? As much as possible. Now over here in this section, now notice this. Now I want to zoom into this for you, and let's see how well we can see that. That's not bad. So this part of the board right here is mostly surface mount. And the reason why is because this is not something the customer was going to mess with. This is a built-in programmer I designed to program these ICs. And with firmware that's inside of this, another processor. So here's another processor just to program the main processor right there. All right, and since I wanted this just to be kind of this black box, I made it all surface mount. So you can see these little surface mount components, right? And these are resistors. That's a resistor. That's a transistor. Resistor, resistor. And you can see R33, resistor 33. Here's some capacitors, C40, C39. That's those reference designators. They're called reference designators. And that's how you tell what these parts are. So when you're putting the board together, you know what to put down. Now, of course, if a robot is doing this, it doesn't need to see any of this, but it looks cool, and these boards are typically in a box anyway, so it doesn't hurt to put these there, especially for debugging. All right, and then there's some text, you know, onboard programmer. Here's the interface, you know, so the text, you know, describes what things are. All right, so let's zoom out again here. All right, so again, this is a 2-layer board. All right, let's go to the other camera. So this is a 2-layer board. We got the top layer right there, and you can see all the copper fill, and then you can see there wasn't much fill in this area right here, right? And this was auto-routed actually, so I let the auto-router route this just for fun back then to see if it could do it. It took it a few minutes, and then it routed it, and then I kind of went over it and kind of fixed it up a little bit. All right, and then on the back here, here's the back. And then we can see there's a lot of holes in this because it's got so many through-hole components, and there's also a lot of vias. Now, one thing you might also notice is look the way that the traces are all running here. They're all running vertical. So in this layer, they're running vertical mostly. And then if you go look at this layer, all right, they're all running horizontally, right? I've got the board backwards here. Doesn't really matter. They're all running horizontally. And the reason for that is because it allows routing to occur in a more effective way. So if you were to route the top and bottom both in the same direction, it makes it very hard to run a wire, in the opposite direction, perpendicular. So one layer you do this way, and the other layer you do that way, and it just helps with routing. All right. So anyway, so there's another board, and again, it's red. This is just paint. This is just paint. This is the resist, and this is the solder resist layer, and it's just painted on there. And you can make these things any color you want. The board, this is an FR4 board. If we looked at it on its edge, we could see its layers very carefully if we had a magnifying glass. All right, and that's that board right there. All right, so let's keep going here. Let's see what else we got. So let's see. So here's a surface mount board. So this one is mostly surface mount. Let me see if I can get the camera to cooperate here. Yeah, there we go. So this board is mostly surface mount. The only thing that are not surface mount are the mechanicals. And again, you want those mechanicals to be strong. This is a little game console, it's called the X Game Station Avar, I believe. And you can see I made it white. And you can see the traces there in the specular light, right? You can see the traces, but the white hides them really nice. And I started doing these whiteboards many, many years ago. Now a lot of people are doing white because it's cool. So anyway, we've got mechanicals, again, which are through hole. I could have made them a surface mount, but again, you want that strength. Now another thing is, when they're through hole, each one of the pins from the mechanical, whatever it is, this is a VGA connector, for example, every one of those pins goes through every single layer. So if you've got a 2-layer, 4-layer, 8-layer, whatever board, then you can route all of those different layers from those signals. Now, when a part is only on top, if I want to route something on the bottom layer, I got to punch a via through there, right? So that's why mechanicals, it's nice because you do them through hole. If you got the room, then you get these signals on all the layers, right? And here's a heat sink over there's a couple of voltage regulators there for 5 volt and 3 volt. And then there's the power, there's the VGA connector, as we said, there's a PS2 connector, programming connector, JTAG for debugging. And then this is kind of a serial port, little debug port. And then here's the processor. This is an Avar Atmel ATmega, I think 644. Let's take a look. So come here on the zoomed camera, and we'll zoom in. Yeah, and it's Atmel 644, and that's a nice processor. It's an 8-bit processor. All right, and then this section here is the video driver, so it generates video for you. So fairly simple, little SD card, little header for interfacing. All right, but again, mostly surface mount. All right, and again, this is a 2-layer board, so it's got a top layer and a bottom layer, and yeah, you can there you go. You can sort of see the traces. There they are, and that's why I like it, because it hides the traces, makes the board very cool because you can't really see anything. All right, so that's that one right there. Let's see. Coming back over here, let's zoom in a little bit here. There we go. Let me get the camera to cooperate with us. Okay, so this board right here, so this is interesting. This is a smart book, and this is completely surface mount except for a few components. Now these big, so this fits inside of a book. So now it's not going to fit inside of the book with all these things sticking out of it, right? So all of these headers are for testing only. So this is a very complicated piece of technology. It's for a smart book. It runs a language and all kinds of stuff. And it's got, USB here. It's got SD card here. It's got an accelerometer on it so it can control motion. It's got this interface to control switches and LEDs and all kinds of cool stuff. Surface mount power supplies here, we'll take a look at those in a second. So everything is surface mount, but when you're designing boards and debugging them for the first time, now remember, something this complicated, if you design this on the computer, right, and you don't do simulation or you can't do simulation because it's too complicated to simulate, at least with the tools you have, you basically have to design a schematic and then build a PCB and then stuff the PCB and see if it works. Guess what? Never works, right? Never, never, ever works. What you can do is you can build like little blocks. So you might build this block on some solderless breadboard, check it. Build this block, build this block, build this block, build this block. You can do all that and then integrate them together, and that's kind of what I do as well. But no matter what, when you put the whole thing on a single PCB, it just, good luck that the whole thing works. There's about 1,000 ways it can go wrong. Wires are wrong, signals are wrong, one of the chip footprints is wrong, just countless ways that things don't work. Or the board is manufactured wrong, or there's a solder short inside of something when you assemble this. So what you do is you put a lot of test points and a lot of things, and that's what all these things are. So I can get to all these signals and verify them. All right, and this board actually worked the first time because I did actually test all these sub blocks, and then when I put the whole thing together, I was lucky that it all worked. So the final version is completely flat, and all these things are gone. Now the things that aren't gone are like this, this micro header right here. This is a test USB, so that actually goes away. So this micro USB and then this SD card are actually there. So the whole thing flattens out pretty well. And this is like one of the smallest. This is, I believe, this is 4 millimeters thick, this audio port. And then notice what I did. I cut a notch in the board, right? I didn't personally cut it, but I designed it to have that cut. Notice this is not a square. I cut a notch in the board so this thing fits flush and it actually grabs under it. Isn't that cool? So that way I take away some of the thickness and it goes into the board. So that way I kind of push it down into the board to take away 1 millimeter or so of thickness. All right, so let's take a look at that on the zoomed in camera. All right, so here we are on the zoomed in camera, and so there's the board. Let me see if I can get it to focus a little bit better. Yeah, so you see all kinds of stuff, and then like these buttons right here, the user is never going to see these things, obviously, right? So those are, again, for testing. Reset and another button there. So a lot of things for testing. So when you do in design, a lot of things are for testing. Here's the power supply. That right there is the entire, it's a buck boost power supply. Powers off a 3.3, or excuse me, a 3.7 volt lithium ion battery, and then converts it to 3.3, all right? And there's an accelerometer here someplace. Yep, there it is right there, a little teeny tiny accelerometer. All right, and again, all these chips, there's a QFP, we know what that is, and then these chips are these called TSOPs or TBSOPs or or SOP or SOIC. Usually SOICs are a little bit bigger. All right, and then again, we've got our surface mount capacitors here, and then here's an audio amplifier. All right, there's a transistor right there. I think that's a transistor. That might be a FET actually. All right, anyway. So that's that, and then flip it to the back, and on this one, there's nothing on the back. And you can see there's not a whole lot of through holes on this one, just this testing stuff. And then you can see the vias, not a lot of vias, and those vias are punching through both sides, so the signal will go from the top to the bottom. And this board, I believe, is 4-layer, I can't remember, 4-layer or 2-layer, not sure. But anyway, so there's another surface mount board. And then again, you don't have to make these things square. This has had to fit inside of a book, right? It was an electronic book. And so I needed this notch here, and then this is where it pushed up against the outside of the book where the user, the child, would plug in his headphones and all that, and then you would charge it through here. And then this was inside the book, and something clamped down on that. And then the signals would go out of there using a conductive ink kind of setup to communicate to it. All right. So again, as you design your circuit boards, don't be afraid to make them big. Don't be afraid to put testing points on them and all that. You can always iterate and then keep, detailing and making it better and better. Don't try to do the whole thing at one time. All right. Okay, let's see what else we have here. So here's another through hole. This is an old, another little game console. This is a kit. You actually build this, and I don't think I have a circuit board of this right here, no. But so you get this as a kit. You just get the blank circuit board, you get all the parts, and you solder this thing together. And 12-year-olds do this in classes I used to teach, and you would put it together, and then it plays a little 3D racing game. So again, totally through hole, and there's not a single surface mount part on this. Totally through hole. And again, you can see there's sockets. I've socketed things so that you can first solder the socket so you don't burn these chips out. Now, in manufacturing, typically you won't see sockets. You will see just the chips. If they are through-hole chips, they'll just be soldered right into the board to save money. These sockets are like 10 cents or 5 cents or 2 cents in quantity, but they actually, they cost money, so they increase height to the board, and so they'll be removed typically, and the chips will be soldered right in. Now, some designers like me, I'll leave these things. I don't care if they cost a few cents or a couple dollars, because one, it allows me to pull the chip out, and also I don't toast the chips during soldering. All right, and how these things are soldered, I think I've talked about this before, but when you're doing a through-hole board, if a machine or a robot did this, a pick-and-place machine, a robot would grab the parts from different reels and trays and put them in here, and put all these things in here really fast, right? Then what happens is the bottom of it, all these pins are sticking out, right? All these pins are sticking out. Sorry, the camera's shaking. And then what happens is this board is grabbed and it goes on a little conveyor and it moves up, and it moves over a molten layer of solder. And as that solder makes contact with the bottom of it, it solders the entire board. All right, and that's called wave soldering. All right, and that's how those through-hole components are done. So when you have a board that's got mixed components, right, like say this one, again, this is and let's skip this thing to lock in there. There we go. This is a little credit card computer. It's got some mounting holes here. So this one's got surface mount. Again, there's some QFP, here's some TSOPs, TSOP. There's a SD card, bunch of headers, mechanicals. This is an FTDI USB to serial bridge. My power supply regulators are right under there. Now this board has both things. So it's got all these through-hole, and it's got the surface mount. So how do you make this thing? Well, in manufacturing, how it's done is typically first the surface mount parts are placed on here, right? And solder paste is put on here with a stencil, and those things are soldered on there. Then step 2 is, and then they're cooked on here, right? So they'll be put in an oven and then cooked on. Now we're done. Now all these through-hole parts will be put on here and then wave soldered. So something will grab this and then push it over again, and it'll go over a molten layer of solder and then solder it all on there. And then you're done. Now, if you want to save money and you're going in China, sometimes the labor is actually cheaper to just have it done manually, or they may have to do it manually. So sometimes just workers will pop these few things in and solder them manually. All right, so that's kind of what happens there. So anyway, so there's another board. Now, some interesting things here. So again, it's square, but then no one said I can't put these here. So these are mounting holes, right? So you could put this into a project. This is used for an industrial controller, right? So it's got a lot of features to do that kind of thing. And you would mount this to something and screw these in, or a couple of them. Now, one thing is these can be broken off. So maybe I don't want to do that, and I don't like these little things sticking out. So these are scored, all right? And you can actually snap them off if you apply enough force. So let's take a look at the scoring. Let me show you that. So if you look on here, you can see these little lines here. And let me see if I can go on the edge here. And it's going to probably be pretty hard for you to see. Let me see. Maybe we can get it right there. Let me see if I can get it to zoom in. And then let me get it to zoom in. You may be able to see it. Yeah. Okay, so that's really hard to see. And where'd my pointer go? So right there. So there's a little scoring. So what they did is they take a saw and they go to a certain depth, and I did some math and computed what depth do you kind of need so I can apply a certain amount of force to snap this part off. And I'm not going to do it, right? But you can snap this off if you want to, and it'll make a clean snap as long as you do it carefully with some pliers or something like that. And again, you can see here's the core, right? There's the core of the circuit board made out of FR4, material. We got the top and the bottom. This is just paint, right? This top solder resist, bottom solder resist. Now notice on this one, this has also got text on the back, right? So it's got silk screen on the back, all right, and it's got silk screen on the front, right? And so that this is just mostly a marketing thing. You don't really need the text on the back, but it's just cool, Prop C3, all right, and on the front for actual manufacturing. All right, let's see what else we have. Okay, so let's go back over to the main camera. So now, well, you know what? I got a couple little small things here. So here's a couple small things. And again, sorry for that camera shaking once in a while. So this is a little programmer, all surface mount except for the connector. All right, and I'll show you that on the zoom camera. And so this hooks into the USB, and then this hooks into 4 pins, and this programs a processor, an SX processor. This is really, really old, and this was originally designed by Parallax, and then we did a redesign, I don't know, a couple of years ago, and made a couple hundred of these things. Now notice it's in this shrink wrap. Shrink tubing, and that's just to keep it protected from you touching it and all that, and then also just to keep the heat. This obviously makes it hotter, but it also normalizes the heat as well. So that's that guy right there. Let's take a look at that under the zoom camera. So there we go. And we're getting a little bit of specular reflections on here. Let me help that a little bit. But there's overhead lights everywhere. All right, so there that is right there. And let me zoom in a little bit. So, and this is by no means small parts. These may look small, and you can see here's the tip of some tweezers. These are small, but you can do this by hand. It just, if you have some glasses on, some magnifying glasses, and some patience, you can do this. These are not small. These are mostly what are 0805 parts, and then of course we go down to the 603 smaller, and the 402 is actually quite small. Those are hard to work with, but 805 is not too hard to work with. All right, and then again, we've got these surface mount parts. These are T-SOPs usually, or they're called S-SOPs, different names for them, but the bottom line is they just have 2 rows of pins. These little guys right here are typically transistors, these little 3-pin guys. They could be transistors, they could be FETs, and of course I can't remember, it's been too long. All right, and then on the back, so this one, on the front here, do we have, no, there was no room, very little room for reference designators. You can see them right here, and I can zoom in. Let me zoom in a little bit. And you can see those reference designators, and I'm trying to get the camera to do something, but you can't even barely read them. That's at the limit of resolution of the printing process to print the silk screen. But on the back, there's another one here because we have some surface, and so this is originally designed by Gunther Dubach, who's recently passed away, unfortunately, a great programmer and designer. So he did the original one a few years back, and then when we started manufacturing, we went over it and kind of cleaned it up to make it a little bit more manufacturable. So anyway, so that's that little programmer. So again, you can make these things any kind of shape and size you want, right? These circuit boards. Here's something else. Let's take a look at this. This is a little this is a USB charger, and so this goes in, and then this goes to your battery. Now I just have this header on here for testing purposes, but normally this would have some wires to a lithium-ion battery that it would charge up. So this is a little charging circuit, and this little LED pops out of a piece of plastic. So this is sheathed in plastic. All right, this is a 2-sided board, and then notice I've got these cutouts inside of here. These are called notches, and those hold inside of the plastic. So I designed a plastic housing in SolidWorks, right? And then this kind of fits inside of that, and then it clicks down and that kind of thing. So anyway, so there's a little charger, right? All right, so let's go back to the other screen here. Okay, so now what I want to do is, so let's go back to the computer for 1 second. I want to kind of use, this is going to be a quick example. I'm going to show you something. All right, so we're back here on the computer, and what I want to show you is, because I've got the Gerber, I've got the design, I've got the circuit board, and I've got the blank circuit board of something, so all at the same time. So let's see. So if we look here, this little design here, and again, this is on Proteus, not Circuit Maker, and the only reason why is because I did this on Proteus, right? So we're just going to look at it. And this circuit board right here, this is the top layer. This is a 2-layer, so let's go, we'll turn them all off. So there's the top layer, right? And then here's the bottom layer. So fairly simple. You can see some holes through here. This is a product that's a controller for exit signs, right? So this is an AC controller. You can put in 110 to 277 volts in it, and then it does a bunch of different things to make that all safe. So here's where the AC comes in, and then there's a transformer here and some capacitor here and a bridge rectifier, and then there's all kinds of things going on here to get this all to work. Here's where the battery goes. These are 3 big mounting holes. So when you do something like this, you have to work with maybe an industrial designer or a mechanical engineer that are designing the housing for this, because this is going in an industrial product, right? And make sure that you're putting everything where they need to go. Where do these controls go? Well, there's holes in the housing where screwdrivers go through to adjust it. There's a fuse over here to make this safe. When you do AC things, you have to follow rules. In the United States, we have UL, Underwriter Laboratories, and so you have to follow UL specifications. And for just about anything electrical, electronic, whatever, there's a UL specification for. And if you want to follow that UL specification, that's a good thing. And then that means that companies that buy things, they say it has to be UL certified for whatever the certification number is. Whatever that particular thing is, it has to be certified. That means you have to design to it, then it has to be tested and verified and all that, which this board was. And this is also verified, and it works in Europe and in other places. Anyway, but what I wanted to show you was so that we have this board here, and again, here's what the top layer looks like. Here's what the bottom layer looks like. That's it. All right, and then there's the top silk kind of going on there, right? And the board is just a rectangular board, no funny business, no cutouts or anything like that. And one thing you can see though is all these AC lines are thicker, right? And you can see hot. When you're doing AC, remember there's hot and there's neutral, remember that, in ground? So when I did all this, right, you do this design and then you do the math. So you're running AC current, how thick do I need these traces to be? And then I probably added 50% or doubled them and then make the ounce copper thicker. So we've got this board right here. Now what I want to do is I want to show you this in all of its different forms. Okay, so let's go over to the bench and take a look. So here is the board right here, and this is after it's been stuffed. So now you can see what this thing looks like, right? So there's our transformer. Here's these big capacitors. This is an AC capacitor. This is where the power comes in. So this is very industrial, right? So you just, take two wires, you cut the wires, you strip them from the power lines up in the ceiling, and you put them in there. And then there's a fuse, right? Glass fuse. And then here's where the battery goes. It sits there. And move this away. There's where the battery goes, and it just kind of sits there, and then this whole thing's in a rectangular housing. And here's where the lights go, and this is actually an electroluminescent lighting controller. So this is an industrial controller. All right, then it's got a couple other fun things. So what's this? Here's the LED, right? So this says what's going on. So when you see an exit sign, right, an emergency exit, there's like a little LED that tells if it's powered up or the battery's good and all that. So we had to make this, right? So this is a cable. This didn't come for free. So I actually had to manufacture this cable. So I said, use this LED, then I want you to put shrink tubing, I want you to twist the wires, I want one green, I want one black, I want this connector on it, and this was manufactured in China for me, right? So that goes right there, real nice. Okay. Anyway, and this will then plug into the housing someplace, right? And then that goes so that people can see what's going on. And then you need a reset switch. This is the only thing. So the second, when this thing's connected, right, when the worker comes and he connects this thing, there's no on-off switch on this particular product. It's just on. Once this power's in here, right, that's hot. So here's our little reset switch. So that then goes someplace on the housing, right, which I can't remember. Anyway, and then finally, this is a closed loop adaptive controller, and that's what makes it so efficient. Here is a little sensor, and I'll show you that up close. This is an optical sensor, and so this is looking at the light output of the actual exit sign. And the cool thing is this looks at the light output, and then I can tell for how much power I'm putting in, I need to maintain a certain level of luminance, right? And that luminance I need to maintain the UL specification, or the European analogy to that UL specification. So that exit sign can't get dim. If you go someplace, go to a movie theater, go to a bank, go wherever, the exit signs are just like jacked up and ghetto and broken and all dimmed out and ununiform. But this controller controls electroluminescent lights, and it maintains the brightness for up to 10 years, which is awesome because you never have to change these. Some buildings have 10,000 exit signs, like the Pentagon. So if these things break in a year, well, you would be going in there fixing 10,000 signs. So anyway, it's adaptive, and this senses the light, and then it comes back in here. There's a microcontroller in here, and then there's this is called closed loop control. We've talked about that in our lectures. And this allows me to adapt things. So as the light ages, as the electroluminescent light ages, right, then I can try different things. I can increase the frequency of the excitation, I can increase the voltage, I can do this, I can change the wave shape, and I have all these different parameters I can play with to try and maintain the brightness so that it always looks the same over a period of 10 years. Anyway, that's just some tech stuff. Doesn't really matter about PCB design, but the whole point is we're here to make products. All right, so there's the top, and if we were to look at that, we would see it looks just like the thing that we just showed. And there's the bottom. All right. Now, where are the circuit boards of this? So let's take a look at that. So first, let's take a look how these things come. We haven't really seen that. So here's some manufactured boards. All right, so this has come from Hubie Gold Phoenix Technology. So this is actually a cool company. Gold Phoenix, that's one of the companies I manufacture things, just circuit boards, PCBs. I don't do full manufacturing there. It says the size, the name, the revision. This is version, what, 6? Version 6, the date. This is like, what, 5 years ago? All right, and then, yeah, I don't know, there's like 10 boards in here or something like that. There used to be something like that. Anyway, and then they're purple. So I'm like, I want to make it purple. So that's how they come. Now, so here is that board right there. There's that board. All right, and that's what it looks like. All right, there's the top, there's the bottom, very nice, very clean. Now let me talk about this surface right here. So see, this surface has got this shiny, uh, metallic look on it. Let's look at it on the zoomed in camera. So see, this is copper. So what is this? Why is this shiny and looks like solder? The reason why is it's solder. So what happens is after this board is made, the surface is all, these openings are all copper, right? So they would be yellow copper. And that's great, but copper gets tarnished and gets very yucky very quick. So what we do is we have to put a coating on these. So you can opt for many, many different kinds of coatings. This one's called Hasl, HASL, and we can look at that on the computer later. But there's these different coatings. Hasl is hot air surface leveling. It's solder. So basically they just put solder on here, and the solder makes contact with these pads and then sits on there. It's very nice, it's very cheap, and it's nice because then there's solder on here. Let me see if I can get this to zoom in and lock on. But the problem with it is, and I'm purposely trying to get this in the light a certain way. There we go. Maybe you can see that, but you see it's not flat. That surface is not flat. It's kind of bumpy, and you can't really see it from the side. Maybe you can a little bit, but it's not bumpy. Excuse me, it's not flat at the level we need it to be flat. So now in something like this, where we're doing, and let me move this light a little bit, it's driving me nuts. In something like this where we're doing something that has kind of large components and larger surface mount components, that's okay. But if you're doing something very fine pitched, very, very small surface mount, we need these surfaces to be very, very flat. So like flat under a microscope flat. That means we'll use a different surface finish, and there's many of them based on gold, based on silver, that when you're done, they actually look very flat. Let's take a look. Let's go to the computer real quick and see what we're talking about, just to make sure. All right, so we're back here on the computer, and I just want to make sure you know what I'm talking about here. A lot of times, since this is the first time you're learning about this, I want to make sure that I'm not just glossing over something. All right, so let's say here is the cross-section of the circuit board. So this is looking at it sideways, right? Okay, and then here is, let's say we're looking at a cross-section of a trace or a pad, and here's another one here. Maybe it's bigger, right? That's a cross-section. So that's nice and flat, okay? By definition, that's just metal. Now, we want to put something on top of here to protect it, okay? We want to put something to protect it. So we can put that Hasl, and let's do that as this gray color. So when we put that, it kind of looks like this under a microscope. See how it's kind of bumpy? So it looks a little bit bumpy. It's okay. So it's a little layer of solder. It's very thin, but it's still bumpy. What we really want is something very, very, very flat. So we'll do this as red. So another thing is like ENIG, E-N-I-G, and I think it's immersion. We'll have to look it up. Nickel, immersion gold, ENIG, E-N-I-G. We'll look it up. And it is very flat. It's based on gold, and it makes a very flat surface. And the surface is very repeatable. In other words, when this coating is put on here, it's the same all over the place. So it allows you to mount things, for example, ball grid array ICs, BGAs, that have balls on them. And these balls better make contact in a very, very special way. So if there's something bumpy under there, like that Hasl, that hot air surface leveling, it just won't work right. So let's look up and make sure we have that name right. So we're going to say PCB coatings, and we'll say Hasl. All right, and let me zoom out of here a little bit. Okay, here we go. So Hasl or hot air solder leveling, and let's go to this Wikipedia. All right, and it'll show the advantages and excellent wetting during component soldering, and this means it's very easy to solder, avoids copper corrosion like we were talking about. Disadvantages: low planarity. That means it's not flat, right? Low planarity, high thermal stress during process may introduce defects in the PCB. Then there's also this ENIG, right? This is the one I like, and this is electroless nickel immersion gold. Like, I'm never gonna remember that. So anyway, this is a much better process. It's based on it's basically nickel plating with a very thin layer of gold, like micrometers. And it's not showing you here, but it says has several advantages over Hassel, including excellent surface planarity, particularly helpful for PCBs with large VGAs, just like I said, good oxidation, its resistance, and so forth, right? So that's that. So those are kind of your two main go-to kind of surfaces. And then here, just some random search here comes up with advantages and disadvantages of different surface finishes. So Hassel, and then of course there's lead-free, because remember, this is solder on here, right? It's a solder layer, a coating, and these days you want everything lead-free, right? Lead-free things have slightly different properties. They're a little harder to actually work with, but we have to work with them now because we don't want lead in our circuit boards. So it's talking about that, advantages, disadvantages, and then there's this immersion tin, advantages, disadvantages, organic solderability preservative. This is something else. I haven't actually used this one. And then here's the one I use. I use Hassel and ENIG always. So when I'm doing a big board, kind of low cost, I'll use Hassel. Done. All right. When I want something flat that I can solder really well, that's high performance or whatever, I'll use this ENIG a little bit more. Those are the two I want you to use: Hassel and ENIG. Done. Problem solved. Let's go back to the bench. Okay, so anyway, there's that purple board we're looking at with the Hassel surface. Now let's go back over here. Now notice here's a blue one. It's the exact same board. Exact same board. I just wanted it in blue because that's just, I felt like it. And I didn't like this. I thought it was too dark, so I got the blue one. And I liked the blue one better. It just, I don't know, it looked happier to me. So anyway, blue one, exact same thing, no difference. And then that's it. Again, you can see that silverish surface finish. That's Hassel, hot air surface leveling solder, right? And I don't think I might have, you know what? I might have an ENIG surface here someplace. Let's see. I'm just going through everything here. Yeah, I do. Here's another circuit board. So let me show you, now I'm going to show you some bare circuit boards. All right, so here's one right here, and I've got this upside down. Again, doesn't really matter. This one is ENIG. You can see it's gold, right? Let's look at it on the zoom camera. So here's this one right here, and you can see it's gold. And let me see if I can zoom in a little bit. Just really a beautiful surface. Yeah. It's hard to see, but as I go by, these things are very flat. If you look at this under a microscope, it is really, really, really nice. And there's the MPU, that's a Cortex processor and ARM that goes on that, and you can see it's just very flat, very nice. I love this. So just a little bit more expensive on this guy right here. Again, it's a rectangle. It's all surface mount except for the mechanicals, which are in these cases just headers for programming and things like that. And then you can see everything's blocked out. Here's a power supply. Here's USB, RX, TX. TTL port, some status LEDs, some I/O here, and then this is an ultrasonic driver, actually, a very advanced one. And then here's the back, very nice. You can see it's just a beautiful this color. It's kind of a it's a blue on the camera. I can't really tell what you're going to end up seeing. So anyway, and this is 4 layers also, and again, very hard to see. And let me try and. Yeah, you can't really see it. But if we were to strip this board apart, we could see the layers. But again, in this thickness, if we go get some calipers, let's get some calipers. So this is probably a standard, like, 63 thousandths board. Let me put the calipers into inches here. So there's my calipers, and let me grab it. Let me grab the board here, and let me do that on the other camera. Okay, so here we go. And there you go. So it's about 60 thousandths. And within air of me squishing it, right? So that's a standard board size. So I just said, hey, just make it standard size. All right, so there's a board with ENIG, and you can see how it's all laid out very cleanly, right? And that's a good thing. And each one of these are probably from a design when I made this a couple years ago, each one of these, the power supply, this, that, whatever, I took these designs from other things that I had already done and kind of plopped them down here and then integrated it nicely. All right, and that's what one thing you do. It's like doing software. You make objects in software. Maybe you make an API that does something. Once it works really well, you just grab the whole thing and plop it down. Of course, you can do that with any CAD tool. So typically, you can't really plop down the circuit layout. You could, but you can at least plop down the schematic. The circuit layout, you kind of have to move things around to make it fit, so you end up redoing that. All right, so anyway, so that's that Ultra DSP board. All right, let's see. I want to show you, here we go. So here's something. Now this is an interesting thing. So I'm gonna turn this on its side so I can get most of it on the screen. So what is going on here? Let me show you this. All right. What this is a set of boards, and this is for touch interfaces. So obviously I've taken out a few of them here and took them apart. So let me grab one here, and I'll put this over here. All right, so here they are here. And so what's going on here is, so I made this big board, and these are the controllers. So this has actually got a touch controller right there, and you can't, there you go. That's got a QFP, a little micro QFP touch controller, couple headers. And how this works is, this header right here, I put a bunch of pins in there, and then I break this board all apart. I break all these pieces apart, and then what I do is, I want to try this design out, and then so I put a header here, a male and a female, and I snap these together. So first I'm going to snap all this apart. That's scored. Can you see the scoring in here? See, if I put my finger in there, it's all scored, so I can break this all apart. So what are all these different versions here? Well, if you've ever messed around with capacitive touch, you can get this thing to work, but if you want it to work really, really well, you got to really know what you're doing. And so there's all kinds of variants here to experiment with different capacitance, different shapes, different board layering, and putting things on the front and back. See, there's no backfill here. There's fill here, fill here, fill here. There's hatched fill here. You can see that it's hatched, right? No fill, no fill. So anyway, all these different things, and then which one works the best? Because in capacitive touch, what you're looking at is when I put my finger on here, I want from no finger to finger capacitance to change a lot. I want the dynamic range to be very big so that my little chip can detect that. So this was a kit. I made this. So I picked a chip and I said, I like that chip. That's going to work for me. But now I got to try all these different things, and this is for I think a game. This is a game console that has Cap Touch. So I said, let me try making 8 different versions of the Cap Touch interface, where I'm going to try buttons doing different techniques geometrically, and which one works the best, then I'll use that in my design. And again, there's that prototyping. We're always prototyping. We're always trying to optimize. We're always trying to do the best possible job. And again, I can just snap that. Let's look at it under the zoomed in camera. This scoring you can really see. Yeah, and you can, let me back out a little bit. Let me back out. See if I can get it to focus. Not really. But there's good scoring in there. And I mean, if I put some pressure on that, that will just snap. And it's scored in all these directions. Very nice. So that way I can basically get one of these boards and just make 8 different PCBs from it. And I just designed it like that. I could have designed 8 different boards and done all that. It's not cheaper. It's, basically the manufacturers charge you for the size of the board, the layers, the amount of copper, etc. And sometimes they'll charge you for how many holes there are. If they're cheap, they'll actually charge you per hole, things like that. But anyway, you can do boards like this, or you can just do them separate. All right. So that is, and again, there's ENIG, and I wanted that because it's nice and smooth. I mean, that's very smooth as I rub my finger across it. All right, so let's see, what else we got to look at? Oh, this is cool. Let's take a look at this. So what this is, it's an IoT device, and so each one of these, basically there's an array of them, and they connect to each other here. So they're all the same, and then you kind of stack them around in a 2-dimensional grid, and they snap into each other. Each one's got its own processor, and one of them has Wi-Fi communications, only one of them, and the rest feed off of that one. So anyway, but just to show you how crazy you can make anything you want, right? Obviously, this is now. So what do we know about this? It's got a top layer, it's got a bottom layer, it's got parts on both layers, right? Okay, it's got so this one's a white board, so it's got white resist with black overlay or black silkscreen, right? It's got an ENIG surface, right? You can see that gold, that's ENIG. And then it's got the overlay on both sides. It's got parts on both sides. It's got through-hole parts, a few through-hole parts. You can see holes in the thing, right? Not too many, though. So this right here, this is a couple dip switches. That's what those things are. And then these are mounting holes, right? And then let's see what else here. This is the power connector. That's just one of those 2.1 millimeter power connectors. There's some maybe an LED. What is that? Oh, yeah, that's to allow me. So here's another debugging kind of thing. Let me show you that. Let's go to the zoomed in camera. So again, you're designing something here, right? And you're saying to yourself, well, you know, when I work with this, I want to try changing out this component. Well, here's the surface mount component, that's the final one, but hey, why don't I add a through hole one, and then I can put a header on here and I can just push in different components and try them out in real time. So again, a lot of what we do when we design circuit boards is we design things like all these headers, these are jumpers here. And this allows me to adjust how this thing works. And you can see these little codes here or notes to me on how this thing works. Master, slave, slave, master, blah, blah, blah. And you know, boot mode and all this. This allows me to do this. So in the final version, these may not be there, but in this version they are. So don't be afraid to put debugging stuff, test points and whatnot. We're going to learn more about that as we go. All right, so anyway, so that's that board there. All right, and again, 4-layer board. We can't see the inside layers. All right, but we can see the top and the bottom layer. But the cool thing is this is this is this weird shape because it goes in this artistic device which is designed by industrial designers. Now, one thing is if you try to get a board like this made in the United States, not going to happen. Very, very, very expensive. All these cuts, the 4 layers, the ENIG, the this and that, you're just going to pay an arm and a leg for this. Most boards in the United States look like this, right? They're green, right? They're green, they're rectangular, that's about it. You put holes in them, they don't like that. You put cutouts in them, they don't like that either. So a lot of times you have to go to a Chinese manufacturer or go through an American manufacturer. And again, I'm speaking from America's point of view here. If you live in India or Mexico or someplace else, then of course you've got a different situation. But in the United States, usually going to China is how you can get these things done for cheap. So you can find a manufacturer in the United States that goes out to China for you so you don't have to deal with it, or you can just find a Chinese manufacturer that does PCBs, and a lot of times they won't even charge for all this stuff. They're like, no problem. You know, we've got to cut the thing anyway, so we'll cut it. And so they don't charge you for all this. So this board in the United States might cost $500 a piece. In China, it's $3 a piece. I'm serious. So anyway, we're going to talk about when we get to building our actual products that we're going to design with Circuit Maker, we're going to talk about going to different websites and getting quotes from things like Seed Studio that you've heard of, or Osh Park. You know, people talk about those. I don't really use those that much because they can't do what I need them to do, but we'll take a look at those and some other ones, and then you just basically Google and go to get quotes. Okay, all right, so let's see. Do we have anything else I want to show you before we end up? Yeah. Let me show you one other thing here. And again, I'm just going around here trying to show you some stuff. Okay, so here, oh yeah, and here, this is that little charger. Where's that charger? This is that little charger we saw. There it is there. There's the PCB for it. Let's go look at that in the zoomed in camera real quick. Let me turn it here. Yeah, and this is actually a cigarette charger I designed, electronic cigarette charger a few years ago. So real small. This has actually got some 402 parts on it. Very painful. All right, so anyway, very, very small. Okay, now take a look at this. Let the camera zoom in. So here's how it comes. So NJPCB, and again, this is a good manufacturer right here. They do both PCBs and full manufacturing. They're a contract manufacturer, so you can go check them out. So what's this? This is a teeny tiny little circuit board. It's so small you can't even see it on here. So I don't think I have any loose. I don't think I do, so I'm gonna get one out of here for us, all right? So just bear with me. So I'm gonna open this package up. It should be open someplace. Yeah, it's open over here, all right? Now what I'm gonna do is I'm gonna get some needle nose pliers, and I'm gonna grab a couple of them here, and I am literally gonna break this off. Careful, careful. There we go, got it. So I got one of them. Okay, can't see it over here, so we're gonna go over here to the zoomed in camera. So there it is. So this one, and let me get this off here. I don't even remember what this was in particular. Let me zoom into it. Let me zoom into it and let me grab it with some tweezers here. Grab it with some tweezers for you. All right. So this thing is like, I don't know, 5 by 5 millimeters, and I don't know, I'm thinking this was some kind of LED, little tiny board, little LED board. And then I made some other ones that were very, very thin. This is very thick, that were very thin, that you put a tiny little microcontroller on. All right, so I've got some other ones over there, which are not where I can get to them, that have something where you can put a microcontroller. But just to show you, that's how they come. And you can see, obviously, I just don't really care about this because I've got hundreds of these things. So they come in this giant array and you just break them off because they're not going to cut these things off for you, right? And I don't know, there's probably, we could sit here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's like probably 400 on each one of these things. So I probably ordered, here's the interesting thing. Let's talk about this. So this little board right here, if you were to try and manufacture this in the United States, it would cost probably a lot, like $5 a piece. But in China, when I go and manufacture these, if I manufacture 100, it's like maybe 50 cents a piece. If I manufacture 1,000, it's like 10 cents a piece. So I manufacture 1,000 of the things, I get 1,000 for $100, done, right? Instead of getting 5 for $200 or $300, right? So I just build 1,000 of them. All right, and then I probably used 5 of these things, and then I just have these. So sometimes you buy an enormous amount of them, you get that price down. It's a kind of a weird thing, but it's cool. Okay, so let's go back here, and all right, so we're looking at this, and we're looking at the schematic here. Okay, so that was a whirlwind tour, and so this total lecture was a little bit long. But I think now that you have enough information to understand what a circuit board looks like, what kind of shapes they are, what kind of colors they are, what they're actually made out of, what through hole is, what surface mount is, what the different surface finishes is, Hassel and Enig, how we manufacture them. We've got the surface mount parts that have to be soldered on there. We've got the through hole parts that have to be soldered on there as well. So one thing that you can do also is go to YouTube and type in PCB manufacturing and just watch some videos. It's actually pretty amazing. It's astonishing, actually. Watching a whole PCB be manufactured and then assembled is actually astonishing. So you can get some 10-minute videos and kind of watch that. The final thing, and we're going to talk more about this obviously, is so we learned about Gerber files, which are the files, these things right here. So remember this, these are the Gerber files that have all these different layers in this Gerber format, right? The top copper, the bottom copper, etc., all these things. Then we also talked about the drill file, which is in here in that case as well, which just shows where to drill all the holes and the size to drill the holes. The other thing that we need, so we got the Gerber files, we got the drill file. All right, now, well, how do I get the PCB made? If you go to a manufacturer, they're going to say drill file, they're going to say Gerber file, and then they're going to say the bill of materials. Bill of materials, you can hear this a lot. What is the bill of materials? Well, the bill of materials is the actual parts cross-referenced to the reference designator. So if you look at this right here, U1 is a 555 timer. From this right here, you can't really tell what the package is of it. You need to know that exactly, right? So what is the package of that exactly? In this case, it's a DIP package. But they're not going to go looking through all this stuff. They just need to know U1, what is the part number, who makes it, so I can buy it. And I meaning their buyer. So you have to make what's called a bill of materials. Now, okay, this is one of my pet peeves about electrical engineers. They can be very experienced and they can make horrible bill of materials. A bill of material is something that it's your way to communicate to some engineer that's basically at a PCB manufacturer. He's doing this all day long. He's got hundreds of PCBs he's got to deal with. He doesn't want to go figuring your thing out. He's not a detective. So what you want to do is make it easy for him, right, or her, so that they can see what it is you want to do. So just make everything easy as possible. It'll reduce the amount of mistakes. So what I don't want to see you do is make a bill of materials that's an ASCII text file that just has a bunch of, U1 is this part and then that's it. Okay, I want you to take it to the next level so you never have a mistake. In all these years I've manufactured everything, I have literally never had a bad manufacturing run, not one. And the reason why is because I use really high level bill of materials. Let me show you. All right, so I just grabbed some random thing and I don't remember what, oh yeah. So this is for this. So this is for this thing. So this is a professional product. It's an industrial controller. It goes and it goes in ceilings, controls exit signs. So this saves people's lives. And someone's got to install this and connect it to 277 volts up in a ceiling. So this is not a toy, and you got to be pretty serious about how you build it. So here is my bill of materials. So I've made this little template in Excel, all right? You can make whatever you want, but it's got the project name, the part number, the Gerber files, the names of all these things, and I'm going to give you, as a manufacturer, a zip file, and in that zip file, I'm going to have a bunch of files, and they're going to have all these things in it, the Gerber files. Give them a copy of the schematic, right? They're not going to steal it. They can reverse engineer anything if they want. They need a copy of the schematic. A test suite. So when they build the board, someone's got to test it. They got to put software on it. They got to run it through various tests. So you're going to come up with a whole test system, write a document on that. That also is going to go in your manufacturing package, right? So, but even in the bill of materials, I reference that. So here's the thing: different engineers are going to be looking at different things, and I want to make sure wherever an engineer looks, he gets as much information as possible. The more information they have, the less chance they have to make errors. And when they do make a mistake, you can say, hey, it was in this file, it was in this file, it was in this file. You made a mistake, it's your incompetence, and I'm not paying for it. But if you don't have this information, they can say, well, we didn't have the information. You're right, my fault. I got to pay the $50,000 fee and throw the boards away. So more information is better. Engineers don't like writing. I like writing. I'm a writer, so it doesn't bother me. Do it once and get it done right. So anyway, you can see all these different things here. My name, my address, my email. Hey, maybe one email's broken and they email me that night and I don't respond to them. Put a couple different emails in there. Put your website, put your Skype ID, everything. Now, then there's assembly notes, note 1, note 2, and they got to read all these. That's their job. If they don't read them, hey, that's their problem. And then these are ECOs, engineering change orders, and it says ECOs shown in green in bill of materials. In other words, if you see something green, that means I need you to change that from the last revision. So engineering change orders, that's what these ECOs. So you can see, hey, R36 make it from 22K to 2.2K. All right, so we've got all these notes here. Now let's get to the meat of it, all right? So then I make this nice chart here, right? This nice Excel spreadsheet. So quantity, I need one of you 1, I need one of you 2, I need one of you 3. So here's the reference ID, the quantity, the manufacturer, the part, the length, the part description, footprint, package, etc. Assembly notes, right? So now when I hover over all these parts, one thing is there's a link to the part on DigiKey or Mouser or Octopart, so they can see what is this guy talking about. Maybe I wrote it wrong or whatever, but give them the link. Then describe the thing, right? More information, doesn't be redundant, right? Then assembly notes. Is there anything weird about this? Right? They're not mind readers. Again, they do hundreds of boards. They don't care about your board. So give them information. So for example, U6, it's a high voltage driver, 7-pin TO220. And I say solder to PCB, no screw and nut. So they might think, oh, I got to put a screw and nut here because it's got a hole in it. Don't do that. I just want it soldered. And I have my reasons for that because I think in some case it's shorted or something like that. So again, all these different parts, and then notice I have them sorted. So integrated circuits, here's all your transistors, here's your diodes, here's your rectification diodes, here's your resistors. Very quickly I can go through all this and I can see everything, and then all these little notes, you know, used in a control loop. So they must be 1% precision. So I tell them things, give them information. Why do these need to be 1%? Can't we put 5%? Well, no, because I said I want it 1%, but they might get cheap on you. You never know. But then I say it's in a control loop, and now they know if this is not 1%, it may make the board fail, which means it's on them if they don't do this. So again, put all these notes. Capacitors, protection fuses, all right? Then in the bill of materials here, I also put there's different options to build things with different step-up transformers and all that. Put all this information in here. Just talk. Just have it. It's a lot of information. Yeah, it is. But this is if you want to take it to the level of professional manufacturing embedded systems, this is what you got to do. And on top of this, I make a video where I describe the testing procedure and I write the test procedure down, right? Because many times you're talking to people that don't speak your language, maybe they don't read your language. So if you make a video of it, now they got video, they got a document, they got another document. You give them as much information, that way you reduce errors. Now, custom cable assemblies. Remember those cables we saw on it? So we got this board, we got these cables. Someone had to make these things, right? So again, my manufacturer made them, and here's how you make them. So I describe, number 1, ready lead. Number 2 is the test. Number 3 is the external light sensor. So here's the 3 things you need to make, guys, and then here's how you make them. What wire to use? What color is the wire? Describe them, and of course I make samples and show them, right? So everything out in painstaking detail, right? You know, very, very detailed. Different battery options, right? Because I want to control the battery a little bit, right? I want a Chinese battery maybe, but here's some batteries. If you can use these batteries, if you can find them cheap, or something that's equivalent, go ahead. All right, but here's their specs. All right, and then here, visual assembly notes. Take it to the next level. Here's the board. There's one of them I built. Looks like that. So now at a glance, so a lot of people are very visual. Oh, I see. That's where the transformer goes. That's where that goes. That's where that goes. I don't need to read this thing. If they don't read it, that's on them, but they can see it. Here's what the board looks like bare, right there. There's the front of it, right? Go down. Here's the cables that I made. So here's my sample cables. I made these myself. I photographed them. Here's the battery cable that I made, right? And then talking about the shrink tubing, here's the sample sensor board cable. Very nice. Now they see, okay, I understand. It's just that, it's just that, it's just that. A picture's worth 1,000 words and a video's worth about 1 billion words. All right? And that's it. This is a professional, AAA plus, awesome bill of materials. If you do something like this, I guarantee you will very rarely have a problem. If you make a little text file with a few little pieces of text and reference designator, you're going to have trouble. I guarantee it. And we're talking about a lot of money here sometimes. So please take things to the next level and do bill of materials like this if you're going to go manufacture something. If you take it to that level where you actually do embedded systems or electrical engineering. Okay, so I think we're done. I think we've talked about everything ad nauseum. So now what we're going to do is we are going to go and we are going to play with Circuit Maker and we are going to build these different circuits. This guy right here, this magic wand, and what I'm going to do is I'm going to sit here and design this for you in real time, and I'm going to speed the camera up. I'm going to figure it out as I go and see how I want to do it. And we're going to end up with something that looks just like this. I don't know if I'll cheat and copy or whatever, but the point is we're going to end up with something like this. We're going to do this one, we're going to do the next one, we're going to do the next one. Then we'll go through exporting files and doing Gerber files and all that kind of stuff and getting manufacturing stuff ready. But first we're just going to do the design, the layout, the circuit design, the layout, and the part selection. This is a big deal. So when you're designing with these tools, and you're going to see how this tool works, right, with part selection. So a lot of embedded electrical engineers, they just use a part someone tells them to use. It's like going to a restaurant. It drives me crazy. The waiter comes and you ask the waiter, what's good? Well, I don't know that he likes what I like, right? Maybe he likes, crawfish heads. I don't know, but I don't want to eat crawfish heads. Why ask someone else what they think? What you want to do is do what you think. And that means that I don't want to just take parts. If I type in a part and I let the tool tell me what it finds, I don't want to do that. What we're going to do is we're going to try and use DigiKey and Mouser to search for a part so we can see what its specifications are and its cost and its availability. That kind of gives us an idea. We can use these few parts here. Then we see if the part is inside of the database at Octopart and this tool. So we don't just go randomly grabbing parts out of the CAD tool. We go to our sources and see, can we get the part? How much is the part? Are you using a $17 LED instead of a 7-cent LED? This happens. I've seen this happen, right? So that's how we're going to do that, and you're going to learn that, and you're going to see my process as I design these boards to make them cheap and reliable, robust, and so that we can manufacture them, and especially if different parts go end of life or whatever, we can replace them. So we're going to do some of that also. So you're going to see that whole thing. So anyway, that's it. I'm done talking. I will see you in the next video. Bye. All right, welcome back, and we're on the final lecture, or series of lectures actually. And so now we're going to actually design the circuit board. So in the last couple lectures, we went through and we looked at circuit boards, we touched them, we looked at their construction. We got a working vocabulary of what things meant when we're talking about top copper, bottom copper, when we're talking about what's a via, blind via, hidden via, what FR4 material is, what routing is, what Gerber files are, all that stuff. If that does not sound familiar, definitely go back and watch those videos again so that you have an idea of what we're going to do. So what the plan is this. I've built 3 different projects. One is a magic wand, like a Harry Potter magic wand, a very low-cost version of it. So, then we've got an organ, a 12-tone organ. And then the final project is a kind of a Simon game, a matching game, if you're familiar with that, and lights up with colors and all that, and you kind of it plays a pattern of lights and colors, lights and sounds, and then you have to press the buttons to repeat the pattern. But I've based that on an Arduino chip, so it's also a microcontroller based project. The idea of these projects is to take you from something very, very simple to and kind of slowly increment the complexity. Because what we want to learn here is, where do you even start? So you want to design a circuit. You don't want to do it on paper. You want to do it in the computer. Then you want to select parts for the circuit, real parts that you can buy. You want to lay the circuit out in the schematic editor, and then you want to design the printed circuit board, and then you want to build the circuit board. So there's all these real things that we want to do. So this is a very complex process, and there's a lot of steps and a lot of decisions that have to be made. Now, as I was thinking about this and trying to say to myself how I'm going to do this, this is a course in itself. It really is. So each one of these designs took many, many hours to do. So the first one probably took, I don't know, maybe it took 10 hours or 20 hours. The second one probably took maybe 15, 20 hours, and then the last one probably took 20 or 30 hours, maybe more, the Simon game. So obviously I can't record myself doing that exact same process. There would be 100 videos just on that. So what we're going to try and do here is we're going to go through each design, and I'm going to kind of go through my thought process, and we're going to design it in real time as much as possible. We're definitely going to do the first two. The last one I think is too complex to do. It would just take too long, so we're just going to kind of look at it. But anyway, the whole idea is that we want to learn how to do schematic entry and PCB layout with the Circuit Maker tool. All right. Now, by no means am I an expert in Circuit Maker. I've been designing circuits for a long time and doing layout for a long time with other tools. But with this tool, I'm no expert. It takes many months and sometimes years to become an expert in any of these CAD tools. But the whole idea is, if you know one tool, you can usually pivot to another tool and get the hang of it in a couple weeks so that you can at least use it. And then, you're looking up in the reference and the help and looking at YouTube videos how to do things. All right. So it's a painful process initially, but I'm going to try, and as I go through, we're going to just do this trial by fire. I'm basically going to design things in real time, and you're going to kind of learn as we go. All right, now, a couple things. One, do not try to follow me with your tool as you're watching the video. It's going to be too hard. You're just going to be looking up, and I'm going to press some key sequence, and you're going to miss it, and you're going to get frustrated. Just watch the video. Just watch the entire design series for one of the projects, then go back and try to do it yourself and watch the videos again. This is the best way to do this. And I'll make an analogy. When you're in school and the teacher is lecturing on something really complicated, math or whatever, you spend all your time writing down and trying to keep up what he's saying. That's a bad idea. So what I used to do is not write a thing. I just listen to the teacher very carefully, listen to him very carefully. And then I would go study myself. I wouldn't even write notes. And I found that was much better, because what you're doing is you're trying to just copy all this stuff down and you're missing the lecture itself. So what's good is nowadays you can video things, and we've got video of this. So you can just watch this video after. So just take your time, relax, watch the entire thing end to end, all the different parts of it. We're going to have to break it up into many parts, and then go back and try and follow it. That's how I would do it if I were you, rather than trying to stop the video and play with the tool and all that. Just first do the whole thing once. All right. Second thing, the whole idea of this is for you to see the real process. So this is the real process. And so when we start off with the first project, it's a magic wand. We're going to go through in painstaking detail how you would do something like this. And that means we've got to do part selection, we've got to do price comparison, we've got to look at the sizes, we've got to see if they have footprints and symbols. There's so many details to doing this. And what this is like is we don't want to show you the easy cheating way. We want to show you the hard way, because when you get to it, you're going to be like, wait a minute, this chip doesn't exist, or this is too expensive, or this or that. So I'm going to talk about those things, as we go. All right. And then the other thing is, as I'm doing this, sometimes I'll speed the video up. If I do something redundantly, like if I copy something 20 times and each takes 5 minutes, I'm not going to sit there and just, let you watch just slow video. I'll speed it up. So anyway, let's jump right in. And the first thing that I want you to do is you should have already installed Circuit Maker. So if you haven't done that, go back to the previous couple videos and install it. Or, it's real simple. Just go to circuitmaker.com. You're going to create an account. So see this sign in thing here. So you got sign in, sign up. Go ahead and sign up. You need an email, you need a name, you need a password, and that's about it. It'll send you an email to your email account to verify you're a real person. Click it and then sign up. That's it. All right. So then you're going to go to Circuit Maker and you can do this from the web. So what you might want to do is what I like to do this. Because the help and everything is kind of online. Remember, this is a cloud-based tool. I'm on the website and I have the tool running simultaneously. So let's go ahead and let's just click sign in here. So I'm at Circuit Maker. I'm going to go ahead and sign in. Okay, and here's my login. So I've got my username and my password is typed in there. So I'll just sign in here, and then it puts up that page is not working. I don't know if that's just a browser caching issue. All right, and then here's kind of the landing page, and we've looked at this before, and we've got all these different things here. So one thing that I want you to do is, and this is a homework, go to documentation up here in the main menu. All right, and you can see there's all these different things here. All right. I really do want you to go through all of these. I've went through them all. I don't remember but 1% of it, but at least you go through it. The whole idea is to know what you don't know. And you may not remember what you don't know, but you'll know that it's there. You'll say, I remember something about that. So if you go through all of this, read all of this, and go through all these links, it really is going to help you. But what I definitely want you to go through is the Circuit Maker Video Vault. So if we click this, all right, and if I recall, yeah, so projects, collaboration, components. So if you click on this, I think it's going to jump. Yeah, and there's only a couple videos of each thing here. And these are embedded. So you probably just want to go to the YouTube version of it. All right. So if we scroll up here, you can, it talks about there's a YouTube site, Circuit Maker, and it's right here actually, if I can find it. Right here. Yeah, so it's actually just Circuit Maker. So if I click Circuit Maker, and then you'll see there's these different videos here, and we'll click on their videos. Here we go. And you can read through and try and click the actual design videos, okay? All right, so anyway, so that's that. So let's go back here. All right, and go back to this little video gallery area. All right, so now we'll click back to Circuit Maker and just get back on this home page so we're get straight here. Okay. All right. So where do we even begin? So we're just gonna jump into this and start doing stuff. All right. So the first thing is I've already launched the tool. So I've got the desktop tool here. So take a look. And another thing, I've got this QI press running right now. So if I hit the over here in the left, you can see what key presses I'm pressing here. And that's going to be important so you can see what's going on with Circuit Maker and try and figure it out, what I'm pressing. And sometimes I have to try things myself. I don't have this all super memorized. All right, so I'm running this QI press little tool here that puts that up there, and hopefully it doesn't crash. If it does, I'll just restart it. But anyway, over here on the left, you should be able to see what's going on with the keys. Now, I've already ran the desktop version of Circuit Maker. This is what we actually are going to work in, right? And it's sitting here. It's waiting for me to log in as well. All right, so what I'm going to do here is I'm going to go ahead and log in, and I'll go get my password, which I purposely make them so complex I don't remember them. And we'll put that in there. We'll sign in. And you can see this page right here mimics this page, very similar. So the web view is very similar. You just can't do anything. You can't work in the web view, but you can look at everything with a web view. All right, so let's go, and we can do this with either the tool or the web view here. But let's start here and just kind of do it with the web view. All right, so you can see I've got a few projects in here. This Cardwino boy is not part of the class, it's just another project, so let's just disregard that. So we've got our 3 projects here that we care about. One is called Crash Course Electronics Magic Wand, one is 555 Timer Organ, and this one is Simonduino Color Match. All right. So all of these things are the projects that we're going to go through, and we're going to actually design these things. All right. So the question is, how do you get access to this? All right. So once you have your account, you're going to go to your projects, you're not going to have anything. So the first thing that you need to do is you need to find these things. All right, so you could type in their full name here, but another thing that we can do is we can do a search, and if we can find the search projects, I believe, yeah, if you just go to projects in general, now we're going to search, just use my last name, Lamoth. I think there's only one of me on Circuit Maker. Yep. And all my projects will come up. So again, we don't care about this Cardwino Boy one. We only care about, and I don't know, maybe you may not even be able to see this because this is a sandbox project. So maybe I can see it, but I don't think you can. We'll see. Anyway, so here's the 3 projects. So now what I want you to do is click on this first one, this Magic Wand project, and give it a time, give it some time. Everything is very slow. Okay, so now I don't want to edit this. I don't want to delete it. I don't want to follow it. What we're going to do, both of us, is we're going to fork this. All right, and it's basically just we're going to copy it. So we don't want to mess with the original copy. You can't mess with the original copy. I can, but you can only mess with a forked copy. Now this forking process is a little bit weird. It's just should do a copy, but it seems like it takes a little time before it populates and updates your project view, so you kind of have to bear with it. In any event, so what we're going to do here is we've got follow, edit, delete, and I don't want to do that. So over here, design files, fork, and open. Okay, so what I want to do is I want to fork this, and we're going to see if this works correctly. So when you do this, it says create new fork. So Crash Course Electronics Magic Wand. And another thing, Crash Course should be 2 words, but it doesn't really matter. Crash Course Electronics Magic Wand, and then what I'm going to do is I'm going to call it work copy. And you can see I've already done this. All right, so work copy, and you can call it whatever you want, but I would call it something similar since it's Crash Course Electronics Magic Wand. All right, hit enter. Okay, that progress bar is good news. If we don't see that, something has gone wrong. Okay, so now it's copied it. So now if I go back to so now it's putting it up here, and it's, you know, there are no design files to display. That right there doesn't make sense because we just forked it, so there should be design files. And this is what I mean. It takes a while for this stuff to propagate through. So let's go back home. Go back home. We'll go back to my projects. All right, so now here is the original because it's got this nice picture, this 3D picture, and then each one of these has a picture. So here is the forked copy of this. So if I just click on this and give it a second, all right, so now you can see it says work copy. So now we know we're looking at the work copy, all right? Okay, so that's good. And now look, in design files, they're actually there. There's the schematic and there is the circuit board. Just a moment ago, they weren't. So it took a minute to propagate through the system and the cloud and the database and get back to us. All right, so this is good. Now, what we can do is we can say open here, and what that will do is it'll launch Circuit Maker and then push this into Circuit Maker and open it. But let's not do that. I just wanted to use this as a tool so we can kind of see what's going on. What I really want to do is let's just go to Circuit Maker. Now I'm using the application. This is Circuit Maker application. I've clicked on it down here just to make sure you get that. All right, and there it is. Okay, and again, we logged into this, and it kind of put us to this landing page. And again, we can go to My Projects. All right, and sure enough, there we go. There's the 3 originals, and then here's this working copy. All right, now one thing that I want to do is this. So we can load as many projects as we want over here in this project list, and this IDE is, you know, very similar to many IDEs you may have used for programming or different things like that. There's a number of windows, and you can drag them and kind of attach them to different places and so forth. But the projects window, which will kind of start off in this position here, is the one that we care about. And forget this free documents. This is just documents you may be working on of different things. So what I want to do is this. So check this out. So what I'm going to do is I'm going to click on, this is the original. This is the original that we just forked. All right, but I have a fork of it. You don't have a fork of it. So now I'm going to say open design. So this is the original. And you can see it says 1 forks. So now when you do this, there might be hundreds or thousands of forks, right, of all the different students that have forked this. Okay, now, Crash Course Electronics Magic Wand. So this is the original, Now let's go back here to let's click up here and there's lots of ways to do things. We can go back, we can go home, we can do whatever. We'll go back to my projects again. All right, and then this, we know this is the copy of it. Now, what if you hover over this, it says Crash Course. Let's do it again. Crash Course Electronics work copy. So we know that that's the copy, and then plus it's got the design and not the nice picture here. So we're going to click on this also. All right, and now we're going to say Open Design. And the reason I want to do this is I just want to show you. So here we go. We got Crash Course Electronics Magic Wand. There's the original. And then we have Crash Course Electronics Magic Wand work copy. Okay, and there it is right there. All right. And then currently in both of these projects, so this is kind of the project name, and then it's a container. So it may have a number of different subdirectories, source documents and other things. In the source documents, I've created two files. One is the schematic, and it always has the extension SCH-doc, schematic doc. And then the circuit board, the layout, has this .cmp PCB doc. All right. And then I'm using this naming convention CCE for Crash Course Electronics, Magic Wand 01, because it's the first kind of version of it. Now, here's the interesting thing. Now, look over here in the copy. So the copy uses the exact same names, but this file is not the same as this file. It is a copy of it. It's a complete separate copy. It's been forked, and I have a whole another fresh copy of it, just like you will. So the point is, what I want to do is I want to show you something. So let's say that we go over here, and here is the copy, or the forked copy. And let's go into the schematic. So I double click and the schematic opens up. And again, I'm just going to show you a couple things. I want you to make sure you understand where things are and what are copies and not copies. All right. So I'm going to zoom into here, and I believe it's if we hold Shift, no, if we hold Control and then the scrub wheel. All right. And then if you right click with nothing, then you can drag things around. So that's a very common kind of interface. All right. And then there's all these capacitors in design, and we're going to talk about all this. Right now, I'm just showing you a couple things. I just want to make sure you can fork things properly and things make sense. So see this capacitor C2? Let's make it a different value. So I double click on it. And again, you don't know how to do any of this yet, but I want to show you that the forked copy is different. So it's 0.1 microfarad. Let's make it 0.01 microfarad. All right, and then I'm going to save this with Control S. That always works. Control S, save. All right, now what I'm going to do is where it says Crash Course Electronics Magic Wand copy, that's the actual project. Okay, I'm going to right click on it to get a typical context menu, and I'm going to say Save Project. Let's save it, make sure it's saved, and then we're going to commit it. This pushes it to the cloud and synchronizes everything. So you always say this commit, and then it says, hey, you've modified these files. Are you good with this? Before you commit it, yes, I am. Go ahead and do it. All right, so now you notice all these green check marks. That means everything's committed, everything's up to date. All right, so this has got this 0.01 microfarad here. Now let's go to the original. Here's the original project right here. Let's open up its schematic. All right, so we're going to now be careful. Here is the forked copy. It's got the same name, and I'm going to open this one up. I'm going to double click on it, and then it selects. One thing you're going to notice is because it's cloud-based, things don't happen instantaneously. It's a little bit disconcerting at first. When you click on something, you're used to it being highlighted. It's not, so give it a second. It'll highlight. Don't click it 8 billion times. All right, so here is the original copy. Now, look at this. Control and scrub to make this bigger. There's that C2, it's 0.1. Now here's this version, it's 0.01. The file names are exactly the same, but they're a different copy of it inside of this new container, this new project, which I own both copies of this now. So I have both copies of this, all right? So that's what you're going to do. And so what I want you to do is, I want you to make a forked copy of this project, and you're going to load it up in here so you have something to work with, all right? And then what you're going to do is, that's going to be kind of the reference design. And then we're going to create another new design that we're going to actually build this in, because this is already built, right? And we want to kind of do this again. But we need something to have a reference so we can kind of click over here, right? So what I'm going to do now is I'm going to close the original. So I'm going to close the original here, which close project right there, and I just right clicked. All right, I have the working copy right here. Let's go back here, and I'm going to fix this capacitor value make it 0.1 back to what it should have been. I'm going to save that. All right, notice it's got that little exclamation, means you know, you've changed something. All right, I'm going to go ahead here and I'm going to commit this project. Again, it's going to show me what I've modified and allow me to commit or not commit certain elements of it. Okay, good. Now I'm all good. So now here is my forked version of this project. So now what you're going to do, I want you to do the same thing. So I want you to go and you can do it in the application or you can do it here. I want you to go and fork. So let's go back to projects and go to my projects. And you're going to search